I see you are all here. You look like it. So you survived the drinks and karaoke and whatever yesterday. I think it was quite some fun. And after Leslie, the real business star with hard work. So we cannot do much more than wait. While we're waiting, I don't know, any of you has a question or comment, after the first day? Of course, the first day is always a little bit special, more on formalities than on, but, we did have some good, interesting presentation of the various HPC system around the world. So if anyone has question, comment, suggestion, you can speak while we're waiting.
You can just tell us.
So
Okay.
no question? Everyone is happy?
Hopefully.
Great. It's still not on?
It's not there yet. But anyway, I would like to welcome you all for the second day of the ASEAN HPC School 2023. Hopefully you enjoyed the first day yesterday, and for the second day there will be the first session. There will be ASEAN Turing Laureate interview by Ina, and will be introduced by Fabrizio, and after that we follow by a talk about quantum technology by Professor Jose Ignacio Latorre. He's already with us, so there will be no problem with Zoom, so we can have him personally here. And after that, because we talk about HPC school, high performance computing, so there will be an introduction. There will be introduction day today for the introduction day. First, we will have an introduction to parallel programming. Hopefully those who from life science and earth science, climate and urgent computing doesn't too afraid of programming. And it's just introduction. So at least you know what you can expect from using HPC for your problems. Hopefully that will be some improvement. So, and after that, it will be followed by Bertmore. He's somewhere behind. Oh yeah, he's there. Okay. Bertmore will give some introduction about how you do the performance analysis. You find your problem probably in sequential model, and then you do the parallelization, and what can you expect from that? If you can do the analysis, obviously you can do the optimization after that and find where to tune and how to tune. There will be given by Dr. Bertmore. And that will be after lunch. So hopefully you're not too sleepy for that. After the coffee break, there will be an introduction to artificial intelligence and machine learning, because nowadays HPC mainly used for AI and machine learning, and it will be given by Dr. Muhammad Wahib. He's already with us. So we will have only, unfortunate, because Dr. Leslie Lamport still in US and he cannot travel here, so we will have him on Zoom. But after that, we will have all the speakers with us here in this room. So enjoy today, and we're still waiting for Leslie Lamport. It's not here yet. So probably you can read his profile and prepare some interesting and intriguing questions for Leslie Lamport. Yes, I am collecting now, and because there will be some check and profile, and we will distribute it by Slack, because everyone is already in Slack, so we will distribute in our Slack. Sure. Any comments? Yeah. Yes. Yes. Oh yeah. Sorry. Oh yeah, the Fugaku. But for the first Satoshi Matsuoka, it's not there yet. I will. Yeah. About the Fugaku, how to use Fugaku from Georgie is already uploaded in the shared folder. You can download there in Fugaku. But I have the Professor Satoshi Matsuoka slides and slides from Andres Jensen yesterday. So it will be posted in slide. Any comments? Okay. I'm sorry to inform you that probably there is some problem with Dr. Leslie Lamport connection or something else. He doesn't used to be late. He's usually earlier. So we switch to the next session. Hopefully he can join after that. I would like to introduce you to Professor Jose Ignacio Latorre. He's Director of Quantum Technology and Professor of Department of Physics, National University of Singapore. So, and he will give us information about quantum computing. The floor is yours. Please, please go ahead.
Hello, good morning. Oh, sorry. Good morning to everybody. Let me first thank all the organizers, Aldo, Fabrizio, all the people here, for the invitation to talk a little bit about quantum mechanics. As you know, certainly there is a revolution associated to artificial intelligence with the large language models that requires an amazing amount of computing. But it is a broader subject, what will be the future of humans in terms of computation. And what I will try to do today is a very, very brief introduction to try to convey the idea that humans ultimately will be computing with the laws of quantum mechanics, not with the laws of classical physics, which is what we are doing now. So let me say it in another way. We are living, although it doesn't look like that, we are living the very early stages of computing. Humans are living the very early stages of computing. So let me go ahead little by little. And the first idea I would like to tell you is how come that now, in the 21st century, we are now discussing about quantum computing. Let me try to tell you about that. Well, the very first idea that may not be known to many people is that by the end of the 20th century, we have achieved amazing control of nature. Let me be more precise. So if you look at how humans have controlled nature, we have tried to do that all the time. We wanted to have a meal. We wanted to work in the fields with our instruments. We develop instruments. So what is so special about the turn of the century? Well, it's the fact that the 20th century was the century where we developed lasers, where we we understood the structure of the atoms in detail, that now it's a time where we have instruments based on our knowledge of the 20th century. And what is providing for us is a new way of controlling nature. I give you an example here. I've chosen a picture which is not computing on purpose. So this is a picture of, maybe you can see it with the two white arrows here pointing to a point. Okay, this is the control of a nanoparticle that we make it levitate, okay, there. And then we can do any kind of perversion to that particle, okay? In particular, we can charge it electrically, we can charge it magnetically, we can control its position. So actually, this nanoparticle is an accelerometer. It measures the accelerations. And this is one of the very many ways we are trying to obtain navigation instruments which are deprived of GPS connection, so that we can navigate even though we don't have GPS. Because we know exactly where we are. We compute acceleration, therefore the velocity, therefore our future position. And not with this system, which is a levitating particle, but with NV centers, okay, measuring the magnetic field of the Earth. We have done, well, not me, definitely. There was this summer the first flight, okay, from the Air Force, which was deprived of GPS, okay, following an attack 3 years ago of jamming of the signal of GPS. So this is the kind of new technologies. We control matter at the level of individual photons, individual electrons, individual atoms. So we go from a coarse-grained control of matter to a refined way of controlling matter. And we are doing that now, so it's really, really special. So let me elaborate a little bit more. So for instance here, I brought to you a picture. This is from the Center for Quantum Technologies in Singapore, the center that I direct. What you see here, if you have a little bit of imagination, and if there is, I know there is some people from Singapore, this is the merlion, the fantastic animal that represents Singapore. What is different here is that it has been built atom by atom. So this is a cold atom, gas. We call them cold neutral atoms at 4 Kelvin. And there we use tweezers, and we pinch atom by atom, and we move them around. And then we change their properties. So here is a control of a lot. We can control more than 100 atoms at present. The records in the planet is around 200 atoms. So imagine, they are there floating. You pinch them, and you move them, and you change them. You make them interact. So just to give you another hint of what's going on, last week it was announced from Harvard, Michelle Looking, the first logical control knot. That means that every qubit, I will tell you about qubits later, it has become a logical qubit, so there are very many atoms representing 1 qubit, and on top they have done the first control knot operation, which is error corrected with these atoms which are floating in the air. Okay? It's really, really spectacular. I love to present the history of science so that you take it a little bit more of conscious from the first equations. Our first equations come from the 17th century. Okay, the zero, okay, probably coming from India, and in Europe in the 12th century, Fibonacci was the first mathematician to write 0. Okay, the first numbers 1 to 9 were written in 980, and they came into global knowledge through the school of translation from the Arab to Latin and Greek with a king that was called Alphonse X the Wise. So the first equations, real equations, is 17th century. It's a rationalism. It's a time where people, well, in particular, philosophers of the time, Descartes is the big name, reduce everything to the least amount of assumptions you need, the postulates. So building a scheme, a complete building based on postulates, comes from the 17th century. For us, what I'm writing here is the history of the 20th century. Everybody talks about the wars of the 20th century. There is a different narrative to the 20th century. On the top line, you see quantum mechanics. The first equation, due to Planck, Max Planck, was written on the 7th of October of 1900. Okay? The first postulates, oh, not my fault. Not me. So technology is progressing a lot in the lab, but not in the classroom. I continue. Oh. Still not?
Anyway, I can share you the links. So, because Professor Latori is also in the Zoom. Zoom is still working, and while still waiting for the connection to the monitor.
Okay, otherwise it will take forever, so I keep talking, okay? So I was mentioning that the first quantum equation is 1900. Okay, here it is. The postulates is 26 to 30. Maybe you know the guy who wrote the first book with postulates. It is John von Neumann. The von Neumann architecture of computers was really a brain of the 20th century, von Neumann. In 47, we get the first transistor. So all the industry that we are here, the HPC, comes from the fact that we applied the laws of solid state. So the PhDs that Niels Bohr directed in the 30s became fields: condensed matter, solid state, atomic physics. So the transistor is 47. Lasers is in the 60s. All our communications are lasers. All our communication. A lot of medicine, a lot of, refined control of positions is done with lasers. I mentioned factorization. You will understand later why in 94. It's huge for computing. I also added www, the web, because it was developed at CERN, at the particle accelerator, and this is why it's for free. The reason why you send mails without paying a tax is related to the fact that this was developed in the public sector. The first quantum gates, 2005, and as I said just before, the first logical quantum gates achieved in 2023. Now, on the bottom line, you have computer science. So in the 30s, you have the first ideas of Church, Post, and Turing machines. The first machine, ENIAC 46, not with transistors, too early for that. Then you have the theorems of Shannon, the ones that we are using for any communication, for compressing the Temple-Leaf algorithm to compress. This is Shannon, based on Shannon's work. The classification of hard problems into NP, non-deterministic polynomial, and polynomial. This is in the 70s. And deep neural networks started in this millennium, and later on, we have now this advanced artificial intelligence. It doesn't take a lot of imagination to see that we are bound to bring the two pieces of progress together. The fact that we are controlling the elements of nature better and better, and the fact that we understand better and better how to compute. The two things come together. Now, let me go a little bit faster. So, in summary, what I'm trying to tell you is that quantum mechanics had 1 century to develop postulates on the first applications, and those are now our instruments to build better machines. And this is what we are doing now, and essentially, we divide it into quantum computation and simulation, quantum communication and security, quantum sensing and metrology, and finally, quantum and artificial intelligence. And just because I'm talking to you guys in HPC, let me make a comment. I mean, computing is behind. Look, this is a TV of the kind when I was a kid, okay? I lived in a building, okay? A very humble family. And my parents got the first TV. Everybody in the building came to see the TV, you know? And this was a TV of this sort, okay? Look at the brutal way. It was generating beams of electrons colliding against the screen to generate a little bit of light that would go into my eye. For the same price, my eyes were receiving zillions of electrons. Wow, there. Now we have LCDs. We stop using electrons. We use light for a screen. And this is why this is so thin. No? You don't have electrons being beamed against the screen. I use these kind of phones myself. A real phone with electrons. Okay, you would take delays when you talk to the people. And now we all have these smartphones, okay? So we are using photons to connect. And we, at present, are using electrons to compute. What a mistake, okay? They heat up, they are expensive to move, they are not the natural way to compute. But we still don't have the technology. We are working very hard to make computations with photons. The day we do that, the cost of energy will drop by an infinite amount, okay? So computing will be essentially for free. Okay, just like now, communicating is nothing. Okay, because photons are massless. Okay, they are massless. They don't have a mass. They don't have a charge. They are not attracted by anybody. They don't get captured by electrons. They don't have friction. So photons is the ultimate way to codify information. We have done it. We have the TV and the phone codify information in photons, but only for transmission, not for computing. Well, let me now move. I hope I convince you that we are living in the early stages of computing. Okay? We are privileged, no? Because the infancy is the happiest moment of humans. So we are living the infancy of computing. So let me go a little bit deeper. Physics and computing. As I said, the liaison, the relation between physics and computing comes in the 30s, 1930s. And there is one sentence, which is that information is physics. If you want to save information, you need a device to save it. If you want to modify information, you do need some mechanism, some machine, some computer to do it. If you want to transmit information, you need to codify it into a physical degree of freedom. There is no way you disentangle the abstract information from the practical information plus physics. So you may have courses on computer science which are very abstract, but when you go down to do it, it's physics. So this is why we have problems. Why I only know about the Barcelona Supercomputing Center. I can tell you that a non-trivial piece of the budget is just electricity, okay? Because we have to cool down the machine and we have to compute. Both things need energy. Now, what if we try to go to the world of the most smallest thing? Well, we try to mimic what we did with classical computing. We found a way to codify a bit of information, a 0 or a 1, which is a physical system. Let me represent it like an arrow, which is a magnet that carries, I'm a 1, I'm a 0. I'm pointing up, I'm pointing down. Okay. But if instead of using 1,000,000 atoms or 100,000 atoms that we are using in classical computing nowadays, we go down to 1, what happens? When you go down to 1, the laws of classical physics are no longer there. And they are no longer there for the good, for the bad, for whatever. Simply the world does not obey classical laws. It obeys quantum laws. So the big surprise is that the world of the smallest, it is not constrained by having an environment that forces you to take a global position like the magnets. But you have extra freedoms. I will not give a course here, but let me tell you that I cannot prove that. It's a postulate of quantum mechanics. Postulates cannot be proven. Okay? They are the basis of the building. We have not found any way to describe the microscopic world except by taking a number of postulates that we have checked once and again all the time. So the postulate, one of the postulates says, it is called the superposition principle, okay? It says that if you have a microscopic system and this guy can be, let's say, in a state which is a spin, a magnet pointing up, and it is possible to have this spin pointing down, the postulate says that any superposition of these two states is a valid state of physics. So that this spin can be in the superposition of being pointing up and pointing down. I'm representing that with 1 over square root of 2, 0 and 1. So here is an element of quantum mechanics to describe that this guy is not classical. We change the notation. In classical physics, we use 0, 1. In quantum mechanics, we put this bracket, okay? A vertical line, a zero, and an angle. This means it's a quantum state. It's a notation, okay? So this is what we call a quantum bit, an element of nature which follows the laws of quantum mechanics and therefore can be in a superposition of 0 and 1. So to be more precise, any position of 0 and 1 is valid, and on top there are complex numbers. So here you have that in general, the state that I call psi, this is a generic qubit, can be, and I write cosinus of theta half 0 plus exponential I phi sinus of theta half 1, because this is the 2 degrees of freedom I have. It has to be normalized, the two coefficients square add up to 1, and the global phase, it is irrelevant. So we have 2 degrees of freedom, and they can be mapped to the surface of a sphere. So this is usually called a Bloch sphere. Bloch, again, in the early 30s, one of the people working with Niels Bohr. And that represents in full generality a qubit. So a qubit is like, instead of having a discrete degree of freedom that only takes 2 values, a qubit can have infinitely many values. Actually, 2 real numbers are sufficient to describe it. Okay, the theta and the phi. So that means that one qubit has an infinite amount of possibilities in its side. It's a hint. It's a hint that this is amazing, no? That we are entering a completely new territory. We have no idea what is waiting for us. And there is no choice. This is the minimal amount of information in quantum mechanics. We cannot have less than this, okay? You have to work with this. In a next step, okay, if this is a magnet, a spin, and it is a 0 or a 1 or any superposition, what happens if I apply a magnetic field? Well, it rotates. You know, a magnetic field and a magnet, poof, rotates. So I can transform a qubit into one state to any other. Well, that's a logical gate. I can go from 0 to 1 if I want. I want from anything to anything. In particular, I've selected one possibility, which is this U sub H with the name Hadamard, okay, one of the mathematicians, old mathematicians. That takes the 0 into 0 plus 1, but the orthogonal state, which is 1, should go to 0 minus 1, so that if I do the scalar product, I get they are orthogonal. Because any law of nature, okay, is a unitary matrix. That's another postulate of quantum mechanics. Evolution is a unitary evolution. Unitary matrices map basis onto basis. If the first 0, 1 was a basis, the next one should be a basis, therefore orthogonal. And below, I have an interaction between the magnets. They are now themselves interacting. So what is the net effect? I may have a gate like a control knot. I may have 0, 0 to 0, 0, 1, 1 to 1, 1, but 0, 1 to, well, you know, the control knot, the XOR gate or C knot. So here it is. I codify information in the ultimate elements of nature, and I use the laws of nature to process the information, let it be a single qubit gate or a control knot gate. So I'm starting to build a language of programming, okay? Okay. Now, you may wonder for a second, I mentioned before that it's very difficult. It has taken us 1 century to go down to the single guys. Why? Well, because if I do like that, you know, I've taken 10 to the 18 electrons from the atoms by doing like that. And then, poof, immediately they recombine. Nature is a crazy place, really crazy, okay? But we don't see it because we are big. What is the difference between the small and the big? Well, the small is extremely hectic to live in the small world. The macroscopic world, we take averages. So what happens is that if you leave one guy there, immediately it interacts with 10 to the 23 particles, poof, and it changes its value. So whatever I prepare, I lost it. Why? Because of the environment. Okay? So as soon as you put one guy in the middle of the mess, it loses its properties. So that is the key why it was so difficult. But now it's also the key why it's so useful. So we can do computing with these guys if we control them. But we can do other things. We can do a sensor. Because if I prepare a spin and I see a change of the spin, I'm detecting who changed it. So I have the best sensors. And that's what I mentioned before about NV centers using to fly without GPS. We use the changes of the qubits to detect who is changing the qubit. And also for communication. Alice wants to communicate with Bob. And she codifies the information on a qubit. It's a fragile qubit. It's a poor qubit. Suddenly, Eve wants to drop. So what happens? That Eve cannot avoid changing the value of the qubit. And therefore, Bob receives something that has been modified. So we have created protocols of communication based on the trivial fact that if Alice sends something and Bob doesn't obtain exactly the same thing, they know that Eve is eavesdropping the message. And this is called quantum communication, or it is used for quantum key distribution, as I will mention later. So for the same token, if you go to the microscopic world, you have quantum computing, quantum sensing, quantum communication, all of them. Just a second, this is the structure of the center in Singapore, and you can see it's divided in quantum communication, quantum computing, quantum sensing. And of course, advanced instruments and basic science. Never forget those things. So this is the structure of all the centers in quantum technology in the world. Why? Because now you see, because of the fragility of the qubit, we can exploit it. Okay, and now let's go to supercomputing. What if instead of having one qubit, I have n qubits? Well, according to the laws of quantum mechanics, I can have any superposition. So I1 stands for an index that says its value are 0, 1, the basis. I2 can be 0, 1. I3 can be 0, 1. So how many coefficients do I have? Well, I can have 2 for the I1, 2 times 2 for the I2, 2 times 2 times 2 times 2. I have 2 to the n numbers, and they are complex numbers. So n qubits contain as much information as 2 to the n complex numbers. Okay? So this is called the Hilbert space, and the Hilbert space is a huge place. It's an exponentially large space. If you can codify information in the Hilbert space, you have an enormous amount of space. If you can manipulate it, you have an enormous potential of manipulation. On top, if I do one action on my n qubits, I send a magnetic field, it acts on all of them simultaneously. So it does one by one on every superposition. So a quantum computer is a massive parallel computer. Let me be more aggressive. It's not a massive parallel computer. It cannot not be a massive parallel computing. So either you understand how parallel computing works, or you cannot do anything with a quantum computer. Okay? It's given by nature. You cannot change that. I give you an example that now one of the problems we have is that on the real chips we are making, we make a control knot. We have the information spills, the interaction spills around, and we do have what is called crosstalk. So actually what is happening is that all the qubits are reacting to our signal. And we have to try to avoid that, okay? Okay, so if I want to put numbers so that you keep something in your memory, if you have a total of 37 qubits, the amount of memory is equivalent to 2 terabytes, okay? 2 terabytes, 37 qubits. 50 qubits is the limit where there has been no simulation, exact simulation of quantum mechanics ever. You may remember that in 2019, Google presented a paper where they use a bad name, they use it supremacy, quantum supremacy. Let's call it quantum advantage. It was at 53 qubits. The 51, 52, and 53 were numbers that there was nothing to be compared with. And this opens many, many questions. Imagine we have a quantum computer and we start to explore 70, 80, 100 qubits. We don't have anything to compare with. We will have to trust the quantum computation. We don't have a second way of getting the same number. Okay? It will be unexplored territory. Okay. By the way, we have an ongoing discussion with Fugaku, okay, to bring the largest possible simulation of quantum mechanics into a supercomputer. And we are developing the so-called tensor networks, which is the best technology we have to represent quantum states there. And we hope, okay, well, let's see how far we can go, but don't expect that we will go anywhere beyond 50 very far, okay? It's exponential, it's 2 times 2 times 2 times 2. So it's impossible that a classical computer will catch up. But it's important to know exactly where is the limit, where is the boundary, okay? So now let me take a further step. Let me imagine that a percentage of you get enthusiastic. They say, hey, man, my work today is on HPC, but maybe in 20 years, in 10 years, maybe I will be a quantum computer specialist. So let's imagine that. So what I will now try to do is to tell you that you need to work very hard, okay? Because the quantum logic is not at all the same as the classical logic. And I will give you some examples. First, I name them. First, you work with complex coefficients of superpositions. You have interference. You have all operations are linear. All operations these use are reversible. If you want to compare to any paradigm in classical computing, you have to go to reversible computation. And all the measurements, turns out that there is another possibility that says they are probabilistic. So how do I work here? I mean, nothing is, the world is falling apart. Let me show you very clearly with a trivial example how subtle the changes become. Imagine I have a quantum computer that says it's a multiplication subroutine. And I enter with my qubits and I represent 1, 1 for the 3 and 1, 0 for the 2. And I want to multiply 3 times 2. So imagine I have that machine. I call it my multiplier. Those will be physical actions that will deliver the 6. Okay? Well, this is impossible. Why? Because it's not unitary. Because if I have a 6, I have no idea whether I came from 2 times 3 or 1 times 6. And because this is reversible, it cannot exist. There is no way to multiply in a reversible way trivially as we do classically. So what we need to do is to keep memory always of one of the two terms. So if I have 2 times 3, I may go to 2 times 6, because then I can go from 6, 2 to 2, 3. It's a unique. Why is this so? Because laws of nature are reversible. It's not my choice. It's a fact. So you see, the fact that we multiply on a classical computer is a result that the environment makes irreversible our actions as a result. Let me show you another problem. Very often you have A equals 4. Let me save A. So B equals A. And then I proceed with A. I keep a copy of A. So copy. Can I copy a state? Can I go to 2, 0 to 2, 2? Well, it is obviously no, because I don't know where the 0 came from, no? Well, you may argue, well, in one particular case, I could always send it to 0. Well, there is a theorem that says that this is not so, the proof is very simple. It is that I have a copying machine for 2 states. A is the ancillary qubit. It's empty, so I copy whatever I want there. It's like a Xerox machine with a white base. And it turns out that you can see that if you clone, because of the linearity of quantum mechanics, you enter in a contradiction. The clone state is not twice the original state. This is the no cloning theorem, okay? There is an obstruction in nature to clone a state. There's no way you copy an unknown state. So how do I make an algorithm if I cannot copy, I cannot multiply, I cannot do anything? Well, on the other hand, I have superposition. So simply is that we have been trained in classical computing. We have been trained all our life in adding, subtracting, multiplying. We have never been trained in superpositions and irreversible things. So nobody is ready to code in quantum mechanics. Nobody. Okay, it takes really training there. Okay, I mentioned also that measurements is probabilistic. This is a postulate of quantum mechanics. Okay, so can I see any quantum algorithm? Because it seems it's impossible. Well, there are not that many that prove something non-trivial. I've chosen the simplest. So we represent the qubits as lines. Left to right is time, therefore the gates, the sequence of gates. And this algorithm I first apply on the bottom qubit, a Hadamard gate, the one that I showed you before. So if it receives a 0, it sends it to 0 plus 1. And the second is a control knot on the upper. So I end up 0, 0 goes to 0, 0 plus 1, 1. And therefore, I have what is called entanglement. 0, 0 plus 1, 1 can never be written as a product of 2 terms. And this is the basis for the so-called violation of Bell inequalities. This was given the Nobel Prize in 22 for the people that started to do it in the 70s, last century. So Zeilinger, Clauser, and Aspect. They did these states by decays of atoms. Now we can do it within a quantum computer. We do it on a quantum computer. Okay? The other one is even more subtle. You know that the algorithms, or the problems, sorry, are divided in categories. There is a huge category of problems which are called oracle problems. Oracle means that there is a black box that I can ask a question and get an output. But I don't know how the output is computed. I have only access through questions. So the triangle is my oracle. I can ask with the 0 or the 1, and I get back f of 0 or f of 1. So I ask a trivial question. Is the oracle even or uneven? So it is giving me the same output, f0 equal to f1, or it is giving me a different output, f0 different from f1. This is the simplest version of an oracle problem. Now, you want to solve this problem classically. How many questions do I have to, how many times should I ask the oracle? If I want to know if f0 is equal to f1, well, I have to ask twice, f0 and f1. And then I know the answer. So it seems that, and there is a theorem, I know it sounds very simple, but there is a theorem that says that. Okay? There is a mathematical theorem that you cannot do with less. I know it's a triviality, but there is a theorem. So a classical oracle needs 2 questions to know whether the answer is the same or not. Can we do that with quantum logic? That's crazy, no? Okay. So this was done by 2 people in the early 90s. This is Dodge and Josa. I know it takes a little bit of effort, but this is I will recommend 2 things for you if you like quantum mechanics. One is to reproduce this little computation. The other, in the end, is another recommendation. So I know it's crazy, but look, you apply to Hadamards. This is done step by step, the first Hadamard, the second Hadamard. I ask the oracle. I get the feedback as I should be with using a second register. And then I rearrange that mathematically, and the output turns out that the result, the probability of finding 0 or 1, depends whether f of 0 is equal to f of 1 or not. It turns out I simply do one query to the oracle, but I'm sending in superposition the 0 and 1. And then I read out, and I know whether the function was equal or not. So you see, the huge thing is that I'm using the oracle on the superposition of possibilities. What a clever trick, okay? And now you learn something. And this is ultimately what is called the Grover's algorithm, one of the fundamental pieces of quantum computing algorithms. In general, if you want to find one element out of n elements with an oracle, if I want to search one element in a database of n elements, how many queries do I need? A square root of n. Classically, the theorem says that to have probability 1, you need n in the worst instance case. To have probability 1/2, you need 1/2 classical calls. Quantum mechanically, a square root of n. So if I needed 1 million questions to get a guy from a database, quantum mechanics, you need 1,000. Okay, a square root. So many of these companies that are now selling quantum computing algorithms, if you look in detail, hardcore, what are they doing? They are using the Grover's algorithm, okay? It's a heart. It is one of the primitives that we know. It's solid like a rock. Okay, there are many other things. Let me flash on them. You can add superposition of prime numbers. So why not using all these things to analyze the series of arithmetical progressions and things like that? Why not? Okay, or why not using a combination of circuits and artificial intelligence? And look at the beauty of the idea. So I make a random circuit, random, but I know it processes an exponential number of numbers. And I want a given output, the energy of a molecule. And I see it is not optimal. So I use a classical computer to do reinforcement learning on the gates that define the circuit. So I assist the quantum computer with a classical computer, or vice versa. I assist the classical computer with a quantum computer. I build a quantum processing unit, a QPU, which is called on demand by the classical computer. And these are the hybrid algorithms that have been applied to quantum chemistry. And this is why there is an interest in understanding how you can plug quantum computers in supercomputing centers. So the ultimate idea is that the quantum computer is a unit, like the GPU, like the whatever other unit you want to imagine. So you only call it for those problems that it is particularly good, because in average it is not good for many other problems. So the quantum computer only provides an advantage on the search, on the Fourier transform, on certain things. Quantum chemistry, okay? So this was done, by the way, by IBM, by the group of Aspuru Guzik, who is now in Toronto. And those were the first computations of molecules, very simple molecules, okay? You can do that in your head, okay? You don't need any computer. They are called hybrid classical quantum strategies. Or, and I will not enter in the algorithm, I will not try to do it, but there is a fundamental element where quantum is much better than classical, which is the Fourier transform. The quantum Fourier transform can be done exponentially faster than the classical Fourier transform. And there are so many problems that you can do with the Fourier transform that this is the hint that we have a really good machine. One of the problems where you solve with a Fourier transform is factoring. And here, you know, I give you 15, and I want you to give me 3 and 5. I want you to understand that 15 is 3 times 5. I want the factors of a number. Now, the best algorithm we have nowadays is the field sieve, and this is exponential of this prefactor, 64/9 1/3, and 1/3 log n. Quantum mechanically, we can do it with n cubed log n. Okay? So this is an exponential advantage. And the output delivers for you the two factors. So it's a classical problem run with quantum logic. Okay? Now, as 2 months ago, after 30 years, because Shores is 94, so 29 years later, suddenly a guy from Israel has gotten an advantage to this algorithm and has reduced if n is very large to n 3/2. If n is not very large to n 5/2. So amazingly enough, there was a space for an improvement in logic. Okay? Something we really thought, many of us, that it was done, that was the optimal. So this is a non-trivial fact. And you see now immediately why. Because it turns out that we do have an application of factoring which is amazing, which is all our communications need secrecy, and we use cybersecurity. Cybersecurity, starting in the 70s, we use algorithms for it. And it was the RSA algorithm that we use for cybersecurity. RSA is based on multiplication of prime numbers. So if you're a hacker and you have a machine that factors, you're a real good hacker. Okay? Now, you may say, no, but there are other algorithms. There is the discrete locks, there is the elliptic curves. All of them are based on a hidden subgroup. All of them are hacked by the quantum Fourier transform. So all the class of algorithms we are using nowadays are in jeopardy. They can be hacked if you have a good quantum computer. Now, what is the solution for that? I should say that this is the reason why quantum computing is a security issue, why there are exploitation bans, why nobody wants to share quantum computing, okay? Nobody. And the reason behind is that the cybersecurity of the countries is at stake. Your social networks, every time you connect to the bank, your bank accounts, everything is in jeopardy, okay? Every backup of a company, everything is done with cryptography. So what are the solutions? Well, I told you in the beginning, if we control qubits, we not only have quantum computing, but we have quantum communications and we can quantum sensing. So what we can do is use quantum communication to take out the cybersecurity issue away. So quantum mechanics is bringing a new level where we bring the enemy, the instrument that kills the cybersecurity, and a solution, which is the new quantum cybersecurity. And it comes in two ways. One is quantum key distribution, and this is the ultimate security. You use qubits. So if somebody reads, they modify them. The other is a really controversial thing. It's post-quantum cryptography. It means a cryptography that is safe against the attack of a hacker who is endowed with a quantum computer. Okay? So can you prove that there is a classical algorithm that will be safe against any attack of a quantum computer? How do you do that? It's a proof of non-existence. This is very difficult. Well, what happened in the PQC world is that the National Security Agency in the States asked the National Institute for Standards and Technology, the NIST, to have a competition to find a new classical set of algorithms that would guarantee the communications in the presence of a quantum computer. So that started in 2017. A number of candidates have been selected. There are recommendations for different protocols, different algorithms, and they are now being scrutinized and ported to reality in certain cases. Two of them, the year they were selected, were cracked, classically. So you see how difficult it is to build a problem of this kind. Okay, it's very, very subtle. So a lot of money is there. There are new companies, very powerful companies, which are, Google has a company called Sandbox IQ, which is only for that. And every country has now institutions devoted to that. You know, in every I can tell you in every country who is doing these things. So let me finally turn to the real quantum computers. They are here, they exist, they are not unique. On the left, I'm giving you the picture of a proposal from a Finnish company. This is IQM. It's very beautiful, but don't get impressed. This is a fridge, because this is superconducting currents, and they go down to 10 millikelvin. You need what is called a dilution fridge, and they have made this thing. On the right, Curia, this is the neutral atom guy, Michel Lukin, who has done that at Harvard, but he has a company, and they are doing the control of neutral atoms in space. On the bottom left, you have Xanadu. This is one of the companies in Canada that they are doing photonics. They are really taking seriously we should compute photons, but they don't have universal gates. Okay? They don't have. This is what is called a bosonic sampler. It's a linear transformation of the original state. And finally, a chip company, and I'm giving you the one which is called Quantinium, with a 1.2 billion money on their pockets, coming from Honeywell. Okay? They have reached 32 controllable qubits. Okay? The quality of them is like having decent 14, 15. You can do operations really with 14, 15. Now, there are more than 100 startups. So the search for talent is amazing. So you have cold gases, Harvard, Quera, Pascal, Planck. In ions, you have IonQ, Quantinium, Alpine Quantum Computing in Austria. For photons, you have PsiQuantum trying to make a universal computer. There will be an announcement. They are making an announcement that something will be deployed in some country with some enormous amount of money. You have Xanadu, you have Orca, Quandela, Quix, solid state. Why not going to solid state to electrons in silicon? This is Dirac, Intel is putting money. Superconducting, you have Google, you have IBM, you have IQM, D-Wave, you have Oxford Instruments, you have SpinQ in China, Atlantic in Boston, you have Conscience in Sweden, you have Kilimanjaro in Barcelona. And let me jump the components. Let me say, what are the fields that people are doing? Well, there is a universal consensus. The money will be in the algorithms. Just like in classical computing, the big money has been in algorithms, not in hardware, okay? Who are the guys? Okay, Google is powerful, Amazon is powerful. All these people manipulating algorithms have scaled tremendously. So what people think is that the business is in algorithms, and in finance, you have teams that work in finance, substituting Monte Carlo with quantum circuits for risk management, option pricing. In chemistry and bio, you have drug discovery. We're doing that ourselves in CQT. We have gene regulatory networks, draft problems. In optimization, it's huge. We have any quadratic problem, we have technology for that. We can do value chain, we have to logistics. A new thing is hydrodynamics. We can handle hydrodynamics. Artificial intelligence is a big thing, quantum machine learning. And cybersecurity, as you can imagine, plenty of people. Now, there are exploitation bans, which is a huge thing, okay? You may know that now there are severe exploitation bans, for instance, in the fridges or in the FPGAs. And and now I'm go to the 1% of people that really want to do something out of you, I recommend, my second recommendation is that you embrace open source initiative to code in quantum. It is called Kibo. Kibo.science, you will see it's more than, I don't know, but people in 7 countries, and it's a starting, but it's really impressive. And if you want to learn more, qtalent.org is the platform we have been developing to give real courses in quantum, not hype, not trivial, real to learn is qtalent.org. So you will be impressed if you go there to see a language, the libraries, how it controls the machines. The language has to talk in terms of pulses to the qubits, so you have to do everything. It's a full stack. I thought a final thing would be just to entice you with a non-trivial thing. Let me show you that the hyperspace is huge. It's a divertimento finale, okay? And I want to analyze whether I can map a picture into a cat, into qubits, okay? Is that a possibility? Well, this is a possible encoding. I simply take the picture in quadrants, and if I'm in this quadrant, my first quadrit is 1, 2, 3, 4. If I'm in the second, and I'm here, I2 is 2. So telescopically, I address, and I use the labeling of the state, and the level of grace is the coefficient. So you see that a picture can be written in terms of log 4 of the capital N qubits. So it's an exponential compression, okay? It's really an exponential. And then you can even consider that those things, these coefficients, I approximate them, for instance, with a product of tensors. This is the idea of tensor networks. So I'm using quantum mechanics to finally write a picture as products of tensors. And this is what we all call quantum inspire. There was not such a thing before. But because of thinking in this quantum mechanical way, I have a new way of handling the pictures. And just if you are curious, with tensor networks, you can improve how you compress, you can really do the traditional things in an absolutely novel way. And this is the technique which is now being used to deal with fluids, hydrodynamics, okay? Quantum inspired. Be aware of that word, quantum inspired. I follow the logic. I don't have quantum computers, so I do it in a classical computer. I need a very powerful classical computer. I need a supercomputer, but I have advantage over classical algorithms. Okay? So this is what I said. Well, and my last transparency is about a criticism. Many people, it's in the air whether so much money went into that. And now we have artificial intelligence, and we have large language models. So whether the funding will go away from quantum or not, to say that yes, it will go away, well, the usual thing, hype, too much hype. The second argument is that quantum computing is great, but it's not for tomorrow. I want to make money, so I don't want to invest in that. Third is that artificial intelligence is more exciting. And why not? It is very difficult. So not easy to attract talent. If you want to make a startup, you have to pay salaries which are astronomical, okay? On the other hand, the opposite can be defended. The pace of scientific progress is unstoppable. I just told you the results in Harvard, but I can tell you about a zillion things going in the planet. Why? Because humans, if you can go to the moon, you go to the moon. If you can clone Dolly, you clone Dolly. If you can do artificial intelligence, you do it. Because it is there, because you climb mountains, because there is no reason why you want to do it. It is possible. I am the guy who does it. So nobody will stop very good brains to go into this domain. Second is that talent is not easy, but still we get very good students, very good. Because they are tantalized by this beautiful idea that you are at the edge of knowledge, because you are making the future. So I hope I'm tantalizing you. And this is a race, so better to be in the race than watching it from the side. You want to be there. And finally, and this is a non-trivial fact, but it's a reality, because of the tensions, the political tensions, having sovereign science is becoming more and more relevant. Sadly, I foresee a 21st century that will be segmented. The science will get segmented. Okay. So thank you very much. And I don't know if you have questions.
Thank you, Professor Latore. That's an interesting topics about quantum computing. Yes, I will give a floor for some questions. If anyone, okay, please.
Thank you, Professor Jose, for the presentation. My name is Arman from BRIN. I want to ask you how to decompose the problem to the quantum logic gate. Because as I know that if we have to calculate or to make quantum computing, we only have to use like unitary gate. So for example, we have Hamiltonian, and then how to decompose to the, yeah.
Hello. Ooh. Well, this is the problem. I mean, why do you think it's expensive? If it were programming in Python, it would not be that difficult. Why do you think salaries are good? Because you are confronted with a problem and you have to see it on the blackboard and man, find a way. Now, there are companies that are trying to sell this service. Okay? There are companies that say, we are the compilers. You want to compile your problem into logic, which is quantum? We are there. Okay? And there are a number of companies that sell their services for that. Okay? And this is a new industry that I didn't see it coming, but it is there. Really selling themselves as compilers. Yeah. Early stages. In the future, you will have libraries and nobody will have to think a lot. Okay? You will simply find a minimizer and you apply it. As of today, no such a thing exists.
One more question?
Sure.
Yeah. So,
you see, I convinced one guy, yeah?
Yeah. In the case of cryptography, you know, in the classical cryptography, we have number and we have to factorize the number. So it's easy for the quantum computer to solve this kind of cryptography. And what kind of problem then used for the post cryptography? Yeah. Okay,
they are all problems which have an element of a root, which is NP completeness. Okay? We believe quantum computers cannot solve NP complete problem. You know NP complete? No? Okay. Okay. Let me then try to you know Turing, Turing machine. So Turing established that any problem can be related to how long a machine would take to solve it. Okay? And at that time, he was obsessed, and many people were obsessed with problems that the machine would never find a solution, would stay forever. And this is the origin of undecidable problems and Gödel's contribution in the 40s. Now, for the same token, in the 70s, it was realized that some problems are easy. There are known algorithms that solve the problem in a polynomial time, and others that need help, need a hint. And those solve the problem in polynomial time with a hint. Okay? The hint can be even the solution in some cases. So this is polynomial problems and the non-polynomial deterministic problems is the name. Okay? These problems, if you don't have the hint, you need typically an exponential time. What are the problems in this category? All the combinatorial problems which are hard, okay, which are very difficult, they are on this category. So we believe that classical computers have an exponential hard time to solve NP problems. So is factorization NP or P? Believe it or not, as of today, we don't know. There is no theorem that classifies factorization, okay? Actually, it carries a name by itself and PI category. Now, if it were P, and somebody finds, you at home find an algorithm that in P, in polynomial time, you solve factorization, you kill the industry. But after 50 years, it's hard to believe that we have missed it. Then you say, well, computers, quantum computers can solve problems. Can they go to and solve all the NP-complete problems? We believe not. We believe that the category QP is now called QMA. It is not attacked by quantum computers. It turns out that factorization was never classified as NP. So that's why factorization is solved. This is a hint that factorization is yet another category of problem, which is intermediate between P and NP. Okay? Now, if factorization, discrete logs, elliptic curves, all of them are attacked by a quantum computer, that means that they have a common thing, all of them. And the common thing is that they are easy in one way, multiplication is very easy. They are very difficult in the opposite way. Okay? This is the idea. Now, NP-complete problems are really different. Okay? In some cases, generating an instance of an NP-complete problem is hard itself. The generation of instance is a hard NP problem. So what people are trying to do is a very clever thing. They are looking at the place that we think that the quantum computers will never get, which is NP, and from there, generate new ways of doing cryptography. And this is one of the examples, it's called learn with errors. This is one of the candidates. You will see that these are so-called lattice problems, and you have to find the closest, shortest vector to a given point in the lattice. Now, this would be NP if the conditions on the lattice were not as stringent. But people are putting conditions so that encoding takes not the eternity. So the fact that you have to encode in a fast way in your phone and hard for the hacker brings constraints that are making the problems not in the category NP. What a mess. So we are trying to do what is intelligent, but there are no theorems that certify that we are doing something that makes sense. Okay? And 2 of the candidates approved were hacked in the first year as a proof that this is a highly non-obvious issue. I would not like to be in the position of the NSA in America, in the National Security Agency. I would never want to be in the decision committee of what to do for all the cybersecurity of a country. That's very heavy. Okay? Okay?
Thank you.
Have I convinced anybody? Anybody wants to work in security? No?
More question?
Oh, one.
One more question. Sorry.
Okay, morning, Prof. Thank you for your very interesting presentation. Okay, I'm Razif from Malaysia, basically. Okay, I just got one question regarding on the photonic chip from the Xanadu, for example. The qubit for that kind of chip is the photon itself, right? So, do the photon generated inside the chip or they produce outside from the chip?
So this chip has 3 pieces. A piece where you generate the photon, a piece where you make them go from different paths, and a piece where you measure the photon. So always you do the generation, the manipulation, and the readout.
And how do they generate that kind of
So
photon?
this is...
Because you need a single photon.
You need
source,
a
right?
single photon, which is not deterministic as of today. So they do it with a process which is very probable, and they do what is called multiplexing. So you put 16 of these guys, hopefully that one comes out. And that's what you do. And as a matter of fact, with a high probability, this is so. They can go to 0.99939 is done, probability. More difficult is measuring, because single photon detection is 1 photon, man. I mean, we are saying these things as if it were a triviality. Imagine 1 photon, okay, 1 guy, with very little amount of energy. How you detect that? Well, we use nanowires. We use another quantum system to measure the 1 photon. And this is now being implemented inside of chips. So it's top technology in the planet. Top. You cannot believe. So, these chips here, they carry electrons and you print them very easily and you inject that photons and they stay there and they are measured. Wow, that's scary. Okay. Yeah.
Do security also venture in photonics-based quantum computing right now?
Us, security? Yeah. To be precise, we are good at photon detection. We do have some generation. We don't have a team that is trying to put all the three pieces together because we believe it's so difficult. And we are fighting, security has 230 scientists. We have 25 principal investigators. But we are fighting against Xanadu with 700 million and, in the West Coast and so on. So you have to measure your bets in science. We stay in the basic science. We think it's premature. They have money, they try. We keep it more humble. But in the long term, let's see who wins. Okay, let's see. These people in the States believe they are so clever, okay, that nobody else is clever in the planet. Wrong. Wrong. Talent is born anywhere. It's yeah.
Okay, thank you. And is there one more last question? If not, one more. Okay. Let's take up.
You're a good man.
So we can go for the break after that.
You mentioned about the variational eigen solver, right? You mentioned about the variational eigen solver. What do you think the prospect of that solver compared to, for example, the fault tolerant, like quantum phase estimation?
Yeah.
Thanks.
Yeah, be careful. Fault tolerant is simply trying to do all these things without errors. So fault tolerant is additional technology to make better the computers, but it does not change the logic. Okay, the difference is that with fault tolerance, you will do logical gates perfect or more perfect. Okay, but which logical gate remains in your algorithm? Okay, to decide. So this idea of variational quantum eigensolvers started, as I wrote it there, in the last decade. It went through a huge attention in the last 2 years. In the last half of a year, many people, including myself, believe that there is a limitation to this. That the training, this reinforcement training will take as much effort as having it in a classical computer. So that we think that we are moving a problem to one place to the other. Yes, we have a quantum computer, we have a huge space, but to handle an exponential space with a polynomial number of gates, it's a problem in itself that by reinforcement will be very difficult. To give you an example, the best solutions with eigensolvers are obtained when the parameters of the eigensolver are treated with genetic algorithms. So really a search using a little bit of a blind search. Any gradient method, as you do in neural networks, is not working at all, okay? Because the gradients are exponentially small. The Barron plateaus, if you are familiar with these. So it is, the field is in a moment where we are all looking for some clever way out of the Barron plateaus and the optimization of the variation quantum eigensolvers. So we believe there is something there, but the first thing that we're trying, honestly, now we believe are not that good. Okay, we have to work much harder. And not the place to show you, but there are new ideas in the last 3 months which are really beautiful. Never stops, man, never stops. Well, guys, thank you very much, and remember that you have a duty, huh? You have to improve your countries and bring science to your countries. Ciao.
Thank you, Professor Atole. And by the way, as the first questioner he's from the Quantum Physics Research Center of BRIN, so probably he and you can collaborate later. Okay, thank you very much. And for the announcement, there will be a coffee break outside. hopefully you can get all the coffee break. And we will come back on 10 minutes, so it means 10:45. And we hope that Dr. Leslie Lamport is already online, or otherwise we need to adopt again. Thank you very much. See you. participants, please come back to the auditorium. Udah. Oke, bisa begini.
Oke, bagus.
Probably you can give it to him, or
Huh?
you can give it to him, or someone. Oh, Rifki will be here and he will hand it over to you. Di setup dulu Pak. Bisa pakai Zoom aja. Nah, pakai Zoom aja kayak tadi. Okay, already here. Okay, thank you. Welcome back to the classroom. And I'm sorry I forgot to have some other ceremonial for the professoratory. We would like to give you a token of appreciation, and it will be given by Director of the ASEAN HPC School, Rifki Sadikin. Please. Camera, please. Okay, thank you, Professor Latori, and hopefully, we hope that you can find some collaboration with those students here. And for the next session, we have to reschedule our interview with ACM Turing laureate to another day because currently it's already too late for him in the US, so we will not disturb him and take his time for resting. So we continue to introduction to parallel programming will be delivered by Professor Heru Suhartanto, sorry. And he is the professor of computer science in University of Indonesia, and he has been in the field for long his career. So please welcome him, and we wait for him to connect. Can you share? Slideshow. Okay, it's all set. So Professor Heru, the floor is yours.
Okay, good morning everyone. Assalamualaikum warahmatullahi wabarakatuh. It's nice to be here, and this morning we just had a good presentation about quantum computing, which is the future of computing, and then we hope that with the assistance of quantum computing, our jobs and our research will be much better. But in today's presentation, I was given by the committee to deliver a very basic material, which is about parallel programming and MPI, or also an OpenMP. Just to let you know that the last time I did the coding with MPI and OpenMP is in 2000, in the year of 2000, when I was finished as being a postdoctoral fellow at the University of Queensland. And the first time I engaged in parallel computing is about in January or February 1995, when I began my PhD student at the University of Queensland. My supervisor at that time was Professor Kevin Barrett. Maybe some of you know about him. The beginning of our discussion at that time is that he said to me that some people works on parallel multi-step parallel Rungakuta method. can we expand the method with multi-step Rungakuta method? 3 keywords. That becomes my PhD research. And then after that, we try to build the numerical method for solving very large ordinary differential equation. For some of you may know that ordinary differential equation can be derived from partial differential equation after some of the reduction of some assumption, some of differential, so that we can have a very large differential equation. So since that, I play with Fortran programming language, and MPI and OpenMP, and I worked with in the machine with silicon graphics. I think silicon graphics at that time. And then we developed the method, and then we developed the numerical method. We tested the method in the machine at that time. At that time, we still get inside the machine by login directly to the machine. If we compare with how we interact with Fugaku right now, at that time was nothing was done. Currently, when we interact with Fugaku, it's very convenient, very convenient. At that time, it's very difficult. There is no web browser at that time in 1995, before 2000. So I would like to just a little bit give you some review. For those who has some experience in programming, this one is very basic, yeah. But just to review again, I was given and suggested by the committee, try to give the idea how to solve the problem in parallel. I think some of you may have seen this example before. At some time ago, a group of people try to protect their group from the attack from the other groups. And the idea is just to try to develop yeah, a very long and hedge walls. Yeah. And then the question is that, and the requirement is that they would like to have the wall established as fast as possible. So we try to look at what kind of jobs and what kind of work that can be done when we try to construct the wall. So that means we can making the bricks. We can also provide delivering and how to deliver the bricks to the people, and then how the people try to lay the bricks so that we will have the wall. So you can see that the main object is to creating the wall. And then we try to find some way or some techniques or some algorithm if you are talking about computer science. What will be the best way and what will be the fastest of building the wall? So this one, we just try to look at the first algorithm or the first method. So we try from the first people, they lay the bricks at the first level. Once they build the first layer, and the second people put down also the next bricks on the second level, and so on until the topmost level. So at least from this one, we can see that several people can work together. So that means if we compare with one only people, this technique is much better. So that means much better. But the question is that, is this the only way or not? Okay. Can we find another way or not? Okay. But the main objective is try to build the wall, not anything, just the wall. Okay. We can figure out some other things. Maybe we try to look at the next one. This is another way. Okay. But you can see that the people itself, the layer of the brick, should be on the position. And that's when they have the brick, they lay the bricks one by one from the first level until the top level. But you can see that in between of the people or the processor of this, like this one or that one, they should coordinate. Yeah, they should coordinate. So that's been only on a critical part. Only one people on one brick layer can put the bricks on the spot. and then two of them cannot put at one spot two different, more or two bricks. Yeah? So that means only bricks at the intersection of the wall. So that means in this critical, so that means there should be synchronization, cooperation among the people. If you are talking about the processor, maybe the process should be communicate with each other and synchronization. Okay, does this solve the problem or not? Okay. We do not know how the bricks is supplied to these people. Okay. One way is to give you the bricks to the group of you like this one, which is a sequential input-output, yeah, sequential input to the people. And then that means if we follow this one, this might be very slow, yeah, very slow. So maybe you have another method, another way. We can provide the data like this one. Sorry, I have a problem with my throat. So we have something like this one. So that means we deliver the data or the inputs in parallel way. Okay, several tasks to be sent to each of the people, and then once they got the data or the brick, they can lay the bricks, and then they will build the wall to its part. Okay, even though on each critical section they should coordinate each other. This is how the problem to build the wall, but we try to find the best way. Where the objective is to find, to establish the wall, but in the constraint is that it should be done as fast as possible. So we have to figure out the way how we deliver the bricks, the way we lay the brick, and how many people involved in this coordination. I think that's try to explain how to solve the problem in a very fast manner, and then how we can put it in programming language. So this MPI and also MPI, you can find the material easy way in many internet sites. You can find it, and also some video also available in YouTube. You can see that's basically MPI, or a message passing interface, is a parallel programming model. Yeah? And then some say that this is a standard for message passing communication. So the processor itself, when they communicate with each other, they're sending the message. Yeah? They are sending the message. Or you can say that they are sending the data, yeah, to their partner, yeah, to their processor. So that means there is a communication between one processor with the other. And some of you might ask, how we can communicate with the other processor? Can we communicate one by one, or can we communicate in a group at once? Okay. I think that's the one of the topic that we have to review again. So basically, in MPI, you can see these processors are independent. It is the independent executing unit. And then we can also that this is the thread in parallel programming. And then each process, and then you can see it will have its own space. So they will have its own data over there. They can communicate between process by sending the data and the message to the other one. You can see that if we are the programmer, we are the one who should explicitly try to divide the data and try to arrange which data to be sent to what processor, to what the processor. Because this one is a little bit tricky. It is not easy for beginner. It's not easy for beginner. So the programmer should be responsible to transform the data and make sure that the data is retrieved by the other at the same amount of data. And then there is two types of two kind of communication. The one, as I said before, there is a one-to-one communication. So that means one processor can send the data or the message to the other one. So by using the MPI send, okay. And then the other one, they could retrieve the data by using the MPI receive. And then the message itself can be the data of any type. it can be a basic type, or it can be a structure type. You can also define various type of data, and then you can send it to the other processor to be processed in the next processor. In the collective communication, one processor, they can send the data directly at the same time to the other one. So we have two times, we have many several way. The first one is the MPI broadcast. That means include broadcasting the data into all processors from one to the other processor. And then they try to gather the data from the other. Okay? So we use the MPI gather over there. And then we try also to reduce the data from all processors. We use the MPI reduce. There will be some example about this one. And then if I see about the synchronization, you can see that, as I said before, particularly on critical area where only one processor to be in that area, and then put the data into there. For example, when we are talking about building the wall on critical part, only one layer can put it the bricks on there. So also in here we order the processor to wait until all the processor reach at a certain point. We can use something like MPI barrier to try to coordinate the quotient of processor. And also we have data distribution, that is how to facilitate parallel computation. Data can be partitioned or distributed among processor, and each process operates on its local data. Remember that each of the processor will have its own memory. So this is, you can also some derived data. Okay, maybe I will try to go back again. When I just finished my study at Australia in 2000, I went back to University of Indonesia. I teach the parallel programming, but at that time we do not have supercomputer, not even multi-cores. Okay, so we developed a cluster system, ya kan? We developed a cluster system from Pentium 2, Pentium 3 over there, and then it's difficult for us in Indonesia to have a multi-processor or multi-cores machine. Before about 5 years ago, the way we developed the competence of parallel programming and also research in parallel programming is that try to buy the spare part from our own research budget. Okay, even if we try to propose to the university or to the Indonesian government, let's buy a supercomputer, nobody care about that one. Okay. And then the thing that make us a little bit sad is that when we got the funding from Hibah or maybe from the government or the other, we are not allowed to buy computer. Maybe some of you don't know, yeah? If you got the funding, basically from the government side, we are not allowed to buy computers. Okay, fine. I will not buy computer. I did not bought the computer, but I did buy spare parts. Okay, I did buy spare part. I bought some processor. We bought some motherboards. Okay, and we bought some memory. Okay, I buy 4 processor or 4 motherboard. I will ask to our customer there, okay, I buy this kind of spare part, plus help me to build it as a computer. So I have about 4 or 5 of them, and then make it into a cluster. So that is how we, a little bit tricky to build the competence of parallel programming by a very constrained condition, which is not good for us as scientists. But alhamdulillah, ya kan, luckily about 4 years ago, Tokopedia is willing to put their machine, NVIDIA DGX 100 at the University of Indonesia. And then about 2 years ago, the government tried to look at, okay, since many people talk about artificial intelligence, that means artificial intelligence will not work properly if we only process the artificial intelligence problem in ordinary computer. So that means you have to have a specific computer. At that time, the government realized that they need a good computer, even though it's still far away from Fugaku, but at least we have at least about 8 or 10 universities, they get the grant from the government to buy NVIDIA DGX A100. So that is currently about 10 or 8 universities in Indonesia have that kind of machine, okay, which is good, that is good, but still not enough we compare with Fugaku. Okay, next time the portability MPI also can be, if you write the MPI code, that means you can run it on multi-core. You can also still run it on cluster. You can even run it on Fugaku. So that means fun. That means it's portable. It's portable. So that means also you can run it on any number of processor, on a number of nodes over there. Sometimes also it has some error handling, to checking there is some written code to be observed by the programmer in order to make the codes run properly. And the next one, this is the example of the MPI code. You can see that on the top over there, okay, over here, you should put MPI edge over here so that it try to communicate with the MPI library. And then you can see over here on the second level, there is MPI init. That means you have to initialization, do some initialization. So that means you are try to initialize the MPI function in our code, and then try to define the word of the processor over here with MPI com rank. So you can see rank is the ID of the processor, or the ID of threads, the ID of thread. And then you can see, okay, we try to get the number of processors. That in, we do not know how many threads and how many processors are available in our computing environment. But you can get it by this kind of comment. You get the numprox, that means you have, okay, we know that we have this number of processors. And then you can predict, and then you can see that if you try to compile this one to run it, in Fugaku maybe tonight, you can see that you can have hello world printed with a various number of ID of the threads. Okay, if you are only allowed to use about 8 threads, maybe about thread number 0 and 7 will appear in this on the screen. Okay, this is the introduction of the very easy MPI codes. Okay. And the next one, there is a global communication. As I said before, we can have like MPI com word. It represents the global communication scope of an MPI program. So that means the people, the threads or the processor, they are in one word, that they will communicate with each other. If you do not put this one, your MPI code will not work. Okay. There is no communication between the processor. So that means, if you look at the first, this one is necessary, include MPI, inits, com red, over this, and this one. In MPI com size, you can see that you will need to look at, you can figure out how many processor, how many threads are available in the system. So that you can, once you know the number of processors available in the system, that means you can allow what kind of data to be sent to the other processor. And then how they will compute some part of the code. Okay, the next one, there is MPI words and like to one. So that means, look at, this is the initial setup. You can see that this is the MPI com word is the initial communication setup. And then also, there is a MPI send and receive. Without this one, without doing the MPI com word, we cannot do the MPI send and MPI receive. Okay. And then there is also a broadcast. You can see there's a broadcast over there. So basically, this is a global synchronization. Yeah? So you can see there is a barrier, if MPI barrier, so that if you want to all the processor to be do not cross this line before the other reach the line, you should put MPI barrier at the certain line. So that means you are doing synchronization. Yeah? You are doing synchronization. The same thing will also. You can do it the same thing but with different syntax for OpenMIP, for OpenMP. But at least for MPI BRIN, that means you have to tell the other processor that you should not go beyond this line. And then after that, you can go and do anything you want after that. And then you can broadcast, and also to broadcast to the other one by using only one command, MPI broadcast, and then you can also gather the information or data by using the MPI gather. There will be some easy example after this. Next one, this is sender as receive. This is one-to-one communication. So that means there is one processor and two. The other one is the one is the sender, and the one is the next one is will be the receiver. So that means it involves two threads or two processor. One is the sender, one is the receiver. So that means you are sending the data from one sender, and then the other one will receiving the same data. And make sure that the number of the data should be the same. Yeah? So there will be no error. Right? So this rule can be performed by different processor in MPI program. So that means you can put it in anywhere, yeah? Just to make sure that you know how, you know what to do about the code that you are developing. And this is the example. You can see that MPI send. So that means this is the command, and then you can see that this is the function used by the sender to transmit the message to the receiver. So the sender specify the following to them. They have the data to be sent, and the number of data that element to be sent, and the data types over there, and also the destination rank or the ID of the receiver, the ID of receiver. So the communication, this is the communicator, world. You can put MPI com as the communicator on the MPI send command. Yeah? And then every send there should be receive. Yeah? So every MPI send those should be related with one command of MPI receive. So that means in this one, the receiver should also look at the data that they will receive from the others one. And also the same number that had to be received from the sender, and also the same data type. And then he or she should know the source of the data. Okay, so know the set of data. And then they will also use the same communicator, which is MPI word. And then from the matching set, I try to look at there is some example. This is some condition. I'll try to look at some example. This is the example of one-to-one communication. Okay? Data sharing between two processors. So that means I put it over here. And then this is the including the MPI.h, and then we have the initialization, and then we define how many rank we have. Okay, so if rank equal to 0, that means this is the boss, okay, or the master, you can say that. Okay, process 0 send data to process 1. So that means the data we want to send is the data which is equal to 41 over 10. And it tried to send the data itself, which is the count of 42. And the number is 1 over here, and then the next one is the rank 1, which is the receiver, and this is the communicator. This is the communicator, and then the processor rank equal to 1, which is the receiver. You can see that it will receive the data over here, and then the length is 1 over there, and it is come from processor 1 over there. So that means you can print it, and then that's when you can check that. The data is sent will be the same as the data to be received by the other processor. So in this example, processor 0 send integer 42 to processor 1 over here, and using MPI send and MPI receive to retrieve the data. In the next one, you can see that this is sending and receiving arrays. If you look at the last one is sending just one data, but in the next time we try to send the data, which is the array of size 5 over here. So sending and receiving array over there. This is the initialization. You can see this is the rank over there, and then this is how they initialize the data over here. Process 0 send an array to process 1, but they initialize the data send over here, and then they send it over here, okay, by MPI send and data send, and then to other processor. This is from processor 0 to processor 1, and the processor 1 itself will receive the data They put the data receive over here, so that means whatever the sender send, they will put it, the received data, into this variable over here. You can see this, the length of data is equal to 5. Okay, the same thing, they will receive the data equal to 5 over here. Okay, and then it's come from processor number 0. Okay, and that's one they receive, they can put it over here, and then they can check that between this data received and the data sent should be the same. Okay? Should be data the same. If it is not the same, there should be something wrong. Okay, we cannot continue with our code. Okay, that means you have to check which part is not correct. Okay, and what caused the problem. And this is one, the resending and receiving structured data. Remember, we can also define structured data over here. We have two kind of data. This is integer, this is double value, double precision. So that means the data can be anything. It can be constant, it can be array, it can be a structure. Okay, it can be a combination of the other. Maybe you can also define any kind of complicated data over here. Whatever data that you define, maybe it should be suitable to the application or the problem that we try to solve. So that means the same thing over here. We initialize the data over here by rank equal to 0, and then we send it over here, and then also the rank number 1 will retrieve the data. You can see that the data is sent only one structure. You can see this is one over here related to the one structure. Yeah, even though the structure itself has two elements, element of ID and element of value. Yeah, so, but the data itself, it is only one structure. One structure. The type is structure. The type also in here is the structure. Okay. And the next one, we look at, this is the collected communication. As I said before, there is a broadcasting. So that from one processor can send several data at the same time to the other processor or the other threads. Okay. Okay, try to look at some example. This is the example. You can see this. It using the broadcast. The first one is you are trying the initialize to MPI, and then you can see this is rank 0 over there, and rank 0 define the data to be 42. On here, it broadcasts to the other processor. So that means the rest of the processor will get the data 42 from the processor 42 over here. So that means it broadcasts, okay? Data is broadcast, and the other one, you can see you can also, once you got the data, you can print over here what rank, and then the data should be the same, 42 over this. This is will print you the rank or the ID of the processor. It is nice to be, to be tested in our machine, or maybe at Fugaku, maybe tonight. Maybe tonight. The next one, try to let MPI getter, as I said before, from the other processor. Once you send the data to the other one, and then let them compute according what is defined for them. And when they get the result, we will like to get it from them, and then we process it in our side. So that's what the master would like to do. Okay, we are using the MPI getter. This is the example over here. Open here something like this one. This is the data sent over here, okay, and then the data gather data from all processor to the root rank 0. We try to gather from data, over here. So we try to gather from there. You can see that the data to be gathered, can here they get the data over here, and if rank is equal to 0, and then they try to print, root process retrieve data, and you can see that they got the data from each of the other ranks, of the other rank. Okay, the next one, we have MPI getter. So that means we are getting data from the other processor. The next one, we also have scatter from one and to the other one. Particularly when we try to do the metric multiplication, maybe one of the master try to broadcast some part of the data to the other processor, and then let them do the dot product. When the dot product is done, they will collect it as the definition of its metric multiplication. Remember, in metric multiplication, we multiply one metric A multiplied by metric B. The metric C itself basically is the result. If you try to look at the component of the metric multiplication, of the element I and G. Basically, this is the dot product from the row of I of metric A, and then dot product with the column J of the metric P. So that means each of the element of metric multiplication will be done by different processor. So that means you can send its related data derivative by the other processor by using the MPI scatter. But you can also send it one by one by send and receive command. Yeah. This is MPI scatter. You can see that we define it, the data over here, rank 0, define the data as you can see it is as array of 4 over here, define it like this one, and then they scatter it over here. That means they send it directly to the other processor over there. Data send, and there's one array that needs to be sent, and then if you can print over here, again the rank itself will print also the same array, this array. You can see that. This is the for scattering. For scattering, let me see how long do I have spent the data, the time. Still 11:30. Okay, next. 12. Okay, until 12. Okay, until 12. Until 12, so we'll have a good time for lunch. Okay. Okay, the next one. This is MPI reduce. Basically, you get from the others their processor. We try to collect it, and then the collection should be the result of computing something. Like if you have maybe example, if you have some array, we try to look at its sum. Its sum. We can also using the MPI reduce. Okay? And then the summation will be done in parallel with the other processor. This is the next example will be something like this one. Okay. We have the data set over here, and then in this example, multiple processor perform a reduction operation. Yeah. So that means we try to do the summation, penjumlahan. Yeah. Summation is penjumlahan on their data. So the data is data set rank 1 over here, and they try to reduce it. Reduce it. Okay, the data from the other, they put it as the sum data retrieve over here, which is you can see this is the way we define, we ask the other processor to do the reducing. We would like have to be the summation. Jadi yang kita terima that we obtain is the sum of the data from the others. Okay. Okay, the next one, derived data, as I said before, we have also derived data. We can also, from the basic data type, we can also develop another type of data, something like structure, something like that, which is the combination of other basic data like constant array or sometimes matrix inside the structure. You can also, this is why we should derive data. Sometimes it depends on our application or problem. Sometimes it's not enough to use array only, but sometimes we need a matrix, or sometimes maybe combination between matrix and with the other types of data. Particularly if you do developing the codes with C, maybe you need some pointer. This is, you can see this. Look at this is some example. This is the example of code factor addition. You can see this is we define the MPI S over here, and we define the factor size, which is 10, yeah, 1,000. So the each of the factors should be, its rank should be 1,000 over here, and then we allocate the data factor A, factor AB, and factor C over there, and then we define the portion of factor to work on. So that means we can let each of the processor to take part doing the job, but only its portion, only the portion of their data. So we try to connect it with their length over here. So then starting over here, okay? The size, the local size of each of the processor will have factor size divided by the number of processor. So that means if we have, maybe if we have 1,000, and then you have about 10 processor or 10 threads, so that means one thread will responsible for 100 element of data, okay? over here. So that when do the addition, that means if we have 10 processor, each of these 10 processor will do the addition of 100 of their part by themselves. So that means this part will be do it in parallel by 10 processor if you are using 10 processor to add element of 1000 array. Okay. You can also do it the reduce start over here. You can you can reduce the start over here. You can also look at by using MPI reduce over here. MPI reduce. Okay. You can see this is. I would like to have it sum over here. Okay. Something like this one. We can check. And then just sample. This is we can free it over there. And then this is another one exercise. I found a beautiful exercise from our source of information from Recon also. This is MPI pairwise communication. You can see that if rank equal to 0, and then you can send it. If rank is equal to 1, you can also send it over here. Just to check, this is the basic exercise. Okay, the basic exercise. Remember, then for computer science class, there will be about 20 students. Okay, maybe tonight you will have some homework. Not homework. Your room work. Your work tonight. Okay, your room work. Okay, there is some exercise. Okay. This is the code over here, but I'm sorry, the code is I put it in just a copy paste from the resources. It is image file, so that means you have to type it by one. This is if you rank number 1, that you are sending. If you rank 0, you are sending. If you are rank 1, that means you are receiving it, and try to print it. What is received from the other processor. So next will be this exercise. Okay. Write a compile, run the code in previous page with 2 processor. Okay, that means you have to do it here, try to code it over there, and then you use it by 2 processor, and then modify the code in the first page so that to perform the volume communication. Rank 0 send an integer to rank 1. Okay, and rank 2 send integer to rank number 3 over there, and rank n send integer to rank n plus 1, and then run the program with 10, 11, and 24 processor. What will you receive on the screen? What you receive on the screen? Okay. Okay. There will be some problem, but you do not have to do it all of them. Okay. But we can negotiate. Okay. Who's doing what? This is another one, another exercise, collective communication. Okay. Okay. Write, compile, run, and the code, which is over here, and replace MPI reduce. You can see that this is MPI reduce over here with MPI or reduce, and compare the result. Okay, just compare the result. What will you receive from this one? And maybe you can you have some conclusion from this one. Okay, MPI reduce and MPI or reduce, and compare the result. You can also try by using several different number of processor. Maybe try from 4, 8, or 16, or maybe 32. If you are allowed to use 32. Last night I only use about 16. 16. Okay. This is another exercise. We have three problems. Prepare an integer array of 3 size. Okay, array of size 3. Substitute your favorite number to array rank 0. And set the favorite number to all process. Okay, by using MPI send and receive, using MPI broadcast, and using MPI or reduce, and run the program with all 20 processor. I do not know whether we are allowed to use 28. Okay, can we do it in 28 or not? Andrea, do you know how can we do it with 48? Okay, we can do it until 48. Okay. And check the number can be set to separately. So this is 1. We have the another. Okay, for MPI we have 1, 2, 3, 4. 4 problem of MPI. Okay, just wait. Okay, this is for MPI. Next, we're going to the. But is there any question before I move to the Open MP? Mas Andre, maybe you can share the name of the student of computer science so that we can divide the exercise. And to next, you have to try it. Maybe you have to record it either by using Zoom, other thing, and then try to record everything appear on your screen, okay, by doing the exercise. Maybe about 2 or 3 minutes, okay, to find the result, okay. And then tomorrow you have show it to us during the parallel computer science hands-on experience. Maybe since if we have about 20 students, each will have about 2 or 3 minutes. Maybe we will have about 10 minutes for discussion. But at the beginning there will be some presentation. But I will give you the site for submitting your name and your links of your recorded movie, okay? And then tomorrow we will play the recorded of your works, okay? Any question before I move to the OpenMP? Okay, Mas Andrea, can you note that we have problem 1 of, I can note it, this is the problem 1 for MPI, yeah? This is MPI 1, MPI 2, MPI 3, and MPI 4. Okay. Okay, if there's no question, I will move to the OpenMP, yeah? You can basically you can see that in MPI we should explicitly send the data to the other processor and then let them to do their work, right? And then we ask them to ask them to send us the result, and then we try to collect also the result of their computation. But in OpenMP it's slightly different. In OpenMP it will works on a shared memory. Okay, just a second. You have your, I believe you bring your own laptop, right? Andrea said that we can use until 48 processor. In Fugaku. We should use Fugaku, not your own. Use Fugaku, okay?
Not ready. So you.
There's some example of in Fugaku. Let me see. Let me share my.
There are some sample code in Fugaku, especially in the thing I've shared.
You can see that if I put my open comment over here, okay. Just let me see. I open over here. Let me see. Oh, the connection not good. Okay. Okay. I'll look at the share data over here. Okay. The share folder, share directory. Folder. And then try to look at the CPU parallel over there, over here. This is the slide, our slide. And this is some source code that you would like to exercise before you do the homework if you want. This is. Okay. Can see
there
that?
are some sample of job submission. Probably Georgie already gives like yesterday. And you can submit those. BGSH. So
I'll give you this is the way we do the just second. This is how we just second. This is should be. Is the last one or not? Okay.
It's already the last one.
Okay. I will in our last slide. Okay, I will stop my slide over there. In the last slide there will be some example how we submit the job over here. Maybe I will try to close this one first, and then try to look at just second. I mean, what's the other?
Sorry. For those are only for those exercises are only for those who take the computer
only
science.
For computer science student,
so
not all the other.
For
only computer science.
Life science and earth science track.
Only for
don't worry,
computer science.
you will get another exercise from your parallel lecture, but not from Prof. Heru yet.
Yes, it's only for computer science, not the other. Okay. I know it's a little bit tricky. Okay.
You imagine. Okay. Okay. You want to give a demo, so probably you can go to OpenMP, and after that I will give you a demo.
Okay. Okay. I'll give you the OpenMP first for a short time because you can see how different is that by using MPI on MPMP. Okay.
Okay.
You can see.
Prof. Heru will continue with OpenMP, and because this thread parallelization, and after that we'll give you some demo how to compile and how to run it.
Okay.
On
the slide, on last slide, I will also put the file for job submission. Okay.
Don't worry.
I tried it last night. It works. I like to try it myself. Okay. Okay. This is OpenMP. Basically, this allow to develop. I mean, this one is for a shared memory environment. Okay. If you are talking about MPI, it can run on shared memory and also it can run on cluster, yeah, or multi-cores. Okay? But OpenMP it is suitable for shared memory architecture. Shared memory. So that means you do not need to send the data to the other processor because they know they can access the same data on the memory. Okay. So that means you don't have to send it over here. And it is easy. Okay. There is some comparing directors. Okay. Something like a parallel region. Okay. This is how I try to put it over here. I just go to the example, right? Like this one. This is the example. Like this one. So I do not need to send any data. I just define over there and then ask them to do this part in parallel. Okay. Just do this part in parallel. So that means in here we define thread ID. That means each of the processor which has its own ID by using get thread number. So that means this thread ID will contains the ID of each processor. Okay. If you print over there, if you are running with 8 processor, okay, maybe they will print you the ID from 0 to 7. Okay, that's different if we compare with MPI. Yeah? So in here, you do not need to send any data, okay, to their processor. And the next one, so that means something like this one. If you have 2 core, they will print two times with their ID. Okay. So maybe if you have 24 thread, they will print about 24 hello world with their own ID. Okay. And the next one also is here. That means you can see that we try to add 2 factor. Okay. Remember, if you do an MPI, we have to send it its part of data to the other processor. In here, we do not need to do that. Okay. Once we initialize the 2 factor, we can do it in over here. Okay. I will ask them to do it in parallel by using this one. Well, we have the parallel region of pragma or M parallel for. So that means in for loop, this should be done in parallel. Okay. So the ID, the I will be private to its processor. Okay. And all of them, they can access the part of the vector A and vector B. Okay. Vector A and B. And you can print it. You can have the result of the addition of 2 vector. So that means you can see that you do not need to send any data, yeah, to the other processor. This is the example, but there is a parallelization. There's only private and shared. You can see there is a private and shared. That means if we in here, so if I put the parallel private, so that means in this parallel path, I can define the SID as a private data. So that means each processor or each set will have its own data. So when they define as get thread number, they will assign to its ID, yeah? Even though they have the same variable name, but they have the same name appear in their own memory space. Okay? So if you print it like this one, it gives you, it will print you the its related processor ID. Okay. Okay, this is a private and shared data over that, and you can see that. Remember that this is another example. So you can define this one as thread ID as the private over here. Okay. So in here you can see that you ask the other processor wait until here. Okay. Do not go further from this line. So that means maybe some of the processor, they just print hello world and they would like to go to the next line. But if you put pragma or OM barrier, so that means you ask them to wait to this line. After that, you can go it together in the next line. So we call this one is synchronization, how we can synchronize. If we do it in MPI, we put MPI barrier, ya kan? But in OpenMP, we just put pragma OM barrier over there. And then this is the how to do dulu in parallel. We do it over here. You can see like this one. We define the data over there, ya kan? And we we ask them to do it in parallel over here, ya? Like this one. Just put this one, ya, pragma OM 4. So it gives you. You will ask some of the processor that you define to process it in parallel. The next one, adding to element. Also, let me see, add element and array of parallel. Again, the same thing. I think it should be almost the same. But you can see that we define local sum as private because some of the processor they can submit some of part of the array and they have the value of the local sum. But also you have the shared variable sum over there, and then from the local sum together they can put it together over here, something like this one. So this is the pragma of MP critical. So maybe only one processor can put it over here, like that sum they will put local sum over there, over here. So we have private and also a shared data over here. But you have to do it in careful, yeah. You have to do it in careful. But sometimes if you do not do it in careful, you might get a wrong result. Okay. Just to make sure that if you are doing the parallel computation, make sure that the output should be the same. Okay. If it's not, there's something wrong. Okay. And this is the critical action. You can, as I said before, you have to be careful when defining the critical section. Also, when defining some variable to be private or shared or global. This is the bad thing. You cannot do it in parallel, something like this one. The for loop cannot stay early. That's when this is the bad thing in OpenMP. Do not never do like this one. Eh? Okay, this is nothing. Okay? This is nothing. And the next one, like this one, you cannot do like this. That means you are trying to set the idea, the index, which is not visible, which is not visible. So please do not do something funny like this one. This is exercise number 5. Okay. The 4 exercise is MPI. This is exercise number 5, OpenMP 1. I think it should be easy. You only need to recode this one and run it and using maybe 8, 16, 32 or 48 process thread. What you can get, what you have on your screen. Okay. Okay. The next one. This is another exercise. Also, this is exercise number 2. You can see. You can. It is open barrier. You can write, compile, run the following 2 codes. Try to look at the difference. Okay? Try to look at the difference. Okay. Try to look at the difference. Okay. This is OpenMP 2. Yeah. This is so that we have 6 problem. Okay, we have 6 problem. The next one, we have OpenMP 3. So we have 7 problem. But you have to do it by your own. Yeah? To parallelize the PI code using OpenMP. But remember that you can do it the parallel over here. Yeah, over here again. Remember, you can do the parallel by using the parallel on for loop, yeah, for loop over here. At least over here, again. You can see that. You can see over there. That's the hints, yeah. You can do the parallel over here, again. The rest, the other, the neural part that can be parallelized, but I suspect that would be of it. You can see that the n is very large, yeah. So that means this is the one that can be making in parallel by using for loops parallelization, okay. 7, 1, 2, 3, okay, 7 problem, 3. This is, okay, this is. Okay, this is last night I test this one, it's working. Okay, if I have the word MPI.c, if I compile it with MPI, it gives you the output, the objective, the Excel file over here. Okay, if you do the computation with OpenMP, if you have the codes in OpenMP, you can compile it over there. When you got this one as the output, okay, then when you got this one as the output, you can submit the job like this one. Okay, you can submit interactive done and then try to run it with MPI minus n with the number of processor and then the name of the output of this compilation. Okay, either this one or this one. But you can also submit it like JavaScript with MPI, something like this one. Remember in the folder that Andrea I just showed you, there is get PGSS. That means the script for the job submission for metric calculation with scattering and gathering, something like this one. But you also have this one as the output of the compilation already there. So we would like to run it with 16 processor. Okay, this is for your exercise before you do the homework. Okay, this is to make try to develop your own confidence. Okay, we know how to compile and we know how to submit the job, and then you can start doing your homework. Okay, this is for MPI single node job submission, and the next one is for if you try to use 16 thread, okay? So that means for call from for node, you do it something like this one. Also the same thing, you do the same code over there, but you are using 4 nodes. Okay? You are using 4 nodes. Okay, you are posting nodes. And then maximal process for nodes is 4. That means until 16 you get until 16. That means you can read until 16 over here. Okay, 16. So that means if you are able to use 48 core, that means we can define until 12 nodes. Andrea, can we do until 12 nodes in here? How about the number of processor per node? How many processor per node?
Max processor per node. So max processor per node, it's up to 48 cores.
Oh, so
correct me if I'm wrong.
So that means in here, if I would like to put to run it in 48. Okay. Okay. 12. Yeah. Okay. Okay. You have various communication. Okay, various communication. It's really nice if you try to look at what's the difference. Okay, what different? But we suspect that it might be the communication. If you use more than nodes, that means the communication might be larger. Okay, might be larger. This is for OpenMP job over there. We tried it before. It's work over there. This is how if you try to submit a job over here. Just submit job there, and then you can sleep for a while, maybe about 3 or 5 minutes, and you will get the result. And then you can also observe the submitted job like this by submitting this over there. So we have. Let me look at the exercise. 1, 2, 3 OpenMP. Sorry. Let me. Okay. I will assign the student name.
Student names. Okay.
MPI1, MPI.
Anyway, Ina will help me with the student names, I would like to share you how we compile
Okay.
and
Okay, let me. We will assign this into the student. Yeah, maybe one student can only work one exercise, but you have to record the way you work and get the result by recording your screen either by using Zoom or something else. Okay, and then we will share you the link for submitting your names and your links of your recorded video. Okay, and tomorrow we'll play that video. Okay, okay. Is that clear? Is any? Okay. Andrea will give you some more information. I will stop the sharing. Okay, please, Andrea.
okay. Before you have lunch, I will ask you for your attention regarding to this moment. Ya, bentar. Okay, I'm sure that you are already connected to SSH, to Fugaku. Have anyone already connected to Fugaku? Okay. And then for computer science, right? You can copy. Okay, I show you. Oh, can you see my screen? That's all. No? Hopefully it's good. Okay, you can SSH with your account, and because you already copy your SSH key to user management, Fugaku user management, and then you can SSH. Okay, and for computer science track, you can copy the material from, I forget, slash. Share RA23, I guess. 4. Call CPU C parallel and copy to your home folder. Sorry. I'm a little bit nervous. Anyway, and you get a CPU parallel here. There is a folder for sources. Here you have hello world MPI with hello world MPIC and everything. So for the compiling, you can use the MPI FC PPX -O, for example, but I will not go into the code myself, and then you can compile with maths.c. Here, probably I hope every one of you know how to compile MPI. The FCCPX is specific for the Fugaku, so I assume that F means Fugaku, so MPI Fugaku C compilers collection X. And then you get the executable file, and in this there is a sample for the submission. You can see maths.get. PGSH. There you can have the RA, so your group is RA 22304, and the resource group we are using currently is small. Because for small, as mentioned by Georgie yesterday, that for small you can have up till 384 nodes, if I'm not mistaken. So you can have more nodes, but you also need to go to the small queues. If there are many jobs already on the queue, so you have to wait. But you can also have, there's a special group for this school. I'll share you later. Probably there is also in the Slack already. And that's a group. That group will have specifically given by this school only. So you will have smaller competition with other user. But you can have only one node only. So you can submit with PG sub get no, sorry. And it said that PG sub is already submitted, and then you can monitor with PG stat. It's already submitted, and we can just wait. And after that, there will be some outputs. There are three text file .out, .r, and .stat. .out, it means output. If your program outputs something, it will within the .out. And .r is for the error message. If you have compilation or execution error, they will be reported in .r. And stat, because we put the export, PGM -s, it show your statistic of your jobs. It's already completed? No, still. This one, because the first was error. You can see the error because it's my fault, so not a real problem. Still waiting. Anyway, daftarnya udah kirim ke siapa? Teks saja. Aku kirim ke daftar teks, bukan teks full name aja. Jangan. Mana? Yang teksnya aja, teks. Nama only. Jangan kita pakai PDF. Okay, we still wait. Okay, we wait, and hopefully it will go into something output job number. There are some folders /0/1, and then there is text output there. So it will be the output of your program. Still waiting. So I will not take more time. So where is the name? Iya, makanya don't use.
Andrea, can you share the student list so we can assign?
Yeah, Roman. I will give you. Yeah.
By the way, if you log in into the slack.com at computer science track, I put the link for your homework submission in the message.
Still have not submitted, so we can see it later. If there any question. Oh, okay. Expected to start to 2:00. Ah, okay. Yeah. So it will not run anytime soon. So, unfortunately, okay. Anyway, just leave it there. So, at least I hope you already know how to submit the job, and if anything happens, so you can call us with the question. Okay, anyway, is there any question to Prof. Heru before we have lunch?
Okay, the point is just to make sure it's correct, okay?
Yes.
Don't submit the job and make it run next year.
Okay, anyway, if there's problem from computer science track, we can ask me, or if I not can handle it, I will ask Georgie. Georgie, will you help me? Georgie, will you help me? If some problem with Fugaku, I will ask for your help then. Oh. Okay. Anyway, any question to Prof. Heru? Panggilin Rifki.
Can I have the student's name for computer science track?
I have sent
In WhatsApp? Okay, just a second. Okay. Okay.
That's
Okay.
Udah. Okay. In a few minutes, Prof. Heru will announce the groups of your
Okay,
students.
let me. Can you share also the Zoom, Mas Andrea?
Sorry, Zoom?
Can you share the Zoom?
Yeah, you can share your screen.
Okay. I can share the screen. Just a second. Okay, I can screen the whole my office. Can you see my? Screen sharing, okay. This is MPI 1, MPI 2, MPI 3, MPI 3, MPI 4 exercise. So there will be 4 problem for MPI and 3 problem for MPI. Open MP 1, open MP 2. Just look at the slide, okay. This is the problem exercise 1, exercise 2, 3, and 4. This is the open MP exercise 1, 2, and 4. And I do have, just a second. I do have the student name over here. Just let me see over here. Okay, see. Maybe if I pass it over here, just keep stack over there. Okay. Maybe start from the above. This is MPI 1. Okay. MPI 1. Okay. And this is MPI 2. MPI 3, this is MPI 4, this is open. open MP2, open MP3. It will continue like this one. Okay, let me see. I should put the in. Can anybody who is excellent Excel? So then I don't have to put it one by one. Okay. MPI1, okay. This is MPI2. This is MPI3. MPI4. This is open MP1. Open MP2. Open MP3. Yes, we start again with MPI1 again. This is MPI1. MPI2 again. This will be open MP1. Open MP2. MP3. And we go again to MPI1. MPI2. So if you have one exercise to try to compile it, submit it, the jobs, and display the result, and explain it to us, and record it either with Zoom or with others recording material, maybe about 2 or 3 minutes. And then so once you got the recording material, please submit the jobs, your exercise at the following. I put it in the Slack already. Here. Oops, sorry, not like that. This is all. Just look at this. Yeah? If you click this one, you just need to put your names and your links of your. This is you put your name over there, and then your video displaying the process. Only the link, not the just the link. Just the link. The link of your recording. Okay. Just. Pardon? Yeah, it's only for computer science student. It's only for computer science student. Okay. Okay. It's only for computer science student. Is there any question? Is there any question? Okay, any question? If there is no question, I'll give the mics to the MC, Mas Andrea. Okay, thank you very much. See you until tomorrow, yeah? We will see the beautiful video from all of you, from computer science student. Okay, thank you very much. Good afternoon. Assalamualaikum.
Thank you, Prof. Heru. And we come to the break, and we have 1 hour lunch break. You can have lunch outside. And we'll come back at 1:20. And remember, tomorrow Prof. Heru will give lecture in the next door on room C for computer science track. So here, this room, it will be for our science or life science, I don't know. Life science, and the next door will be on our science. Yes. No, tomorrow will be from morning. So there will be 3 parallel sessions from the morning for tomorrow, and for earth science, life science, and computer science track in 3 different rooms. Sorry? Yeah, today we're still in the same room, and after the break, we'll have a performance analysis and optimization introduction from Dr. Brandmore. See you around later.
Okay, just okay, just announcement to computer science student. For those who do not have the certificate, please work on together with the student that has the certificate. You can work together in the group based on the problem assigned to you. Okay, okay. If you do not have the certificate, please work together with your friends.
I just have a question. So for the MPI one, this is one.
Okay. Yeah, right. Okay. Welcome.
Recording in progress. matrix multiplication and FFT and so on. And on top of that, you write your application. So it's not only complicated hardware, but also a complicated mixture of program modules. And something can go wrong in all of these places. Yeah. So it's a very interesting field when you work in this. But it helps if you develop a positive attitude. So it's not like a mess or it's horrible, but it's an opportunity. It's an opportunity and challenge you can solve. Yeah, as an opportunity to make interesting new research, find out new algorithms, make something. And if you have to think it this way, yeah? You have to think it in a positive way, and then it's a lot of fun. So I basically just said that, yeah? Like in order to do parallel programming, yeah, we have to distribute the data to the memories, we have to distribute the work to the processors, and then we have to organize and synchronize the workflow. Yeah, and I use a little, almost the same example. Oh yeah, security, yeah. Good idea. As Professor Haru, so he is using to build a wall, and my example is making a hole. Yeah, you want to make a hole, and so like you have a big hole, so you divide up a work, so you make 4 pieces of your hole, and then you assigned different people in the different. So basically these are your workers, yeah, and some of them do the digging of a hole, some of them are the communication, they transport the earth out of a hole, and then you had something to synchronize, we make sure that no one is drinking coffee and everything is working together, yeah. So basically this is how it's working, and when you have to develop a program for a computer, you have to think in this way. How do I divide up the work between different cores and so on. So, but now, I said, this is parallel computing, and now we come to HPC. So HPC means highest performance. That means I not only make it work, but I make it work in the most efficient way. Yeah, with the least resources, with the least amount of power, and so it's not costly. And this is the extra twist. So when we evaluate parallel programs, yeah, basically we have to, you don't know in the beginning, is it working well or not? So we first have to basically find out, yeah, is it good or bad, and so on. And so there's basically 2 things. Either it's not running fast enough, yeah, so say a weather forecast, yeah, you want to forecast the weather for tomorrow, but if the forecast program takes longer than 24 hours, it's useless. Yeah? So you need, sometimes they have to get as quickly as possible. The other thing is sometimes you need to work on a lot of data, so you want to use more processors more as possible, and this is scaling, it's called. Yeah? You scale out, and sometimes they say, okay, it works with 4, it works with 8, it still works with 16, but at some point, adding more processors doesn't help you anymore. Think about like you move your apartment. Yeah, you move from one apartment to another one. You get some friends. But if you just have a small, like 1-room apartment and you invite 20 people, we are just blocking the door and it's not helping. So yeah, the number of processors has to be kind of consistent with the amount of work you need to do, and this is basically the scaling problem. So we have to either find out, yeah, is I'm fast enough, and do I use the right scale? And this we call performance analysis. So you analyze the efficiency, the performance of the application to do that. And there's actually tools, software packages, which allow you to do that. And I talk about that in my next lecture in the computer science track, what tools are there and how to use that. But here for the general portion, I only talk about general concepts. So that's the first part. You find out, is it good enough? And if it's good enough, be happy, go on, do your science. Yeah? But unfortunately, often this is not good enough. Yeah? Like, typically, it's working really bad. So then you need to develop better approaches, and this is called, like when you make a car run faster, it's tuning optimization. And this is actually the more difficult part. Finding out if something is bad is easy, but how to fix it, this is a difficult problem. And the problem is, even for me as an expert, because it depends on your application. Like some person in astrophysics uses totally different algorithms and data structures than someone in biology. And I'm a computer science expert, but I'm not an expert in all these different areas. So I can give you some, as a performance expert, typical advice. This is the overall problem, but how to fix it, it's typically left to you, unfortunately. Yeah? It's like the professor says at the end, yeah, and the rest is homework. Yeah? So it's basically the same way. So what are factors who influence the performance of a program? And I divide it up in sequential factors, which is basically just how do I calculate something on one core, on one processor. It's also basically for a normal non-parallel program, it's the same thing. So it's basically how fast I can do the computation, yeah, how fast is my algorithm to do the instructions. Then accessing cache and memory, which is very important because memory is typically much slower to work with than actually the calculation. So you have to make sure that you can get your data into the processor very efficiently, and also input-output is the same thing. Yeah? And then on top of that, you have the parallel factors, factors which will influence if I'm using more than one processor. This is the communication. Like with MPI, you send messages around. Every time I send a message, I'm not doing anything useful for the communication. I'm just exchanging data, which I need because the other processor doesn't have the data yet. The same thing is also like creating threads, creating processors, synchronization, waiting for each other. You can waste a lot of time waiting for each other. Yeah? And so, again, so you have to optimize basically how to make that very fast and how to basically make the parallel interaction very fast. And then, so basically, yeah, how you can do that. So for computation, yeah, you have to basically find the right algorithm. Yeah, like even for matrix multiply, there's probably now several dozens ways to do a matrix multiply, and it depends on your matrix or something, you have to use one or the other. So you have to either look at the literature or find some expert in your area to basically do that. Also, the compiler can help you here. The compiler often has flags for optimization. So some people know there's an O, O1, O2, O3, means O3 is a higher level of optimization, or so, and sometimes they have a dash fast option, and all kind of weird things. So you have to look, like at Fukaku user manual, what are the typical options I should use to produce fast results. Cache and memory is tough, because you write your program, somehow the compiler generates instructions to get data from memory, but it's not really under your control. But it could be a big problem if you are accessing the memory in the wrong way. So, and the problem is to find out that you're using the memory in the wrong way is also hard, because it's in the hardware, and there's no way to really look into the hardware. And then input-output is also an important problem, but people have already so much to do with the first two that often the input-output is ignored. But once you reach like your program is working and you work it on larger and larger experiments, at some point you also run into an input-output problem. The parallel factors are actually quite good understood. So we have now classes developed for MPI OpenMP, various framework libraries that said, okay, if you want to do this, you do like in a master slave or in a master worker setting, or you use a pool, and there's different things, and there's actually tools I can show you tomorrow how to find out problems in these factors. But the other part is a little bit yeah, harder. So if I, sorry, a second. So if I want to do that, basically this performance analysis process, it's a process. It's not just like one thing, it takes multiple steps. So the first one, I need to collect data about the execution of my program. Yeah, I need to find out what's going on, and this is called instrumentation. So what it basically does, you take your code, and additional code is kind of put into your program, which collects data. It's counting, measuring time, and so on. And there's typically tools which help you by that. You don't have to do it yourself. But basically first you instrument your program. And instead of your normal program, you get a program which has additional code. And when you run it, that instrumented program, this is called the measurement. So you measure, so it produces your normal, whatever, matrix multiplication or whatever, but in addition, it generates data about the performance. Yeah, so this is called a measurement. Then the next step would be analysis. So you look at this collected data, and then from the data you can identify specific problems. Is it too much communication, too much synchronization, bad memory behavior, and so on. And then that basically you want to make, for the user, you want to make it nice. So it's typically some presentation tool which gives you some graphical display, you know, some bar charts or histograms or things like that to show you basically about the data, and then you know that basically, okay, what's wrong. Yeah? And then based on that, as I said, you say, okay, this is wrong. Then the optimization part comes, but as this is basically left to the user. Yeah, so the upper parts, the first 4 steps are basically, you can download tools which basically allow you to instrument, measure, analyze, and present the performance data, but the last part is up to you. But you're not done. Yeah, because you fix something, but to tell you you haven't fixed it, you thought you fixed it. Yeah? And you have to find out whether you really fixed it. Yeah? So what you do, once you made your changes, you do it again. Yeah? Measure it again. Is the problem really going away? It could be that the problem is gone away, but you got a new problem. Yeah? And so this is like running in circles, and you do it basically, at some point, of course, you have to stop. And it's either that the program is fast enough, when you're lucky, or you run out of time, or and so on. Yeah? But basically, this is the basic process. Okay, so that, as I said, is just the introduction, and now I talk a little bit about what kind of data is measured, and we call that metrics. And then we look at how to instrument programs, how to instrument parallel programs, and a little bit measurement techniques. So what is a metric? It's basically things that we can measure. So we can count how often something happens. Yeah, I count how often is the function ABC called. Yeah? Or how many messages were sent from A to B. We're just counting things. The next thing is, it's very important, the duration. Yeah, like how long did it to run the solver or to send a message? How long did it take? Or the sizes, yeah, like number of bytes transmitted and stored and so on. So these are simple metrics, and then we have derived metrics, which are typically used for normalization. Yeah, so it doesn't help you if I say, yeah, I had 1,528 cache misses. Okay, but you say I got so and so many cache misses every second, then you get a better thing. Yeah, if you divide it by the time, or also like the function took so long, but on average it took so long. So these derived metrics allow you to basically get better. So most tools collect the raw metrics, but then calculate with more useful derived metrics, and this is what they present to you. So what are typical metrics? You might have heard already something like MIPS, millions of instructions executed per second. It's just a measure how fast your program is executed on a processor. Most simulation programs are actually doing calculations in floating point numbers. So what a lot of people are using are flops, floating point operations per second, which is actually funny because in normal life a flop is something bad. But in HPC, flops is good. The more flops, the better. Yeah? Then execution time, of course. Execution time is divided up in, we call them wall clock time. So you basically, I start my program, I look at the wall, at the clock, it's running, and I'm done, I look at the wall again. So it's the real time, the clock time is really executing. Sometimes on a computer, also CPU time is available because, especially on a login node where different people use the computer at the same time, The wall clock might not be the right measure because in between other people that do calculations, of course, this is not for your program. And when the CPU timer only counts for execution your program was running. And depending on the situation, you have to see which timing I'm using. And then there's something called hardware counters. I tell you what that in a minute. And then, of course, beyond that, there's like benchmarks. You can run this predefined set of programs you run and measure. It's to compare computers and so on. And Jens will talk about that in 2 days, I think, about benchmarking and so on. And then, of course, on your application, you also can have specific things, yeah, like how many time steps I'm doing, how many molecules per second I'm processing, how many like climate program, how many days I can calculate, how many days of simulation, how many days can I simulate within a day or something, and so it also gives you something to compare. So the first thing a little bit about flops, which sounds like a simple concept. Yeah, you say, okay, I'm just counting every addition, multiplication, and so on, and measure the time in seconds, and I say, okay, I executed so and so many operations in a second. Sounds simple, but it's nothing in HPC is simple. Yeah, so the first thing is these numbers get meanwhile quite large. Yeah, so you use this international prefixes like kilo, mega, and so on. The big computers like Fukaku and others, they are meanwhile at the exaflop range, so it's 10 to the power of 18. Yeah? Yeah. But then you have to basically go out for, when people talk about, oh, my computer has so and so many flops or something. Yeah? So there is the difference between the peak or theoretical performance, so how much could the program or the computer do if everything is working perfectly? You wouldn't have to wait for data. Nothing. Yeah, you always have something ready. So what is the theoretical limit? Like you can't go any faster. But of course, in reality, you have to wait for data, wait for messages and other things. It's typically lower. But people, of course, want to kind of say, oh, my computer is bigger than yours. So they don't tell you it's like a real measure, but it's the peak one. Yeah. So I could go as fast if I would. Yeah. So yeah, but you have to compare. But when people tell you, is it peak performance or measured on some real program? Then, do you count every operation or all the operations which are useful? Yeah. I mean, you think you do your matrix multiply and something, and then at some point you need to synchronize. And while you're waiting for the other processors to become ready, you could just add a few numbers. Yeah, and it would basically get the number up, of course, but these useless, it's not useful at all. Yeah, so just generate lots of operations is simple, but generating lots of useful operations is much more harder. Now with AI, this is another, the latest thing is, in HPC simulation programs, we use double precision numbers with 64-bit because it has a high precision. AI is lucky that it doesn't need that. It can do it in like half precision, I don't even know how it's called, like a half of half, like 8-bit or even more. And then of course, because the hardware is up, they can go much faster. Yeah. Again, so if you want to basically don't mention that, so like our computers we're getting next year in Jülich is an exaflop computer, so it has 1 exaflop performance. But when I run AI programs for NVIDIA, I have 90 exaflop AI performance. Yeah, so I can say I have a 90 exaflop computer and not telling people, oh, it's only for AI. Yeah, you have to, yeah, you have to be careful. Another thing. And I said it's details, but I just want to get the point over that most of the concepts are simple, but when you look at the details, it's really getting complicated, and to become an expert, of course, you have to know the details. Yeah? Another thing is like, is it operations or instructions? So some processors can do a multiply and an add in one instruction. So these are 2 operations, multiply and add. So do you count it 2? Or you count it 1 because it's the multiply add operation, yeah, and things like that. And so Floating point is nice, it's good for bragging, large numbers, but when you really want to compare and give useful information, you have to specify, yeah? Is it double precision? Is it this, what I'm doing, so other people know when you see your number, how to interpret it. Same thing with time, yeah? So the wall clock time is the most easiest way, because you just basically start the timer, stop it, like a clock in your hand. But it includes all the waiting time. Yeah? You're waiting for I/O from or memories and so on. And as I said, on the login node, you share it with other applications, so it's not useful there. But luckily, in HPC, what we typically do, like when we run a program, we submit it on some cores, and these cores are just used by us. So if you're using these nodes in a supercomputer on your own, it's not shared with someone else, you better use wall clock time, because it's just the most reliable and best way. But if you are in a cloud environment or sharing the stuff with other people, then you better should use a CPU timer, yeah? Which is basically operating system only counts the time when your program is working. The problem is that this is depending on the operating system, it's not well defined. What does it mean? My program is running. Sometimes the I/O, which is done for my program, is included, sometimes not. So it's useful for performance analysis, but not so good for comparing between systems. Yeah? But wall clock you can always compare, because the real time is the same everywhere. The main problem also is, even if you have your own set of nodes, you're still using the file system with other people, and you're still using the network with other people. So if someone else is currently doing a lot of messages, it could also affect your program. So we'll notice you run your program 5 times, and you will get slightly different numbers if it's a good computer. Yeah? Say it's 40 seconds, 41 seconds, and 39. Yeah? But it could be, if it's really bad computer, it could be 40 or 80 or something. It can go up and down quite a bit. Yeah? So when you do a measurement, you typically have to do it multiple times to see, is it deterministic? And if it's not, because it's kind of fluctuating, you have to basically make multiple measurements and take the mean or something to have something useful. Okay, so how do I measure time? There's functions, of course, in MPI. So you have an MPI program. This is the Hello World program. Professor Haru showed this morning. Yeah, you initialize the program, get your rank and how many processors, and then you print out I am 1 out of 5, 2 out of 5. So in order to measure the time, there's a function called MPI W time. W is for wall clock. And when you just have 2 double values, you do it before and after what you want to measure, subtract it, and then you know how long it was going. Yeah? So it's kind of simple. So this is the one in C. I'm not showing you what people are using. So this is C. This is the version in Fortran. Basically looks the same. It's the same. When you have OMP, same thing. Yeah, there's a function called OMP get W time. And again, you call it before and after the section you want to measure, or begin at the end of a program, and calculate the difference. And so you can, it's always good when you write a Perl program, especially a larger one, not like this Hello World, but you put these in and at the end print out how long it's going, just to see a feeling, is my program also executing roughly in a deterministic way. Okay. Okay, so hardware counters. I said already, we have a hard time looking into such processors, how the memory is behaving, or cache, or other things. So also, the people at the companies who make these chips, they also need to make sure their processor is working. So what they did, they put special hardware in these chips to count things and so on. Yeah? And when they say, okay, I run an algorithm and it executes 100 instructions, and when we look at this special counter which counts the instructions, and is it really 100 at the end? If it's 101, I don't know, where does that other instruction come from? So in the beginning, this was used internally by the hardware designers to do their debugging and controlling. But when the HPC and performance people like me find out that, hey, great, yeah, and let me access these counters, and then by these numbers, I know how many cache minis happened, how many stalls, and so on. So this is really nice. The problem is there's no standard. Basically, if you go to different like ARM chip or Intel chip or something, they have used totally different counters with different meanings. Some of them are not working, some are not documented, and so on. And it's even worse that even between generations, yeah, like you think Intel, yeah, but you get the Sandy Lake, and then the Ice Lake has other performance counters or something. So when you want to use them, it's not easy because you would need to know what process I'm using, how to access them, what was the meaning. So it's really complicated. Luckily, there's something called, PAPI. And it's basically people, the only thing they do is every time a new chip comes out, they do research, what counters are there, what is their meaning, how they are accessed, and then they basically have a library, it's called PAPI, and then basically you use basically the same, it's like MPI, use the same PAPI, like PAPI give me this counter, PAPI get me that counter, and they do all the work to find out what is the right commands to do that on processors or something. So using PAPI, you can do that. And then there's a high-level interface, which is for program developers, which basically you want to cache, like measuring the time. You measure how many cache misses or many floating point operations you can use for that. And then there's a low-level API which allows you to do all kind of weird things, but this is for people like me who develop these performance analysis tools so we can get all the really detailed information. And this is just like a very simple example. You would really have to look at the documentation, but basically you say, you have something you want to measure here, and then you put PAPI high-level region begin with a name and PAPI high-level region end. Yeah, and then it measures it between that, and you can do it in multiple places with different names, and then it produces a file and saying basically, like in the region computation, you had so and so many cycles, instructions, and so on. And then there's an environment variable where you can specify the different things you want to have counted. So this is actually quite nice. Okay, yeah. And then there are so-called standardized or preset events, which basically we have standard names. So like instructions, level 1 cache misses, level 2 cache misses, and so on. And they might be available in all the different systems, and PAPI makes sure it translates to the real things counted on the processor. But it also makes all the special events which are available on that processor also available. These are called native events. And there's commands PAPI avail, basically gives you the output what standard events are available, and PAPI native avail tells you which are all the other counters available on that system. So here basically is the output. I am sure you can probably not read it in the back or something, but when you do it on Fukaku, on the compute nodes, it basically tells you some things, how many counters are available, cores, and so on. And then it gives you a list of basically, yeah, like what counters are available on that system, yeah, and then you can use that and so on. As I said, you can later look it up in the slides. The details here are not so important. Okay, so this is basically the basic stuff. Measuring number of iterations, the time, and some other hardware counters. So the next level of interesting behavior is load imbalance. Yeah? I said parallel computing, one thing you need to do, you have to kind of distribute the work and the data in a way that every processor has roughly the same amount of data to do. Yeah? Because otherwise, if one is faster, it's just waiting for the others to finish and it's not. Yeah? So, and how can I get a feeling how good my load balance in a program is? So I have a specific region, yeah, like my matrix multiply or whatever, some operation, and I will say, is that balanced? I measure the time before and after on that section, but on every processor. And then basically I take the time basically from the slowest processor who took the most time, the maximum time, and then I calculate the average time, and I subtract that, and basically this difference is a metric for which basically tells you how much of that is it bad. Yeah? So the more closer it is, it would be close to 0, it would be fine. The larger the number is, the worse it is. So this is for computation, and if you are have a barrier, a synchronization operation, you are taking the average time and basically subtracting the guy who's the fastest, who gets into he's done first, basically. And then it gives you a factor how bad the synchronization is. Yeah, and you can also calculate a percent, but I'm skipping that here, it's a little bit too detailed. Okay. Other things, what you often hear in presentations and talks, is speed up and efficiency. Yeah, so this is about, especially if you scale up a program on multiple processors, how good or bad is that working? So it looks complicated, it's actually quite simple. So first, you think about, I have an algorithm which I run just on one processor on my laptop. Yeah? And I take the best algorithm to do this problem I want to do, and I have a specific problem I want to solve. This is the size n. And then I parallelize that program, so I have now another algorithm who does the same thing in parallel for the same data problem, but I'm using now P processors, like multiple processors. Okay, so when speed up is calculated by, I take what is the time for sequential, and I divide it by the parallel time on that processors. That means, so if I use more processors, it should go faster. Yeah? So the idea is, like think again about our moving your thing from one apartment to another. You do it yourself, it takes 1 hour. Or say 10 hours, it's easier to calculate. And when you're using 10 people, ideally it should be just in 1 hour. Because, yeah? But, as usual, the thing is that, I mean, we are blocking itself on the stairways up and down and things like that. So it could be that you're doing it in 2 hours. Yeah? So it would be 2 by 10, so it would be 5. Speed up would be 5. Yeah? And efficiency is the same thing, just with you multiply by the number of processors, and instead of going from 0 to n, it goes from 0 to 1. It's just normalization. So basically, the most efficient would be 1, and worst would be 0, and by speed up, is it between 0 and p. Yeah, and then you do this measurement, basically you say, okay, I measured on one processor, and on 2, on 4, 8, 16, whatever, like some higher numbers, and then you always calculate the speed up or efficiency, and you make a line. Yeah? And so there's something called a linear speed up. Linear speed up means basically the more processors I'm using, the better I'm getting. In a specific, it could be like this or this, but at least it goes always up, but in a linear fashion. So it's not, then the perfect or ideal speed up, which you typically never get, would be, for every processor I'm getting, for 10 processors I'm getting speed up 10, for 100 I get 100. This is the 45-degree line. The typical one is you start up and you're using more processors, but at some point you don't have enough things to do for all these cores, and then you level up. So this is the typical line. Which is not bad, it just means I run my program here. On that, I don't have to use more nodes, it would be a waste, I just running it here. Then there's a funny thing, it could be that, it's called superlinear, you're running and it's faster than the number of processors. So you're using 10 processors, you're 12 or 15 times faster. How can that be? It could be at the algorithm. Yeah, think about you are searching a book in a library, but you don't know how it's ordered. So you go in the first row, you look at every book. Is it my book? Is my book? Second row, very good. Until you find the book. Now you do with 10, like the same thing with 10 people. And they start in different rows. So it could be that, like, because in the beginning of a 9th row, it's the 9th person finds it very quickly. And then, of course, it's much, much faster because the parallel algorithm can be. So that's, but this is very rare. It's typically for search algorithms. But other thing can happen is, so as I said, the problem is often the processors are meanwhile quite fast, but you have a hard time getting the data into the processor fast enough. And for this you have the caches, where you get data which is used all the time, you have it in this fast cache, and you can use it. And so at some point, if you use more processors, you have, of course, more caches, and at some point, all your data fits into the caches. And then it runs faster because you don't have to get it from memory anymore. Yeah? And then you, at some point, has a fact that it goes faster again. But again, it only works for a program who using the data the same data all the time. But this is just when people talk, oh, my program has linear speed up, whatever, just that you know what it means. Yeah. And then, now there's a funny story. This is actually, it's really old. At that time, I was only 7 years old, which means it's really, really old. So a person named Amdahl, he said, oh yeah, this is a crazy idea with this parallel computing, but it will never work. Yeah, and how, I mean, he was kind of, probably had a mathematical background. And so he said, okay, yeah, let's think about this. Yeah, I have my parallel program, and typically I have to do something to prepare and set everything up. There's a portion which only runs with one processor. Then you do the parallel stuff, and then you have the serial portion again. So, and now just for mathematical reasons, you say, okay, it runs in one time unit. Yeah, it's just a scaling. Yeah, so basically speed up is the sequential one. So sequential means I'm running in one time unit. In parallel, I mean I have a specific fraction, like this portion, this is f, say like 10% or 20%, which runs serial. And then that part I can parallelize. So if I have n processors, I can divide it by n. So this is basically 1 minus f, which is the rest of it, divided by the number of processors. Yeah? So it's just like the thing. And now I think, okay, now I do the mathematic thing. I make p larger and larger and larger. I'm going, like, limit of p goes to infinity. So this term, yeah, we get smaller and smaller. So at some point, this goes away. Yeah, so the limit is 1 to f. 1 divided by f. So, but as I told you, in a typical program, like this is ideally like 5%, but sometimes 20%. So now we just look at how does 1.f look like? Yeah, okay. So this is a chart, the speed up, and then the processor. So I plotted, like the blue curve means f is 0.1, so 10% is serial. And when you calculate that formula, you see it never gets more than 8. And if I use a 10th of a percent or something, you get more, but it's always flattening out. Yeah? And as I said, and typically it's more like 5 or 20%. So he said, I can prove with mathematics it's not working. Yeah? Everything more than 4 or 8 is useless. Yeah? And many people at that time said, okay, I do something else. It was a good idea with his parallel computing, but yeah. But you know now, I mean, Fukaku has 7 million or 5 million cores. Kengo, do you know, or Jens? Yeah, several million. Yeah. So how does it, so mathematics says it can be faster. Yeah. But how can we have these machines who have so many thousands and millions of processors? So what's the wrong thinking? And luckily, someone came about. Yeah, okay, that was too fast. So first, in that case, he was even optimistic, yeah, because in that formula, you didn't count any communication, synchronization, and load balancing. So it's even worse. Yeah, but basically, but he also was too pessimistic. And the thing is, there's laws, but everyone knows you can break laws. You'd have to follow the laws. Yeah? So the thing is, you can have better parallel algorithms, which get better, and with superlinear scale-up. And the most important thing is scaling. Yeah? The thing is, the time used in the sequential portion can get smaller when you use multiple processors. And the other thing is, when you look at the formula again, let me go back. This is the critical part. So I'm using a sequential algorithm of a specific size, and I use a parallel algorithm on the same size, independent how many processors I'm using. Yeah, but think about the same with, of course, you move your things out of your apartment. At some point you have too many people for apartment, but think about you are moving like a whole dorm. Yeah, so you're using larger problems. Yeah, you divide people out within the dorms, and so you can still use it. Yeah, so what Amdahl basically kind of ignored is, oh, you can, with a larger computer, I can do larger things. Yeah. So, and then there's something basically called strong scaling, yeah, which means, yeah, I keep the problem, like here the size of a hole, the same. This is called strong scaling. And then, of course, at some point, I have too many people for that problem, but as I said, with more people, I could do something like this. Yeah? If I use 2 people, I make my hole twice as large, with 4 people, 4 as large, or some factor. And this is basically and this is called weak scaling. So this is basically what most people are using. Yeah? If I want to use these large computers with many numbers, of course I scale up the number of my work. So when people talk about, yeah, this is my speed up curve or something, you should basically, it should tell in the paper or in the presentation what is the scaling factor. Yeah? Otherwise, just saying, oh, I have a good scaling is useless. I need to know basically, yeah, like how did at the same time the work develop and so on to compare it with other things. Yeah. Okay. So, and why is load balancing, I mentioned it before, a difficult problem? Yeah. The problem is, yeah, I have the divide up the work. Yeah, I have my hole I have to make. And everyone needs to do, basically, I said, okay, I have so and so many people, so and so many fields, I split them up exactly in 4 quarters. This only works in the most simple problems, because what you don't know sometimes, yeah, you work on something, so you start digging, oops, I'm really, I shouldn't do that, sorry, I'm breaking. Okay. Yeah, like you start digging, and here basically there's sand, and here's some mud, and here's rock. Yeah, and suddenly now, like these people can dig much faster, will take forever, and here like in the middle. And then it could be, okay, when I move more people from here to here, but once basically they broke through like 1 meter of rock, and there's sand actually there. So this is just an example what can happen in your application. It depends. But the things you are calculating, is it always the same? It's static? Then it's simple. You just divide it up. But if you're depending on where you are, which molecule or atom you're currently processing, it can change. And then you have to, sorry. Yeah. Saves the day, as usual. Yeah. Yeah. So, I mean, this is just a picture, but it basically, what does it mean for you as a programmer? The more you don't know about your distribution of the work. Yeah. So they say, I'm doing astronomy, and you're working on the different stars. But depending on the star, you have to do different calculations. And I don't know what is the next star or something. You have harder time to do it up. So that you have to write extra code to watch the situation and move data between the processors to balance it out. Yeah? But of course, this takes away time because it's extra work. Yeah? So this is like one of the typical really bad problems. Okay. I'm doing in time. I used half an hour or something, or longer? So I probably need another half hour or something, that would be fine. Huh? I have 1 hour. Oh, perfect. Okay. So that was the really high level. So now we come to the portion where, okay, I'm an expert in performance, and I want to write a performance tool, and I want to help you finding out how bad is your program, and if it's bad, where in the program it's happening and when. Yeah? The problem is that when I measure, I get the hardware counters, I get the times or something. This happens on the hardware, but of course you are thinking about your, oh yeah, this is the calculation I have to do. And then of course this is translated in an algorithm, compiled by compiler in instructions, executed. There's a difference in between. But of course, if I tell you whatever, this instruction is bad, it doesn't help you. You want to know basically what step here is bad. So I, as a performance tool person, I have to map it back to your level. Yeah. And as I said before, you have your source code, who typically runs through some preprocessor, which gets through compiler and object code. You link it with libraries when there's executable. There's an operating system, which sometimes run in a virtual machine. And on all these levels, something can happen. Yeah? And so I need to kind of, at first I can do measurements on all these different levels, and I somehow need to kind of put them all together to give you useful information. So how can we divide up this instrumentation? So the simple thing is, we can distinguish, is it a static instrumentation, which means I take my program, I instrument it somehow, but then I leave it as it is. I have an instrumented program, and when I run the program, do the measurement, the instrumentation doesn't change. This is called static. You can go further and say, hey, I start only measuring a few things, and I notice, like in this phase, it's bad. When I add at runtime more instrumentation or switch on more instrumentation to get more details. So the instrumentation changes during the thing to be adaptive, and it's called dynamic. That's one thing. The other one thing is, how do I do that? Is it basically done by the programmer, like manually? You write it, you have to open your editor and add extra code in it. Is it done by some special tool? There's a preprocessor or source-to-source tool. Basically, basically you feed your program in, and it spits out another program with instrumentation code, which you then compile. Or the compiler is actually doing it. Some compiler have options to insert code, measurement code for you. You can do it by linking against an instrumented library runtime system. Think about, you want to measure about MPI things. Instead of linking with an MPI library, you link with an MPI library which has measurement code in it, and by running it, you get automatic information about MPI. Or there's tools who can rewrite the instructions. Either basically you get the executable and you translate it into a modified executable, or you could even that on the processor, you load code and it modifies your code while you're running. It sounds complicated, is complicated, and I always, the picture I have in my head is someone wants to make his car faster, and while he's running down the highway, there's a guy in front, and is it fast enough? And then change the motor or something. It's a little bit like that. Okay, so the typical debugging method that people are using, they put printfs in different places. This would be a manual, static, source code, instrumentation. Yeah, so basically. Okay. So source code instrumentation. You think, oh, it's not too complicated. I hack to live a little Python script or something who takes a C program and inserts at the right places the net measurement code. Okay, just to give you an idea. So like simple C function. Yeah, it declares a value and then it returns, as it calls to functions, multiply it and returns it. Okay, so I say, okay, I just insert measurement code basically at the first executable line and the last executable line. Of course, it will not work. Yeah? You start measuring, but when your program returns, you never get to the exit. I said, okay, then I move it before every return, but when you're not measuring anything because the stuff is happening actually here in the return. Yeah? So what you have to do is something like that. That you start with measurement. If I broke it, put it on my bill. I'm bad, sorry. You can ask my wife and my kids. I'm always breaking things or spill things. Okay. Yeah. Yeah, so backing into the problem. So you start the measurement. When you start a new scope, make a temporary variable of the same type what the function is returning. You do the calculation in the return. Then you measure back and returning that value. But it's just one situation. Now think about you have to write a Python script which can handle all these different kind of quirks in C. C++ even worse with templates and virtual functions and so on. So it's typically like we tried it. It's a lot of work. Don't do it. It's not worth it. So if you want to do something like that, I mean the compilers, like a GCC compiler or the LVM compiler infrastructure, they have to compile this code and understand the code. And they do that. And so there are ways to kind of, it's called plugins. You write special code, and when the compiler is translating your program, you load this plugin, and this plugin basically in the compiling process in the middle kind of says, okay, what you are currently putting together, I don't know how much compiler background you have, but there's an internal representation of a program called abstract syntax tree, and then you can basically work on this syntax tree to manipulate it. And this is basically how most tools do this instrumentation on the source code level. Yeah, then there's binary instrumentation. As I said, you can do it by, you take an executable and instead of rewriting the source code, you're rewriting the instructions, or you do it on the fly, as I just said. Yeah? The problem is here, if you do it on the fly and you do it on a parallel computer, you have to do the on-the-fly changes on every core, yeah, which is also, and synchronize it. It's an additional problem. There's also, if you want to do that, there is a library called dyninst. It's an open source project, also over 15 years old, by the University of Wisconsin in Maryland. And it supports basically Power Linux, like PowerPC code, x86, and ARM 64-bit. And it has like, it's a C++ library where you say, okay, find me all the points where whatever function call is happening, and then insert this and this. So and then it generates basically the new code. It's, if you want to do that, I don't know. It's probably just weird people like me who's writing performance tools are using this kind of stuff. Okay. The point which is I want to bring up, across is there's many different ways of instrumenting a program. And as many things in life, there's not a simple solution. Yeah? It depends on your problem and so on. So think about source code. If I do it on a source code, I don't care which computer I'm using. Is it a Fukaku, an ARM, or an Intel chip? Because it's in the source code, it's always like C or something. So it gets compiled, it's portable. I also, when I get the data from this measurement point, I know exactly how to get it back to the source code, because I said, okay, this was measured by this function here, so I know it was this line in my code. That's easy. And of course, if you have things like modules and higher things, which when compiled, the compiler compiles them away, the only way to capture that is basically on the source code level. So that's the good points. The bad thing is, I get a better idea, I want to change something, I need to change my source code again and recompile. For large programs, that can take an hour or two, or even longer. Yeah, so then of course it has to be the source code available. So I'm using the Intel MKL library, which they only distribute as binary. You cannot measure because you cannot insert source code in it. If people are doing that, unfortunately, they mix languages. So they say, I have Python calling C++, which uses some Fortran routines for very fast executions. You kind of have to insert in all the different languages. And as I said, with doing it for C++ and Fortran 90 with source code instrumentation is really bad. So is binary the solution? Binary is just the other way around. Yeah, so binary means, yeah, I don't have to recompile, I don't need to have the source code, mixed languages, no problem, but, yeah, I don't know, again, basically, like this instruction, to what source line does it occur? It's not portable because every computer has a different thing, so it's just the other way around. When you use this pre-instrumented library, say like an instrumented MPI library, it's very easy to use. You only relink with another library, but you only get information about that library, not about else. So what does that mean? Yeah, of course, you have to use all of them at once. Yeah. So depending on what your problem is, yeah. So like for MPI libraries, for I/O libraries, you typically use these pre-instrumented libraries. For the functions, you typically use some compiler instruction because the compiler finds all the functions, so it's instrumentation, and so on. You typically do some combination. Yeah, and when you asked me about, yeah, like why is your tool so complicated to use? Yeah, sorry, because the whole problem itself is so complex, and we do our best to make it easy to use, but the problem just is complicated. Okay, so a little bit about, because everyone is using MPI, most of it, or many people MPI or OpenMP. What about if I want to instrument MPI and OpenMP? So this is what Besa just said. So what we want to have in a parallel program is typically, we want to get something about the user code, and so typically the classes, the functions, sometimes also the most important loops. And then for parallel programming, the message passing, we want to get typically, like when our message is sent, when there are synchronizations, how much is sent. In OpenMP, the threading. Yeah? There's also accelerators. We will learn about the CUDA and so on. They also have, you can measure CUDA and AMD, ragam and so on. But this is a little bit too much for this introduction lecture, but it's techniques like that just for accelerators. Yeah, and so as I said, how to do the user functions. So fun thing is basically every compiler I know on the, available on the world has some compiler option to instrument functions. Sometimes they're just not documented, sometimes they don't tell you about it, or something you have to find out by reverse engineering, but all the compilers have them. And once you know how to do it, you basically give them a flag, and then they insert basically every function with a specific begin and end, and give you the name, and then you implement this function, and you can use it for measurement. So that's one thing. Or you use these GCC and LLVM plugins. And of course, what always works, you sit on your hand and put it in yourself. Okay. This is actually, inserting the functions is not that problem. The problem is actually, which function should I instrument? Because if I blindly instrument every function I have, you drown in data. And also, every measurement takes time. So think about, you sometimes have these little one-line helper functions. Yeah? And if you instrument them, basically, you have to get the timer, what process I'm on, and so it takes some time. So your single one-line function typically takes then 10 times longer. And these small functions often get called millions of times. And then suddenly your program runs 100 times slower, and you don't want that. So another problem I'm really sad that I couldn't solve this in my 30 years of working on that problem is I haven't found a good algorithm to automatically select the right functions automatically without the help of the user. because every program is simple. I mean, you can do simple things, ignore little one-line, inline functions and others, but there's typically always a few functions you don't think about it, but they are a problem. So it typically, you can instrument them very quickly, measure them, but then, and I will show you that in my hands-on, you kind of basically, after the first measurement, you have to kind of do a check. Yeah? Is the data good enough or not, and then fix the instrumentation before you do the real measurement. Okay, then MPI. This is one of the things where for tool people, this was really simple from the beginning, because it looked like the people who implemented or did the MPI standard together, they knew about the problem, and from the beginning in the 90s, in the standard, they had something in the standard which allows you to measure MPI all the time without a lot of issues. And the trick is very simple. Every function is available twice. Yeah? So you have a function MPI send. Yeah? So when there's an MPI send, but when the same function you can also call by the name p MPI send for profiling MPI send. And broadcast the same thing. So every function is just available twice. So what can you do now? Yeah? So I want to measure, basically, I want to count how often a message gets sent. Yeah? So what I do, I write my own MPI send. I write a function called MPI send, which does the counting. But then, of course, I have to call a function who actually then sends the message. I cannot call MPI send again because I would call myself. But I can call the original code by calling psend, the p MPI send. Yeah? And this way, basically for every function I want to measure, and we call it because you take the function and wrap it, yeah, like a burger, you wrap it, it's called a wrapper function. And then basically what you do is, so I have my measurement library, which contains all the functions I want to measure, yeah? And when I link my program first against the measurement library, and then with a real MPI library. And so now, if a program calls send, it calls my send, which does the measurement, and for sending the message calls pMPI send. And if it call broadcast, which I don't know, it just calls the original one. Yeah? So it's kind of simple. You just have to link in another library, and for every function I'm interested, I have to write a wrapper function. Kind of simple. Yeah, and this is kind of how it looks like. If you want to do it yourself, yeah, you write, basically you take this MPI send, this is copied out of a standard, basically how the function is called, yeah, and then you just call pMPI send with exactly the same parameters, yeah, and then, yeah, instrumentation means I want to count, so I make a global variable, like num send, I initialize it to 0, and every time this function is called, I add 1. Yeah? And at the end, when I'm basically getting the results, I write a wrapper for MPI finalize, who basically finds out what processor I'm on, and then just prints out this processor sends so and so many messages, and then does the normal finalize. And if I link that together with my program, yeah, at the end it prints out on the screen how many messages got sent by every processor. Yeah? And so the only thing you have to do now, if you are interested in, you have to write these wrappers for all functions you are interested to measure. Only. The problem is MPI is old, yeah, and we're still working on it. So the latest standard, the MPI 4, which came out last year, has now 664 functions. So if I want to measure all the functions, I have to write 664 wrappers. No, because there's a C interface and a Fortran interface, so I have to write 1,328 functions to measure all Fortran and C functions. But it can be automated and so on. And then there's a lot of things in MPI, but this is really for tool people, yeah, like there's communicators and data types and so on. There are functions of it, but it's hidden inside the MPI library. So So if I want to know about communicators, I have to capture all the functions who create communicators or use them and do my own little internal bookkeeping. yeah, so that I know what is the communicators and so on. But as I said, this is details you don't need to know about. Okay. Then OpenMP is also actually, I think, the first version was late 90s. For a long time, they thought, tools, we don't need tools. We told people, talk to them, we want to have a performance interface. No, it just slows down the program, we don't want that. Our people can write good OpenMP code without tools, and so on. So the tools community and performance people talked to them for a long time, and something like 10 years ago, they finally understood it might be a good idea to have a tools interface for OpenMP. So, and since the 2020, like 3 years ago, we finally have in OpenMP version 5, we have now an interface in the OpenMP standard for profiling and debugging. It's called OMPT, and basically it is that in the runtime system, you create a thread or you do a barrier, you can register callback functions at that point, and then I can implement these callback functions and do the measurement. But it's new, and not every compiler supports it yet, especially for when you want to use OpenMP on graphics cards, but it's now possible. Okay. So now, almost done. So that was instrumentation, and now basically we have instrumented our program, and we want to collect data, and you can do this in different ways. And there's basically two main ways, and these I want to explain next. So first, a little bit more about measurement. As I said, what the typical things we count are counts, duration, communication costs, I/O accesses, system calls, hardware events, and so on. With a duration, you also think, oh yeah, this function takes from here to here, takes so long. Simple. Yeah. Again, devil is in the detail. So in a typical function, you can call other functions. Yeah? So if you measure the time from the beginning to the end of a function, everything is called the inclusive duration. Yeah? It basically says this is basically that function and everything called from it, this is how long it took. But sometimes you're interested only what is actually happening in that function without the function calling it. Yeah, because when you want to say you look basically how much time a function is using, which one should I optimize? You want to actually optimize or look into functions with which spend the most time on their own function, because what called in it you cannot change. Yeah, so and this is called exclusive duration. So you typically measure exclusive duration to find out basically what functions you want to look out for. To instrument or to optimize. And so most tools gives you both, inclusive and exclusive. Okay, again, when we do measurement, there's two dimensions. And one dimension is, when do I do a measurement? And the other dimension is, when I make a measurement, what I do with the data. Okay, so the first one is, when do I do a measurement? The first one I told you already about, by instrumentation. Yeah, basically every time I put something in the source code, either by the compiler or by manual or it's in the library, it triggers. Yeah, so basically it's somewhere at important points in your program. But it means I have to have an instrumented program. Yeah? Another way of doing it is I don't do instrumentation. I just use the program as it is. And then basically I let it run. And then at a fixed interval, I say every 10 milliseconds, I'm interrupting the program. The operating system stops it and looks where I am. When you let it run again, 10 milliseconds again, it stops again, where it is. Yeah? And so it's a statistical method. Basically, it means if in 10% of the times you interrupted the program, it was in function ABC, it means 10% of the runtime was in function ABC. Yeah? So the nice thing about the sampling is it doesn't require instrumentation. You don't have to recompile, but you only get the statistical information. That's the thing. And then basically once you interrupt, either by the sampling from outside or by calling that function from inside, what do? One thing is you sum things up. This is called a profile. Yeah, so basically you say, okay, that functions get called, so basically you make a table for every function, and every time a functions get called, you increment it, and you measure the time, how long it took to run that function. And then at the end you say, okay, every function, this was called 10,500 times, and in total it took 1 hour 50 seconds. The next function got called 2 million times, and so on. So you get basically just a summary table. This is called a profile. The other one is called a trace file. It's like writing a protocol. Every time something happens, you write it down. And you get this very long list about all these things. But it gives you all the information, yeah? Because it's like, you can look, okay, at which time, which processor did what. Yeah? You have basically the full information, at least on the level of where you put the instrumentation. And now the different tools use a combination of these. Yeah? So about the profiling. So as I said, it's like summing up things or aggregated information. So typically the time, the count, how often, and hardware counters. Yeah? And you do that basically for every function, or you could do it for every call path. So the functions could be called in multiple places. And you basically sum it up for every place a function gets called with a call path profiling, or for every loop. And then you do it, of course, on every processor, on every thread, and so on. Yeah? And then you can also create statistical information. So the advantage is independent how long your program is running. It could run for weeks. The amount of data you get is always fixed. Yeah? It's the number of items like functions or calls I have, and the number of processors. By the number of metrics I'm measuring, and this is the number. And typically is good enough. The bad thing is, if your program behaves differently over time, yeah, in the beginning it works differently than in the end or something, then you don't see that because you just get the overall sum and the average. So you lose the information, but it's typically good enough to basically know roughly what's going on and where's the most time spent and so on. Now tracing, I just explained, yeah, basically every time there's something, either it's a sample interrupt or it's an important point of a program. So typically every function you enter and leave, you send or receive a message, you do a barrier, you do an I/O call, all these things, you basically write it down. Yeah, and you write down when did it happen, where did it happen, which processor, which rank, what happened, and depending on what happened, you get additional information. Yeah, like if it was send a message, you record, or it was called this communicator, so and so many bytes to that processor. Yeah, a function, you say which functions get recorded. And so this is called an event record, and when you save that, and you order it by the execution time, and it's called an event trace. So it's the stream of event records sorted by time. It basically gives you an execution model on the level of these events. You know exactly what's going on. So this is amazing, yeah, because when you get such a trace, yeah, you can reconstruct what was going on all the time, even in backward. It's like a video recording. Yeah, you can, in minute 8, this person in the back, he pulled basically on his nose or something. I can quickly see it, yeah, or things like that. And it's the same here. You'll get your recording just on a text level, and you know exactly what processor was doing all the time. The fun thing is, because I have all the information, I still, basically after that I have a trace, I can go through the trace and calculate a profile out of it. Because I have all the information. I don't have to rerun the program. So if I do a tracing, I get a trace, but also I can calculate the profile. So I get everything I want. So why not everyone using tracing? Very simple. Yeah, these protocols get large, huge, gigantically huge. Yeah. Don't ask my system administrators how often we killed our file system because we were not careful instrumenting the program and generating traces. Yeah, so terabytes. Yeah, you can. It gets horrible. So it works typically, say, for you run your program for a few iterations. You cannot basically do the whole program run. So 10 minutes, 15 minutes, and yeah, because you do, every processor basically multiplies it. So this is, it's hard, unfortunately. Yeah, so how does that work? You got already basic idea. So you have a program here, function foo is executing on one process, and it sends a message to another piece of a program running on a process B, where it executes the bar function. There's the receive function is called. And then you do the, as I said, the instrumentation. Yeah, so you have some specific instrumentation library which marks the begin and end of functions, the sending and receiving of messages. And when this gets executed, yeah, there's a measurement library we call a monitor. It takes the wall clock time and it writes down basically a file, a trace file on every processor. Yeah, you want to do it separately. You don't want to mix it or something. Yeah? So on the process A, you get these measurements, say like on time 58, I entered a function, and you don't want to basically write the long name, so you make kind of like a simple table. And you make a file table and a communicate table. So you get kind of a trace and this meta information. And then on the other processor, you do the same thing. And if you have more processors, yeah, you get more of them. But at the end, you want to basically look at the whole program. So first, you have to get your global symbol table. Because here you just say the first function execute is foo is number 1, and then 2. But here, the first function execute is bar, so bar gets number 1. Yeah, so you need basically, and we call that unification. So you take the simple tables at the end and merge them together to give a global numbering. And then you take all the trace files and you merge them together. It's called merging. You sort them by time, and then you kind of rewrite the numbers for the global table. Yeah? But basically, this is the output and how this tracing is kind of working. So, of course, you can imagine, I mean, these are huge files. You don't want to read them. Yeah, looking at them is boring, and finding problems in there. So people said, okay, if you don't want to read them, you make a picture out of it. And how does that work? It's called a timeline visualization. Very simple. Yeah, you have a diagram. The time goes from left to right, and then you basically make a line for every processor. Yeah, and then basically you use color to indicate what's currently going on that processor. So you give every function a color. Yeah, and so now we look at the trace. Yeah, so we said, okay, of course everything is running main. Yeah, so we make everything, we make 2 yellow lines. Now we know on process A, at 58, it entered 1, which is foo, to 64. So from 58 to 64, it was foo, and foo is red, so we make that red. Clear? Yeah, I think, yeah. And the same thing then for bar, executing from 60 to 69 on B, we make that section, we make blue. Yeah? And then when a message was sent, yeah, from A at 62 and it arrived in B at 68, we make an arrow, and then basically like that. Yeah? And then you basically look at it and you see exactly, oh, like, yeah, if is everything basically the same colors, it indicates that every processor is doing the same stuff at the same time. If it's kind of very twisted, if something is probably bad and synchronization is bad and so on. And if there's many black lines, you have too many communication. But you can imagine, I mean, it works fine for like a node or 2 or few, but once it gets larger, it gets a bit out of hand. But especially when you start learning and you want to understand how things are working, like on graphics cards, you know, you say, I run that kernel and I load it onto the graphics card. You see now the kernel is executing, now I'm waiting. You see the nice display, and it helps you understanding this dynamic execution. Yeah, and so I said that already kind of. So a trace is the gold standard. It gives you the temporal, like the timing, and also the distribution over space, the spatial relationship between all these things happening. Yeah, and it allows you to reconstruct the dynamic behavior. Yeah, and you can detect time-dependent behavior, bogusly balanced code. I'll explain what in a minute. And it gives you kind of a lot of insight, especially if communication and synchronization is not working out, where it could come from. Because you can follow the arrows backward and see basically where could be the source of it. Yeah? Yeah, and this is basically, yeah, you could have something like that. Yeah, you basically, you execute something in green and then you do a barrier. Yeah? So it takes a while to synchronize the processors. But at different points, different processors don't work on the green portion. So if I sum that up, yeah, like this processor used 1, 2, 3 green units, this one also 1, 2, 3 units. They all used 3 green units. So when you see the profile, I said, oh yeah, everyone took 3 units, perfectly balanced. It could be, but it could be, it depends, yeah, like something it's canceling out. Yeah, or you see something like that, where basically at some point something develops and it gets out of hand. Again, you see that in the profile, that this takes longer, but you only get the average. Yeah, and you see that it's an imbalance, but you don't get information that it developed, it got worse over time. But most of the time, profile gives you at least a first hint what's going wrong, and then you use profile to go deeper. Yeah, and this I said already also, just written down, yeah, like, don't kill the file system. The sysadmins get really bad at you if you kill the file systems. And then also, making this tracing work also requires that when you make the time measurement on the different processors, the clocks have to be synchronized. So if the clocks on the different processors are running their own, you don't know, like, oh, did it really was later or before? So you need clock synchronization and a lot of stuff. You also need to store all this information before you can write it out at the end, which requires extra memory. Sometimes you don't have all that memory. And as I said, so you have to be really careful about what you are tracing and for how long. Yeah? And so basically the rule of thumb is you only use tracing if you can't find the problem otherwise. Yeah? Try profiling first, simple things. And then the profile gives you some information, where is the problem? Yeah, so now, okay, I don't spend a lot of time in MPI, but a lot of time in OpenMP synchronization, so I only trace the OpenMP stuff and ignore the MPI and things like that. And this is as I said, the idea is typically simple. Yeah, instrument the program, the data, I look at the data, but the problem is, and it's even hard to write down and give you good rules, this is how you should do it. It's just, you have to play around with it and get experience with it. It's basically like the accuracy and the granularity, basically how often do I measure something and how to which detail and how accurate it is. And depending, I have to find the balance that I get all the information I need to find my problem, but not more, because every time I insert something in my program, it alters the behavior. Yeah, it's like every physical experiment. If I'm probing it, it influences the experiment. Yeah? And so you said, oh, there's a problem, but actually it's just a problem because you used a bad tool or something. So you have to find the right way, is basically that you get enough information without disturbing the program too much. So basically, you cannot make a measurement without, we call it overhead. So you run your program and it takes longer because you do this extra measurement. So how much more measurement is good? I don't know. Yeah, the rule of thumb typically says, like if it's 5, sometimes 10%, it should be good enough that you get the basic picture. Yeah, but in some really weird cases, this 5% could already trigger some bad thing and you don't see it anymore. Yeah. Some people get really religious about it. They say every tool which uses more than 1 or 2% overhead is useless. This is wrong. Yeah? Because you don't want to use the tool to find 100% exactly know what your program is doing. You use the tool to find out what's wrong or what's bad. So even if the code is like 10 or sometimes 50% faster, if a tool still points you to the right place where something is wrong, you can fix it, it's still helpful. Yeah? But as I said, where's the line? Yeah? And it requires some experience to say, okay, now, okay, it's like in the 20 to 30% range, it's give me some information, but I have to be careful. Yeah? So you have to get a feeling for me, is it me leading to the wrong direction and looking in the wrong place? But use perhaps different tools if they both find the same problem in the same place, things like that. So again, basically as a summary, yeah, in instrumentation techniques, measurement techniques, whatever, there's not a single like go there and use this tool. Yeah, of course I would love if you use my tools we implemented in my team, but there's situations where I say, no, other people, like other tools might be better, yeah? And it's the same thing, you do something in your garden and you can use a shovel, yeah, to make holes. You could also, with a like cut trees, something, if you like carefully hit the shovel in the right way or something. But, I mean, what you do at home is you have something like that, yeah? You have different tools for the different things, yeah? And so, unfortunately, yeah, I know basically you're already overwhelmed by, oh, HPC, big computers, I have to use all these different compilers and libraries, I have to write my program. And now there's this guy coming telling me all these complicated tools. Unfortunately, yes. Yeah? If you really care about being efficient, I mean, that's the whole point. You can ignore it, yeah, and say, oh, I don't care, like, as long as I get my program data. Yeah, but the sysadmins are typically not so happy about people like these, yeah, like using up too much time and energy. But, and there's even, you can even go further, yeah, so this is, say, like, this is your garden at home. But now you get the task, say, make a flower garden for your city. Then, of course, yeah, you get the big machines. Yeah? But typically, as a normal person, you don't know how to use this machine. So what you do, you get experts. Yeah? Who know how to run these tools, how to use them. And the same thing is, like just as a picture, yeah? You have a really complicated program to run on Fukaku at some point. It could even be, it's like multiple people of you working together on a program. So don't, I mean, it's an important program, yeah? Go to the operating team of Fukaku, say, help us, because they know how to do it. And it's the same thing. If it's a really large problem, complicated, don't be afraid to ask experts to help you. It's not a shame. Yeah? You cannot be able to know all of it. Yeah? Okay. Yeah, so it's a combination of all these to make it successful. Okay, so to finish up, so that's basically, so basically understand what is performance about, what techniques are used, what kind of things you can expect. If you're interested, tomorrow in the computer science track, I'm giving another presentation about all the different tools which are available, open source, and you can use to use them. And to get more information, or if you're on a different track, at the end you still could look at my slides. Actually, I have videos available from other talks I gave. You could watch these videos or something. So don't be afraid if you miss the talk tomorrow and you're still interested in it. Okay, some more high-level piece of advice when you basically say like yeah, I'm in this situation. I want to make my program efficient. What do you need to think about? So the tuning or like optimization of is really a combination of using the right algorithm and the right libraries. What a lot of people do, so they say, the professor tells you, okay, here's this program for that other student. Yeah, he implemented, but it's not fast enough. Make it faster. So you work on this algorithm and try to rearrange it and use the different blocking factors or whatever parameters to make it faster. But sometimes you really have to go a step back and say, hey, that whole algorithm is wrong. I rip it out and use a different algorithm. But this, of course, requires, again, experience. But typically, again, you just ask in your community, yeah, what are the typical algorithms are you using? Yeah? And which libraries do you use for doing this and this? Yeah? Instead of doing it on your own. Yeah, especially libraries. A lot of people write their own matrix multiply or FFT. Waste of time. There's libraries out there, yeah, who do that, and people put a lot of work in making it optimized for that platform. So the standard things like mathematical operations, where typically libraries out there already use them instead of implementing it in your own. Then, again, so this is basically doesn't mean change any, might be just using another library without changing your program. The same thing about compiler. The compiler have, unfortunately, a good compiler now has, the manual is something like 90 pages and it has 140 different options you can call to optimize this and that and that. Most of them are probably not useful for your program, but some are. So look at the documentation of your computing center you're using. They typically give advice for a typical program, use at least these 3 options, -03, -fast, something. Yeah? It helps you already, just by something changing some optimization flag, your program can run already 20 or 30% faster. Another thing you can do without changing one line in your program is, so you have a specific amount of data you want to run your simulation on. So how many MPI processors should I use, and how many OpenMP threads per MPI rank? Or if you have an MPI program, just how many MPI processors will you use, or how many threads? How many nodes, and so on. So like thinking about Fukaku, we're taking 2 nodes, each 48 processors. We could run two MPI processes with 48 threads each, or we could run 4 with 24 each, or 8 with 12 each, or sometimes a weird number. Yeah, you run it with 1 and 40 threads, and you don't use the last 40. It's all kind of things, and just try it out. And sometimes, depending on your algorithm and the computer, just using the right combination gives you quite some speed up. Yeah, and at some point you will notice, like, oh, we learned we can use in the small queue 386 cores or something, or nodes. But for this little hello world, probably more than 4 cores is, so you have to find the point, like think about the speed up and efficiency again. Where is it useful for your program? So you make some tests in the beginning, especially if you run that program multiple times, you find out once where it's working, and then just use this configuration. Yeah. If it's still not fast enough, then you can think about, okay, how can I make it faster to use more cores, or so on. But if you are happy, I mean, in the end, what you have, the result you need for your work, this is the important stuff. Yeah? And if you get it in time, be happy and do your research. Yeah, I mean, we computer people. Yeah, we like to tweak around and optimize and tweak and something. It's like these car nerds. Yeah, we're like, I'll add another bigger motor, and I have, you know what I mean. Yeah, and every Saturday we tweak around on the car, and it's never really working. But don't do that. Yeah, like do as much as you need to use the program efficiently, and you are happy with it, and then just be done. Yeah, and if there's a problem, try to use some of the things I told you, or come to a team like my team or something and ask for help for optimization. Yeah. So basically, it's a lot of thinking. Yeah, nothing is really automatic. So it requires asking the right people, reading the right documentation, and just be careful. The next thing I want to tell you is measurement is always better than reasoning. Yeah. So when you think, oh, let's fix that, it will be better. Yeah. Or I optimize that now. Now the problem is gone away. Yeah. Every time do a measurement. Yeah. If you have solid data, and it could come out you were right, fine. But when you have data to prove it, yeah. So, but it's most cases, and the worst thing is you ask some experts, like, oh yeah, it's that problem. Never believe them. Make a measurement, yeah, and because the tools are typically more reliable than some wild guesses of people who don't know your code. Yeah. And I said, when you do this, after each step, redo the measurement that it doesn't get worse for your optimization. Another important thing is, yeah, it's easier to optimize a slow program than to debug a fast, incorrect one. Yeah, or said differently, yeah, nobody really cares how fast you can produce the wrong answer. Yeah, the important thing is, yeah, make sure your program is calculating what you want. Try to put some code in it which kind of makes sure. It depends on your mathematical algorithms used. There's typically some, I don't know, I'm not a mathematician, yeah, whatever, calculate some eigenvalues or something like this mathematical stuff to see, oh yeah, it makes sense, yeah? Okay, and once it's working, and only then, you measure, is it fast enough? If it's fast enough, be happy, done. And only then, basically, make it faster. Yeah, not from the beginning already start optimizing. It's fun, but I know it doesn't get you anywhere. Then there's these famous 80-20 rules, or sometimes called 90-10 rules, they are in all areas. And the 80-20 rule here is that a typical simulation program spends 80% of it, like most of the time, in a short portion of a program. You have all this initialization, blah, 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 and then you have this iteration loop who does it over and over and over, but this is just like a small portion of a program. But this takes most of the time. So, yeah, you need to optimize that portion. You can optimize that other stuff, but it doesn't matter. Yeah, you have to optimize the code which is used mostly. And with profiling tells you where is the most time spent, and this is where basically where you optimize it. The next thing is, so you make a measurement, you fix it. In the beginning, there's typically some stupid thing you did. So you change 2 lines of code, and suddenly it works much faster. Okay, you measure it again. Now it's more complicated. So you spend a few hours or days to fix it, and then you get another 5%. And so over time, you spend more and more time to get less and less output of it. Again, at some point, you have to stop, yeah? Because at some point, you only spend all your time optimizing and never get to your results. Yeah? So know when to stop. And it's kind of the same thing here. So don't optimize what doesn't matter. Yeah? It's like your car, you want to go faster, you can paint it or whatever, make arrows on it, it doesn't get faster. Yeah? You have to fix the motor, and the same is here. Okay, so what is the typical procedure? Yeah, what you do? So you have your correctly working program. You do a simple, just like, as I told you, MPI start, beginning at the end, yeah, and when you run it on multiple processors, basically, is it fast enough? Basically, do I get my answers as quickly as I need them? And does it reasonably scale, and how far does it get? Gives you a first number. It's 5-6 measurements just running the program. And it gives you an idea, do I have a performance problem? You are happy, it scales fast enough, done, forget the rest. Next is, okay, you're not happy. So then you find out where is the main bottleneck. So you do this profiling things, could be even sampling, where it just says how much time do I spend in different portions of a program. And you say, okay, oh, I spend a lot of time in MPI, so perhaps I need to look into communication. I spend a lot of time in the OpenMP runtime system. Oh, perhaps it's also barriers or thread creation or something, yeah? Or when it doesn't give you enough information, you do like more complicated, like call graph profiling or basic block profiling, which doesn't only show which function, but which this function called from here and so on, gives you more information. And then, if you still not have enough, then you could think, yeah, like, okay, I have memory problems, so you might want to look in hardware counters, in cache counters, or I have some communication problem in this region of a code, so you trace that region to see exactly, basically, how the communication is happening. Yeah? And then basically for a scalability problem, basically what you can do is, so I say it works fine with 8, but doesn't work with 16. You do your profile on 18, you do a profile on 16, and then you compare function by function. And some scale as expected, so it's like 8, 16 is twice as fast, and some are not. And then you basically know, oh, these functions don't scale, these are the problems where the scaling is coming from, so I need to fix these functions to make it scale. Okay, so that's all the advice I can give, at least. And I mean, I could, as you could probably guess, I could talk for hours on my love topic performance, but I need to stop here. So hopefully, with all the information I gave you, and then the tools, my thing is we can basically get in a situation like that. It's a little bit more relaxed working, and I'm happy to answer any more questions.
Thank you, Bern. Okay, you already got one question, two questions. Yeah, I'm sure no one is sleeping already.
Hello. Hi, so good afternoon, Doctor. I want to preface this by saying that from a computer engineering background, I really appreciate the explanations regarding the computer architecture of it all, right? But normally, right, when we are testing, like you said earlier, regardless of how good your hardware is, if the application is garbage, it will really not function well. So normally we would perform theoretical assessment of code to see the growth rate or the complexity. So my question is, earlier you mentioned that if I want to test my code on the hardware, maybe I could, running it in this instance would definitely be, or it would definitely return different results if I run it a second time, a third time, because there might be other people using the same hardware. So earlier you gave a very rough figure of you can test it 5 times, and then I can average that value. So my question is, those 5 times, right, the 5 tests, is that just a rule of thumb, or?
It's a very good question, and there's one person in France who wrote a whole paper about it, and he would tell you, no, 5 is not enough. and so he made like this, I'm a computer scientist, not a mathematical person, so he wrote all these formulas with all these Greek letters, and so he typically says it's more to get really be sure, like with some 95% interval or something, yeah, you have to run it, whatever, 70 or 60 times. Yeah. Okay. Yeah, but I think what we typically do is like 5 times. And when you see already, I mean, is it kind of close? Then it's fine. But if the 5 measurements show quite a variety, then of course, yeah, you try it, you say, okay, perhaps like it's a bad situation. I try it again next day or on the weekend, if I'm still getting it. Yeah, so when you, this is, yeah, like it's a multi-step process. But it's a very good question, yes.
Okay, thank you.
Yeah. You please give your name and
Hi, I'm Warawan from Thailand. Thank you very much. It was very actually entertaining performance evaluation I ever learned.
Many things.
Thank you. Well, I've been doing some benchmarking on HPC. For example, on quantum espresso, on MPass, on the GROMAX. My problem is, how do I calculate speed up? How do I get a serial time from the application that was designed for massively parallel computer already? I look back on my report, I'm not able to measure the sequential time. Do you have any suggestions?
Yeah, I partially said that, but of course, I mean, there's 2 kind of computer users, yeah, or HPC users. Some who develop their own application, and then they control the code, and then of course you can do the full thing. Yeah, I can rewrite my code and so on. And then there's probably more like in your situation, I'm using a package from somewhere else and I just want to use this package. And then of course you can only go so far. Is that like, look, did you compile it with the right flags on that system? Do I use the right split up between MPI and OpenMP threads? Sometimes these tools say I can use internally this algorithm or that one. So basically you have to play on a different level, but typically gives you still enough things to optimize. And then I would say, when you come to the point, says, okay, now basically anything I do, like independent of what MPI, OpenMP numbers I use, independent of, it always is bad, when there must be might be there's a problem with the code or the combination code of your system. And when I would try to contact the developers, whether I heard about, yeah, or can they give some advice how on this environment that could better. But it's, I mean, you can't only do so much on complicated code written by someone else.
Yeah, I think what you mean is you just measured parallel execution time and see if it's grow up or
and
down
and you
according
try
to
it with different parameter settings and so on and find the optimal one, which is good. Yeah, much more you can typically not do.
Is that okay if I first measure on one single node and then use that execution time as a reference when I scaled it up, and then I divided the execution time of the larger number of nodes with one single node? Say that it's a speed up.
I don't know, but you don't have to start with one. I would start with, I mean, you have to have, you're typically interested in a specific use case. I said, yeah, I want to do this and this calculation. Some quantum expressions with some molecular dynamics, or you have this molecule, I'm going to do that. And then it could be that because of the size of a molecule, you need at least so and so many nodes to start. Yeah, so it could be that you start with 4 or start with 8.
Yes,
Yeah, and then from there you work your way up. Can I like use less? No, it doesn't work. Can I use more? I get faster, yes. But so you have to find basically a starting point which is suitable for your use case, which can be, hopefully the documentation of the code tells you, you know, like if I want to use this thing, I should give you some hints basically, like where to start, you know, what would be a good starting point.
Okay, that's
Yeah, sure.
very much answered my question. Thank you very much.
Thank you, Warren. Any more questions?
Yeah.
If not, we can.
I'm around all week, so you can catch me in the break or something if you don't want to talk in front of a class or so. Yeah.
Bern, yeah, fascinating, very instructive lecture. I'm Fabrizio. Is that not an ideal case to start using AI and get AI doing all the performance tuning for us?
So performance of AI programs is an interesting topic. The problem from our diehard MPI, like the old HPC people is, our tools are optimized for C++, Fortran, MPI. Whatever. The precision is not the case, but these AI codes are typically Python frameworks. They use their own, because why use MPI? I mean, it was only used for 30 years and it's highly optimized. We invent our own AI communication library and so on, yeah? And so we would need to have, it's possible, but it would require a lot of work from our side to adapt basically like how to measure effectively Python programs, how to measure effectively their communication libraries and so on. To do that. People are looking into that, but to be honest, like in my case, I have more than enough to do on the normal simulation cases. But we tried it, but the problem is, so you get some high-level Python stuff, but when it's like big frameworks, and somewhere you get lost in there, and the typical users of these AI frameworks, they cannot change the code. They download TensorFlow from, I don't know, from which company or the others. And yeah, they have to use, they can do the same with the test here. They can try out, should I use 8 GPUs, 4 GPUs, how many nodes? But going beyond, it's really hard.
Okay,
but
thank you.
I hope that the AI people at some point get interested themselves to make it work, and they instrument the code or make it work or better tool friendly.
Probably next, after the break, we get something information from Mohammed Wahib, that he will introduce something about HPC for machine learning and AI.
Okay,
so,
good.
Thank you very much, Bren.
Okay.
And we'll see you in the next couple of days on Computer Science Track. And for all the participants, please have your coffee break, and we come back on 15:30 with introduction to machine learning and artificial intelligence in HPC from Muhammad Wahib. Sure. Either Rini Kurniasih and Siti Bahya. Rini Kurniasih and Siti Bahya. No. Kelupaan, sorry. Gak diingetin, udah diingetin tapi introduction to generative AI, one of the hype today, so you can get more information and dig more information from him. Please,
thank you very much. Thank you for inviting me here. My name is Wahib. I work in RIC in RCCS. My team works in what's called HPC, our high performance actually AI, which is at the intersection of AI and HPC. First, I have to, okay, I have just a little lag. So I have to, probably the question you have is why you should listen to the talk. And I have to explain ahead of time. Especially it's the last talk of the day. You had a long day. I'm sure you listened to a lot of talks and your brain is already fried. So one reason though you might want to listen to the talk is in the room there's a lot of fresh and junior scientists and engineers. Sorry if there's a typo there. I'm curious, how many of the school participants are computer scientists? If you can just raise your hand. So, minority. And the rest, I guess, are science and engineering, different disciplines. Okay, that's good. That's good to know. Well, that's good because this is adjusted for domain experts, scientists and engineers, not particularly computer scientists. And there's a lot of hype. I will explain the next slides, but nonetheless, it is important to notice that you might be noticing once in a lifetime event if you're a junior or a fresh scientist or engineer. Well, I wish I was young as you to use this opportunity. And that's because many, I would not say all of it, and maybe not fully, but maybe partially, many of the science and engineering disciplines or areas will probably be reshaped a lot in the next few years by AI and machine learning. So that's an interesting time to be starting your career, basically, because this opens a lot of opportunities for you. And I would probably say it's just like when computers were introduced and came to exist, and a lot of disciplines were reshaped by how computing comes into play. This might be not of a less of an impact. It's not clear yet, but it has the potential. So you might want to keep an eye on that, because this is a big wave, and you are positioned exactly in the right time and spot to ride that wave. And again, remember, when computers were introduced or existed, we had entire computational science fields bloomed after that, and they still do in what we call now HPC. Again, it might be an opportunity to reshape. I thought that instead of just having a talk that would give you information, I would focus more, not to give you, but try to motivate you to go and then look for information. For two reasons. Number one, no matter how much information I pack here, you probably will forget 90% by the time you leave the door, which is understandable in any talks, especially if you have a dense program like in this school. So I would rather, if I can motivate anyone, then later he or she can, on their own, or even ask, come here until Friday, ask more details and what to read, what to look on. This is the first reason. I chose to make it more about motivating rather than giving information. The other reason is topics of AI and generative AI and use of AI in science have tons of material out there. Full courses by universities, YouTube, lectures, talks, slides. And no matter what I do, probably I will not reach that level in just 1 hour and a half. So I would be glad to suggest some sources where you can just go later on and check out yourself. Okay. So first outline, even though the title is generative AI, but I actually have 2 slides only on generative AI, the last 2 slides. That's because I thought many in the audience here are not computer scientists and not mathematicians, so it would probably be better to start off from a little background. What's AI and machine learning? What does AI and HPC and AI mean? The challenges if you're a scientist or an engineer and want to introduce into your work, right? And finally, generative AI, just like a small teaser with 2 slides. And actually, there's another lecture in 2 days from now. Hopefully that time I can prepare something and we maybe take a deeper look in 2 days into generative AI. So with the first chapter, AI and machine learning. First, I have to clarify AI and machine learning is not magic, right? It's important to distinguish the hype from the real prospect, right? This is not specific to AI or machine learning. It's typical for new technologies. People get excited. There's a lot of hype, and then it's not clear what really this can do and cannot do. And after the hype cools down, the real potential comes. I found a really interesting analogy when I looked on. There was a nice, funny article, 2004, in RSNA journal, that says, it tried to track when X-ray was introduced. Like this is 1890 something, whatever, like about 130 years ago. People were so excited, oh, there's X-ray, right? So what can you do with X-ray? And here's what this journal kind of documented, the kind of, in popular culture and in newspapers at that time, which is equivalent to internet now, how is X-ray exposed, or how was it seen by the public? So they proposed all kind of soup, things like X-ray soup. People will go to the supermarket and not buy soup anymore, you buy X-ray soup. Why? You don't know, but it's X-ray. So it must be good, right? You can have also X-ray whiskey, right? If you need a hard liquor, X-ray whiskey, yes. And it's scientific, substantial, beneficial. So there's science behind it, right? This is not bogus. It's a real thing. And you have X-ray stove polish. You have a stove and you want to polish it, polisher, you get X-ray stove polish, right? And there was X-ray matches, right? You don't use any matches, you use X-ray matches. And people were buying that stuff, right? People were lining up. The article actually covers how much the sales increased because everything has X-ray on it. This is X-ray razor, if you're shaving. There's X-ray headache tablets. Oh, this is my favorite one, right? You have a headache, you go to the pharmacy, you don't just get the painkiller or a headache medication, you give you the X-ray tablets. And again, this is scientifically proven that it works and people will buy that, right? And again, X-ray exposure. So you go to a clinic, they expose you to an X-ray, like this guy, he has a headache, you walk out, you feel very good. Because X-ray, of course, has good benefits, takes away all the, headache and so on. I guess you can see the pattern here. So again, the hype is not related to a specific technology. When a new technology comes out, there's hype. So just be aware. But the news is, well, did X-ray die? Did not. It's very practical technology. It's used everywhere. So just that there was a wave of hype. After that went away, people started to understand what X-ray is. They started to distinguish how can it be useful and how not. So that's not different this time. So what is machine learning? Basically, it's a subfield in computer science. So in computer science, there's something called AI, artificial intelligence. A subset of it is called machine learning. It's a field that is interested in seeing how computers are able to learn without explicitly being programmed. So you want the machine to learn to do something, right? I like the word machine learning because it's very clear. Maybe artificial intelligence is not a very clear term. And if you look at the origins and roots of artificial intelligence as a word, it came at an era where people had ambitions, what these kind of new compute machines can do in the 50s and 40s and 60s. So artificial intelligence was a really overloaded term because we didn't even know what intelligence is. And even if you go and read the famous papers by Alan Turing himself, there were back then still arguments about what is intelligence, what is artificial intelligence, and what if a machine is intelligent or not. So this debate has been going on for 60 or 70 years and it's still going on. But that's why I like machine learning, which is a subset of AI, and the name is very clear. You want the machine to learn to do something. It doesn't imply anything about the machine understanding what to do. You just have a task, you want the machine to learn to do it, and that's it. So, machine can learn from something and make predictions on the data itself. That's basically at the high level what it is. There are types of learning. Broadly divide them into three categories. What's called supervised learning, then there's unsupervised, and there's reinforcement. Supervised learning means you have data you collected, samples, training samples, that are labeled, right? So for example, you have images, and each one has a label. This is a cat, this is a dog, this is a car. And you want to train some machine learning model from this labeled data set. After it sees enough example, the hope is that you show it a new image without a label, and then it can label it for you. Right? This is what's called supervised learning, and this is nowadays the most prominent. So all what you hear about from ChatGPT and all these applications are supervised. Okay? There's unsupervised, in which you do not tell the computer or you do not program a system with data with labels. Just give it the data itself, and you let it discover the patterns in unlabeled data. A famous example is clustering. Right? if you give it some data points in some space, whatever the dimensions is, and say, find for me classes or clusters, right? The way it happens that it just tries to like apply some algorithms. There are a lot of them, k-nearest neighbor or whatever. There's many of them. It just tries to automatically, in a way, without label data set, to try to figure out the pattern, right? Third one is called reinforcement learning, which is designed in a way that you have actions, and each action has a reward and a feedback. And famously, when you think about games, an alpha family, if you heard the news, AlphaGo, and so on, this is what reinforcement learning is. If you can define your problem, and this is the hard part, in a way that there's actions, clear actions, each action also has a reward, and you can measure that reward, then you let the computer go on its own, say, hey, go do these actions, and you will learn because there's a reward. You're learning to play chess, for example, or Go, or any computer game like Mario. You can take actions, right, with the pieces you have. It's a closed system, and I can assign a reward to each action, and then what I ask you to do, keep on playing. Takes a lot of time, of course, but on the way you're doing that, you're basically learning, right? So these are broadly the three types of machine learning that we see. There's other niche types or combinations, but those are, broadly speaking, the three types. When you say machine learning, you expect to see. Machine learning versus deep learning, probably you heard about that. So as we said, in computer science, there is artificial intelligence, which includes a lot of things. One of the, a subset of AI is machine learning. Another subset of machine learning is called deep learning, where machine learning basically, when you go to the realm of deep learning and so on, it just becomes about optimizing weights to make a prediction. So as you've seen in the previous slide, in the end, if you're going with something like supervised learning, I show you a lot of samples and I want you to predict, okay? Or even the two other types of machine learning. The question becomes, how do I predict? What it really boils down in the end, what it really at the very high level it is, you have some function, right? And it's curve fitting. You have weights or you have parameters that define a function and you want to fit the curve. As probably high school, I would not say even university, you learn what regression is. When you have some points, you just put a line that fits in it, linear regression. This is actually machine learning, right? You have some points, you fit a line, right? Then when you have a new point, then you can predict, does it fall on this or not, right? So more or less, it's about how do I fit the shape of this line such that it fits the data as good as possible. That's it. No more, no less. You'd ask, but what is this function I'm trying to fit? It's called the loss function. What is the loss? The loss means if I have a labeled data set, I would take the labeled data set, and while I'm training a model, each time it's predicting, I said it, check the ground truth label. If you're wrong, then you should update your weights because you're predicting in a wrong way. If you're predicting correctly, don't change anything. And the hope is that after you see a lot of data, you keep on adjusting the weights and parameters, right? Until you have a model that when it sees a new type of sample, now it can predict correctly, right? And what is deep learning? To go to a more specific way, it's a learning representation, okay? So it says, I will have a deep learning, a machine learning model basically. What it does is, it has some input, some signal, some function, whatever it is, right? I push features into some model here, and this I will explain a little bit later, and it gives me some output. In this simple example on the screen, it's a car. It describes the features of the car somehow, right? And then the model in this case is trying to do classification. It tells you, is it a car or not a car, right? But this is just high-level machine learning in which you have to, this is what was done before deep learning for a long time, that you have a human expert extracting those features. And why did it stagnate? It stagnated because for each new type of problem, you need human experts that learn how to extract features to describe a specific problem. For example, you want a machine learning model to train it to play chess. And there was a big push for that in the 90s, and systems from IBM were called Deep Blue, I think, something like that. A family of supercomputers at that point, they were just dedicated to playing chess. That's because the people who programmed it, they programmed it in a way to understand how to play chess. Can this be useful to play another game? Go, for example? No, because it's a totally different game, totally different strategy. But with deep learning, you don't need that anymore because you're not feeding features to a model, you're feeding your input directly. That means it's versatile. It can be adapted to different things. And this is actually the real strength of it. And the fact that the more data you give it, and I'll explain in the next few slides, the more better it gets, right? And this is called model-based machine learning. There's symbolic machine learning, you know, expert systems, and they were used a lot in the 80s and 90s, in which you're trying to describe a machine learning problem using an expert. An expert here doesn't mean a human, it's like expert system. Like you program the logic of what the task you want such that your machine learning model can solve it or predict, right? Versus model-based. Model-based means you just feed it data and you just rely on the hope that from seeing all these data, a lot of it, right, it eventually learns, right? It sounds a little bit weird that it would work, but it actually works. And the fun part is this was invented in 1980s, basically, right? This is nothing new. Like we knew these models from 1980s. You would ask, but, and it went through the winter of what they call winter of AI, where, you know, funding and interest in AI died out 80s and 90s, in early 2000s. And it resurfaced when people simply had the way to collect a lot of data, right? Because now you have internet, for instance. You can accumulate a lot of images, a lot of text, and so on. You weren't able to do that in the 80s or 90s, like in a digital form, right? Plus, if you have a lot of data, you need a lot of compute, which is HPC. As explained today by many of the speakers, you had Moore's law, which means back in the 80s, you were orders of magnitude slower in compute, right? You get exponentially faster, right? But that means also if you go back in history, you're exponentially slower. That means you didn't have data, you didn't have compute. So this thing was not useful, right? It was just for toy applications, basically, nothing practical. But now that you have a lot of compute power, a lot of data, it is very effective, right? You don't need all this expert stuff for extracting features. You just feed it that and it works. Then why is it useful, right? Because when you have manually designed systems like this one, here basically, the one on top, right? Where you have an expert extracting the features, sometimes you over-specify the features, or you have it incomplete, or it's hard for you to define, right? And it takes a long time. But then deep learning is more flexible and universal. Like I said, it can work with any task, right? Because you just take the job of finding those features and make a system do it. And it's end-to-end. That's what makes it easy and to understand. Plus, there's something called the universality theorem, which people have shown. And it shows that if you have any continuous function, right, if you even have, well, they call it deep learning, by the way, maybe I forgot to mention, because it has those layers. It's called deep. If you have just one of them, it's not deep. The deep comes from that. It's not deep because you were thinking deeply or something. No, it's literally because this is many layers in a neural network. And I explain that in the next few slides in more detail, right? Something called the universality theorem, which is important. It says, if given enough hidden, what they call, these are called hidden layers, hidden because you don't see them. This is where the input comes from. This is the output. So those are exposed to you as a user. You feed input to first layer, and you take the output from the last layer. The output could be a classifier, it could be a predictor, it could be a generative AI generating stuff for you. The layers in between, you don't see them, right? So, but this theorem says, if you have a continuous function, it can be realized no matter what the function is. You can map anything to anything. No matter what the dimension of the input is, no matter what dimension of the output is. In theory, that of course in theory, not in practice. In theory, no matter what the function is, you can map it to something else, right? Which is amazing. And I'll explain what this means in the next few slides. And this is the real power of deep neural networks, right? How does it look like, by the way? I mean, the universality theorem didn't really answer that. It might be shallow, so you have fewer layers, but, you know, wider, or it might be deep, and, you know, you have narrower ones, right? People explored a lot with them. And early on, people increased the number of layers. So for instance, what we know that GPT-4 used to train ChatGPT used by OpenAI is like 100 layers or so. Okay, so, but this started way from 1, 2 layers, MLP and so on, and they went up. And this is purely empirical, unfortunately, because the universality theorem just tells you, you will find the mapper, a universal mapper, no matter what the input and output is, but it doesn't tell you exactly how it should look like. And this is the unfortunate part. This is what they call black box optimization. So it's entirely empirical. People just try everything, whatever works, they stick with it, right? I know for those who have a strong appreciation of the rigor and understanding in math and science and engineering would not appreciate this, but here we are, and this is how it works, right? A lot of it, again, is empirical to know what works and what doesn't work. Again, even if you have the same number of parameters, you don't know which one is better. So I'll give a clear example, right? So when I said universality theorem, where you can take any input and you give me any output, let's say the input in this case is a handwritten digit, right? Something like this. And I've made it pixelated so it's easy for you. So you can see this is the digit number 2, written in pixels, the orange pixels basically. What you want to do, you have a machine learning that tells you what is the value. So what is the input here? The input basically is this dimensions. Multiply this by this, and this is the dimensions of the input. What is the output? Just a digit, just a number, just a byte basically, right? So this is your input, which is again 16 by 16 pixels. So imagine you have an input that's a vector of 256 values representing something, right? The model doesn't even care what it represents. And that's the fun part of it. Again, you don't need to actively explain to it, oh, this is a digit, or even this is an image. It doesn't care about that. It doesn't see that. Your input for it is actually this 256. And by the way, this is not just here. When you use ChatGPT and you type a sentence, the model doesn't see your sentence at all. The model, when you type a sentence, a prompt, this text is taken, breaking down into what's called tokens. It's not even breaking down to words. Sometimes words are split in the middle. Those are replaced by vectors, and the model just sees a vector of numbers. Text doesn't appear at all. So when people say models understand, you should really just stop them and say, wait, the model doesn't see text at all. It doesn't know anything about a language. It just sees vectors of numbers, right? So, and that's a good part in it, that it's universally can take any input, give you any output. Just how you express it or how you encode it, this is what matters. And the input, you can say, okay, on the first layer of neurons, I will make parameters. So again, remember the example of linear regression. You had a line fitting some points. Okay, how many parameters do you need to describe the line? Not many, actually. I mean, probably if a line is like, straight line, it's A, B, AX plus B. Y equal AX plus B. So 2 parameters basically, right? That's it. A and B, right? But here, how many do you need? I don't know. As an input, because it's dictated by the input has, you decided to encode it. It's not necessarily the only way, but you decided to encode it as 256 values, each representing one value of a pixel. It's either 0 or 1. If it's empty, it's 0. If it has a color in it, it's 1. So you decided to choose 256, and you feed it to that. So you said, okay, at least primarily I need 256 parameters because that's my input. What happens next? Again, where the values you feed are ink or not ink. Then you have an output, right? And the output is confidence in digits. Okay, here the input, again, it's a universal mapper between functions. Here your input, you chose to define it, or your encoding is, let me feed this model each pixel. You choose to define a number as pixels. You can choose a different way, by the way, right? You can choose to define this. You can encode it as a different type of signal. It's up to you. But you just said, okay, the simplest way, because it's logic, this is written. I just divide it into pixels, ink or no ink, right? And by the way, this is one of the real use cases of neural networks in the 80s, when people were signing checks at banks. You're so young to know, but there was something called checks, right? You have a checkbook, you open it, you write, I'll give this person that value. You give it to him, he goes to a bank, and he can check it, he can take money. Nowadays, nobody does that, but that was one of the use cases. Anyway, your input is these pixels, ink or no ink. But what about the output? Well, you know how many numbers would you write? It's just 10, right? The digits from 1 to 9 plus 0, so you have 9 digits. So intuitively, if you want this output, you want to map, you would say, okay, then the output should be one of 10 values. 0, 1, 2, 3, 1 until 9. But it's not really exact. will not give you, I'm sure 100% it's this. It gives you probability distribution, basically. It gives you some probability distribution with the, it sums up to 1. So 0.5, 0.4, 0.2, 0.05, you add up, it's 1. So it's a probability distribution. And the highest confidence is the number with the highest value. And by the way, this is not just here. Again, I'll go back to ChatGPT because this is the experience you have. Same exactly as in ChatGPT, by the way. When you're typing a prompt, your text is not generated at once. It's generated word by word. You'll ask why? Well, because the designers of the model thought this is the best decoder, this is the best way to extract the output. If you extract long sentences, the quality degrades. How do they know? Try and error, a lot of testing. So they decide to give you word by word, right? And they don't just give you a word. Internally, it exactly does something like this. All possible words, and in English this is like 50,000, it's called the dictionary or the vocabulary. There's 50,000 words. So every time you get a new word, it's just giving, the model internally is giving the output, or the input is your text. The output is, okay, the probability of the best output to follow the next word or the next token to follow your text is 50,000 values, and each of them has a probability. They add up to 1, right? So it's exactly the same, again. And that's, again, what makes it very strong and versatile. That this exact thing that worked for, what, a number you wrote in an image, works for text extraction or text prediction, right? This is the strength of it, right? Anyway, so it gives you a confidence for each one of these, right? Like this. So higher probability here is 0.7, that's 2, right? Will you say, okay, is that good? I don't know. This is why they call it accuracy. And this is also the Achilles heel of these kind of machine learning things, is that you don't have assurances on correctness. And I will come with a lot of slides in the end towards that. If you're a scientist or an engineer and think, oh, this I think is fantastic. Well, it does a lot of prediction. A lot of my work, for example, is, let's say, inspecting samples I collect in the lab. But wait, there's no assurances on correctness. There's just a confidence. There's just some values being output based on how good you trained, how big, how long you trained, how many of samples did this model see, how good your sample is, how good your model is, sorry. It predicts something with a confidence score. Must it be correct? No, it's just predicting what it is. There's no assurances, which is very different if you're a scientist or an engineer and use an equation. For example, you use the wave equation or the heat equation to solve some, partial differential equation. You know it's correct because people who derived this equation had a proof for it. And people who wrote numerical methods to solve them had to validate and verify, right? Validate by making sure that the equation matches physical phenomena, and verify by making sure your code or your program matches your math. And there's even inaccuracies because, for example, if your phenomena is continuous, computers cannot express continuous numbers, floating point representations, so there's errors. Even then, people did a lot of studies to how to, narrow down these errors and control them and describe them. And they have subfields inside, math and computer science and HPC, like people working on numerical analysis, numerical stability, uncertainty, quantification, all of that stuff, which doesn't exist here. And I will come to this in fewer slides. Again, this is just a side note. So that's pretty much it. And if you do a lot of that, you show the model, hey, this is a digit, predict it. If it's correct, you say, you're good. If it's bad, you say, wait, you predicted it wrong, right? Then I will just adjust these parameters a little bit so that you make the value correct. And the more you go on doing that, the more it gets, your loss function decreases and the more accurate you get, right? And that's pretty much it. And here, this function or this deep learning model is basically a function that's mapping some input with some dimension, some output with some dimension. What is that? The model doesn't care. That's up to you to choose how to encode. The dimension is up to you how to choose how to encode. You can innovate on all types of encodings you want. And also, you can encode on all types of decoding. Decoding means whatever the model is doing inside, I want in the end something I can use. Just in this example, people tried everything before you, and they arrived at the fact that if I just take, again, a handwritten digit and treat it as pixels, and I treat the output as a number, it works fine. There can be other ways. And in a lot of applications, there are other different ways. And maybe this digs deep a little bit into what this looks like, basically. Inside this and these layers also. Each one of them is a parameter, right? Or in the name, the lingo of neural networks is called a neuron. Because they say it was inspired from how the brain works, has nothing to do with how the brain works, but you just took inspiration. So a lot of the naming conventions in this field is like based on like, you know, how the brain works, basically. So each neuron is basically, if you're a mathematician or you're even an engineer or scientist, it just looks easy, right? This is just, you know, a weight sum of some values. You have some inputs, right? You assign a weight for each one, and you just sum up. It's simple, right? For example, if I tell you, try to classify or try to figure out how different students will perform on basketball, you can say, okay, I will care about their height, I will care about their hand reach, I will care about their jump, how much you can jump from the floor, assign different weights. How do you assign them? It's up to you. And then add up those, it gives you a score, and this gives you a prediction of how well would this student perform, be a good basketball player, right? This is exactly the same. And this is what you're trying to find, basically, those weights. This is the input that comes from whatever input you have, and you're trying to find these weights, because you don't know which values to give, right? So it's a deep neural network. So usually the first layer, you call it the input layer. The last one, you call it the output. Again, you choose whatever encoding fits your problem so that your input can take whatever is meaningful for you as an encoder, and the output gives you whatever is valuable and whatever is valuable or whatever you can interpret as an output that you need. One might say, why do you need all these layers? Why not just, you know, slap input and output and you're well done? Well, because again, universality law, which said if you have a layer in the middle here, all these compound nonlinearity in each layer add up. So that way you can express and do curve fitting for a nonlinear function, right? Because you expect that this is search space. You're searching for the best set of parameters, right? And you expect this for the loss function to be a very tricky looking search space, right? So you need to be able to handle all the nonlinearity in this curve fitting. And that's why you need a lot of layers. How many of them? Again, like I mentioned earlier, a lot of studies have been done, but a lot of it is also empirical. People try different things until they found what worked, what doesn't work. And those are called hidden layers. This is the naming convention. An example is you have an input. You keep on moving the values on layers in a forward way, right? So you have your input, you multiply by weights. I will probably skip through that. But the slides are there and with animation, so feel free to use it, of course, later on. And I can also discuss offline. I'm here until Friday. The thing just I have to mention is that the output of each neuron, you don't just multiply the weights, add them, and move them directly. But you have what they call sigmoid function. It's some function that applies a nonlinear transformation. And why is that? Again, because you want to express nonlinear relations in your model. It doesn't necessarily have to be a sigmoid function, but it usually is some representation. There's something called ReLU, GRELO. There's like tons of them people experimented with. But what people know that works is some form of sigmoid-like looking function or ReLU-like function, which is flat and then goes directly. What's important that it's differentiable. And I will mention later on why it should be differentiable. So at each neuron, you take an input from the previous layers, you accumulate what's going on, right? And then you pass it through a function that you give a value, and then you go to the next layer and next layer. So this is how you flow through it in a layer by layer fashion until it gives you the output. And you can, of course, represent this as matrices. Right? I mean, immediately looking at it, you can just say, okay, well, if I'm multiplying these values by the weights here, and multiplying these values by the weights here, why not just put it in a matrix? And then it becomes just matrices being multiplied together. And this is why, at the essence, deep neural networks are doing dense linear algebra, right? And that's why, from day one, HPC systems were a good fit, because they were designed in mind to handle dense linear algebra and other things, but that's mostly what's important. And that's why GPU, for example, specifically excelled, because GPUs are designed for vector operations and dense linear algebra. So if you can represent your problem as just matrix multiplications, that's perfect. And this is why GPU gained an advantage early on when this came out. I will skip through the values. This just goes to how to set up the parameters. You initialize, you start, and the input again is whatever encoding used for the, whatever the encoding used for the actual input, the actual signal you have, which happened here to be a 2D image represented as pixels, and the output happened to be a probability of the number being written inside this image. So training data, right? Remember, like what I said is what the model does, it takes an input, it just projects the output, but how do you train this model? Remember, we said there's supervised, unsupervised reinforcement. So let's stick to supervised because this is the most commonly used, right? Supervised means you prepare a data set. In this example, you would naturally think, what is a data set? Basically, it's a lot of these images, 16 pixels by 16 pixels, with digits written in them, right? And the quality of the data set matters a lot. And this is, again, something that reflects scientists and engineers looking forward to use machine learning, that data engineering is very important. In fact, there are people who just get an advantage in their careers and also like in the commercial space by just owning clean data of high value that's not exposed to everybody else, right? Because it's hard to get valuable clean data because remember the model is learning whatever you give it to it. If you give it garbage, it will learn garbage. If you give it too much error in the signal, it will learn things you don't want to learn, right? So you have to clean up. Famous example is, this was I think in UChicago a few years ago. They were using machine learning model to train on, I think they were handheld CT devices, right? They designed like handheld or small CT devices where people can take them and go to rural areas in some countries. And for example, use it. It's not big, so it's portable basically. Doesn't need a setup. It's cheap, so they would take images. And they had input images, right? From, when they prepared the data set to train, from CT scans, right, that are from high-end CT devices installed at big hospitals, and also input that comes from CT scans from these portable, low-quality, CT devices. They put all that together. They didn't clean up. That was years ago, actually. They trained the model, and then the model started doing something weird, right? That it started for samples that are collected from the high-end devices have more confidence than the other ones. What happened is they didn't do proper cleanup because when you see CT scans, sometimes there's some string value, added in the end at the bottom, right? When you even go to an X-ray, usually there's some value, patient name, date, case number, stuff like that. So proper data cleaning means you should remove that because remember, you're feeding that to you as a human, you don't look at that. You just look at the doctor looks at an X-ray, he just looks at an X-ray. This is just meta information. This is not the real signal. This is not what he's looking for. He's looking for the data in the image. This doesn't know. It just takes pixels, right? So what happens is it started to learn this and it started actually to distinguish devices based on the format and how the text is written below. And it realized that those samples coming from better CD devices were better generated images, so it started to learn. Whenever it sees this text, it just gives a high confidence score, even if it's not sure. Right? So you have to be sure about what you're feeding your model. This is the downside of it, right? I can also skip through that. So this is just a total cost, which says how much samples you're pushing, and for each one you're predicting, and you're telling the model, are you predicting correct or not? And based on that, this is actually the cost you need to train. And remember, imagine, like I said, in the end, how does a model update the weights? Right? Remember, we said in the edge there's parameters or weights that define a model on how well it's going to predict in the future. And all what you're doing when you're training is you're tuning these weights in an iterative way, step by step, until you get to a point where it does very well. I can show it new images it didn't see before, new samples it can predict, right? So what's happening now is, assuming you have only a simple model with 2 weights, so 2 basically neurons only, right? Weight 1 and weight 2, right? You're predicting the loss over these weights. And for that, they use gradient descent, right? Why? Because it's very effective. It works with dirty data. The data doesn't have to be clean. It can tolerate noise. This is a big area of research. People have looked into hundreds of optimizers. These are called optimizers, by the way. First order optimizer, second order, like gradient is first order. Second order optimizer, natural gradients, a lot of them. Like, it's just a huge research area, but the winner so far is more or less a variant of gradient descent, like SGD or static gradient descent. How does it work like? It just works like this. You assume some starting parameter, right? And the color represents the value. So this is the spot you want to reach. This is the value where for weight 1 and weight 2, you get the least amount of loss, which means you get the best prediction. So initially, maybe you initialize the weight value of 1 here, for example, and 2 here. But you want it to go there in an iterative process. The more it sees samples, the more smooth you want it to move towards this. How does it do? By gradient descent. Gradient descent is like hill climbing for the first order derivative. Right? It's like hill climbing. It's a very simple, intuitive way. If I'm standing on a hill and I want to go to the lowest part, I take steps. At each step, I look around me. Which one is the one that's going down more than others? If the slope is up in this direction and down in this direction, you just say, okay, go 1 step down. Again, go 1 step down. You keep on each step looking which is the area you should go down, step down, until you reach a point where you stop. It's a very intuitive and simple way. So if you started here initially, right, you don't know. Initially, you cannot know what is the best combination of weight 1 and weight 2 to predict for this model. Again, this is just 2 weights. Just to give you an idea, GPT-4 is 1.7 trillion parameters. So you're doing gradient descent in a space. This is just 2, right? This is easy to see, visualize. You know, you have 2 parameters, so you can visualize. Imagine that was 1.7 trillion parameters, which is an insane number, of course, right? Right? This is the size. And you would say, why? I'll explain the next few slides later on. Why do you really have to need all these parameters? So anyway, what happens here in gradient descent is you compute the gradient. Again, you move. And then you compute again. Each time you see a new sample or some samples, you move. You keep on moving like that, right? Next point, to the next point, to the next point, to the next point, until you land in a minima, right? It's not necessarily the minimum point, because if the curve, if the space or the surface of this space is going up and down, there are many minimas, but you're not sure, you don't guarantee to get to the very absolute minimum. You can get stuck in the local minima, but sometimes this is enough. Like, it can be like this, right? So gradient descent never guarantee a global minimum, because it's a very, how'd say, it's a very simple algorithm. Just looks around it, takes a step. Looks around it, takes a step. If I'm in a hilly plateau outside the city in Jakarta, I'm standing somewhere, tell me get to the lowest point, but I cannot see far away, I cannot do anything. All I can see is just around me, and take 1 step at a time. I will end up somewhere in a valley, yes, but am I sure this is the lowest valley among all valleys? No way. But is it good enough? Sometimes it is. So sometimes you can get stuck, as in this example, right? Local minima, you stand here, you look around you on both sides, well, both sides are going up. And that's it. I should not move again, right? Sometimes
recording
you get stuck what they call
stopped.
saddle point, like it goes like this, right? Each one of those are mathematically described, like saddle point, local minima, and so on. Or you can slow in a very plateau. It gets a little bit flat, right? And again, tons of research, and researchers like just spending decades of their lives on how best to find which optimizer that works best, that avoids these plateaus or adds some randomness or something like that. I can skip this. Again, a network can have, maybe this is an old slide, it's not millions anymore, it's not billions, it's actually, it's close to trillions now, right? So that's a lot of parameters, right? And you say, how do you train it? How do you do this process? Because for me, I gave you an example. I'm standing on a hill, looking around me, and then going like this. But how is this implemented in code? How do I really write a code for a model that does this? Something called back propagation. You move the samples through the model. You see how well it's predicted. You can know that because each sample has a label. You compare the label, the prediction to the real, or the prediction to the ground truth. If it's not, then you move back through the model. That's what's called back propagation. And at each parameter, you're changing the parameters again based on the gradient, as we've seen in the previous example. The good news is, as a scientist or engineer, you don't need to do all of that. There are specialists, people, computer scientists, people who work machine learning, who have frameworks to do that for you. And remember, that's why when I was telling you, no matter what the function is, it should be differentiable. It's exactly because of this. Because when you do back propagation, you're using the chain rule to back propagate, right? So you must be sure that you have a function that's differentiable. Otherwise, you cannot move in the back propagation through your layers. What about the size of training data? Well, this is where it gets a little bit hand-wavy, and it's not exact science anymore. But what we know is that the number of training example, there are some papers that are called scaling laws. They're not really laws. They're observations. But what they say is, roughly the number of training samples should be 5 to 10 numbers the weights of the model. That means when you scale the number of, because, okay, we know that these models work better the more data we have, the more clean data we have, right? Let's say you were able to collect a lot of data. But then you cannot maintain you could say, okay, I don't want to spend so much time, because as you have seen, when the model gets bigger, this is expressed as matrix multiplications. If the model gets bigger, then the compute is just so much. I would just have a small model. But no, people found out empirically that there's some correlation or some proportion you must maintain, or you want to maintain if you want good quality, between the number of parameters and data. That means if you want to increase the model size, you increase the data set size you train with, and vice versa. Vice versa, if the data is a lot, you increase the model size. And this is again what I was just describing in backpropagation. A famous example of this type of deep neural network is called convolutional neural networks, right? CNNs, probably heard about, which was the hot thing, right? People were doing 2017, 18 or so. Everybody was thinking, oh, yeah, convolutional neural networks, that's a future. People were even writing libraries, they were even designing networks, they were making new supercomputers, designed their networks and their storage system and their compute and everything just to handle convolutional neural networks. And this is a type of a deep neural network that uses, in the early layers, what they call convolution operator or convolution layer, to extract features from images. And it works particularly well for images. That's why it early on, it was used a lot in computer vision. For example, in classification, segmentation, and so on. But then another example is transformers. And transformers is what's used, is the architecture used in what known as large language models. Probably you heard about it. This is what's used in GPT, ChatGPT, a lot of applications. And it's based on a family of models called attention. And those power large language models, like generative pre-trained transformers. There are many other types and architectures you can see in deep neural networks. But more or less, I think you got the picture. You have input, input layer representing whatever encoding you have of whatever signal, output on the other side that makes sense for you. And then you have hidden layers. There are a variety of architectures and details of how we design them, right? But in the end, they are a universal approximator of some input signal, some output signal. If you're using a supervised method, then you have data set, it's labeled, it goes through the model, and you have a proper propagation method using gradient descent to train your model. So in the future, when it sees a new sample, it can do its work. It can classify, it can predict, basically. It can generate also stuff, which what they call it generative AI. So what's a transformer? In the simplest case, right, it takes a sequence of tokens. And I will explain what a sequence of token means. Remember in the very early case, when I said the example of the digit 2 written, we chose to make the input just the pixels. We showed, okay, this is an image made up of pixels. Just put the pixels one after the other, so multiply height by width. And if it's a colored image by channels, you have 3 channels, RGB or more channels if it's a scientific data set. And this is your input, right? And that worked in convolutional networks, actually. The input was exactly this. Take an image, multiply this by this, it gives you the pixels, and add the channels. You add also layers for channels, and that's the input that people have found naturally works in CNNs. In transformer, it's different. It takes what they call sequence of tokens. What is sequence of tokens? Okay, remember that these models were used in NLP, natural language processing. And if you have a hammer, everything is a nail. If you have an image and you're making a model for an image, you would intuitively think of pixels. This is how I present an image. If you have text, what would you intuitively think about? Words, right? That's it. Any language is just a sequence of words. That's what's called sequence. But they don't take words. You would say, why? I would simply, if I have a, English or Indonesian or Chinese or any language, if it's made up already from words, why think a lot on how to represent? Just break down the words. You have a sentence like this. Like it looks small outside, then each one is a token. Right? They call it a token. The fun part is, they realized, again, by experimenting, again, a lot of this is experimental or empirical, that this doesn't work the best. When you split the text in different positions, sometimes it's better. So you would have a sentence like this. It looks small, and for some reason, nobody knows. If you cut small, for example, in the middle, it becomes SM and ALL, right? It works better. So there's something called tokenizer or tokenization. You take as an input a text, you break it down. How? You don't have to concern yourself. There's a lot of algorithms, but two of them are most common ones. We just break it into words. What you care about in the end, that a transformer takes as an input a sequence of tokens. These tokens can represent text, as in one word to one token, or you can break it further. And the current state-of-the-art best practice is 3 to 4. So each 3 words break down to 4 tokens, right? Further, people even thought, well, why stop there? Use it for language. I want to use it for images. Back when I used the convolutional neural network, I decided to use it again. If you think in images, everything is a pixel, right? But they said, if I feed it each pixel as a token, that's too much pixels, right? Then let's split the image into patches like this. If you have an image, break it to blocks, 16 by 16. You would think, but why? Why 16 by 60? And wouldn't you, in this case, be cutting across objects in an image? So if an image has a cat, maybe when you're cutting these patches or blocks, you're cutting the image of the cat. You're giving the model a signal. As an engineer or scientist, you think it's distorted. It's weird. It's meaningless. It works. Again, people tried it. It works, right? They basically said, which is called vision transformer or VET. They just took an image, split it into like patches like this, and then they made a flat. They took each of the blocks, flattened it out. Again, the same trick, pixels by pixels. Feed it to a model, and it still learned. And it worked. And people can do classification in images. They can do segmentation. You can do whatever they did in convolutional neural networks. Is it better? Yeah, but people show that they match, go together, head by head. But transformers has an advantage is that it's called multimodal. Multimodal. What does multimodal mean? Now, if you use a convolutional neural network or the first, really impactful architecture that until 2007 or 17 or 18 was the winner, and everything, people just were rushing to do convolution for anything, right? If you transform and go to here, realize, hey, I was able to use it for both text and images. So it can ingest any type of that. That's what's called multimodal. And later on, people realized that not just ingest, it can even give you out any output. And even if you use ChatGPT, initially it was just giving it text, gives you text. Now in the latest iteration, you can give it an image with text and it generates something. Or you tell it, give me an image. So you have this model that maybe is not much better than CNNs, but it's multimodal. And again, what does it consume as input? Whatever you encode. It's up to you to encode it in the way you want, right? People give it a lot of things. They can give it text, then it's a sequence of words that you break it down. Images, you break down the images to patches. If it's videos, you break down videos to frames and then cut the frames. If it's audio, They can just break the audio signal, a 1D signal, or sometimes they take the 1D signal, transform it into an image, plot it as an image, and feed it as an image. Sounds very weird, I know. Because again, remember, this is a universal approximator. It doesn't care what it is. Whatever you give it, what ingest. In the end, if you have enough data, it would work. If you're a curious scientist or engineer, you might by now think, okay, I work in a field where I have a lot of data. This is basically great. If it can help me do prediction or generation of stuff or find correlations, which is basically most of the work in science and engineering anyway, to understand the phenomena, you have observations, meaning data, input, right? And you want to understand the world, you make a world model of this data to figure out something out. It exactly fits what you want. But then the trick is, how would you find the best way to represent your input and the best way to represent your output? Right? This is the main trick. And also, how do you get this data in a clean way? And then how also do you do the actual training? And I come to that in the next few slides. How am I on time, by the way? Half an hour remains. Yeah. Okay?
Recording
Just
in progress.
one caveat in transformers, and you will hear a lot about large language models of transformers. Why is it so expensive? You probably heard in the news, it took, ChatGPT, OpenAI, hundreds of millions of dollars to train models. Why? And why is it a rich man's club, basically, if you have big supercomputers and you were trained? Because simply, remember when I told you your input is a sequence? Without going into much details, you're basically brute forcing and finding correlations across each token to all other tokens. So if you give it an input, a sequence of inputs, right? N, like sequence length, the input, it's finding the relation between each one of those tokens and all other tokens. So you have a quadratic effect, right? Basically. So the compute and memory cost is proportional to the sequence squared, okay? And that means you have a lot of data, right? Because we know that these models work with a lot of data, and because we said there's something called scaling law, that the number of parameters in a model should be proportional to the size of data samples. So you have a lot of data, but you have a big model which takes a long time to train. And what's worse is that when you train it, the cost is quadratic. And that's why all this, all this money goes in. So for instance, if you have a book, like, I don't know, GPT-4 can handle 32,000 tokens. This is about the length of a small book. So you can give it and train it. It can do fine. Beyond that, it cannot. But we know if you're finding correlation among data, you want it to have a big view for the entire data in front of you. Of course, I wouldn't be exaggerating if I said hundreds of thousands probably, or tens of thousands, hundreds of thousands of researchers around the world are finding a way to make this faster. All kinds of tricks you can imagine. At the fundamental level of how you design the model and how you learn, at the optimizer, approximations, mathematical tricks like you sparsify, you approximate, all kinds of tricks you can think of. Nothing yet materialized. Some narrow cases where under some assumptions these can work, but in production it remains to be, unfortunately, that this is how it's done. I don't know how the future will look like, but I would imagine in 20, 30 years people will look back at us and say, this was so stupid, this was very inefficient. It's really inefficient. It's like the early days of internal combustion engines, when you had cars with efficiency less than 1%. So you put fuel in it, and less than 1% is used to, for mechanical movement. The rest is just dissipating from the engine or so. And even nowadays, it's in an efficient car, 30 to 50%, which is still not that high, but still orders of magnitude from where we started. My guess is in some time when people figure this out, they'll say, this was very inefficient. But just because there's driving forces from industry and commercial applications that people are pushing faster in these directions. And you would say, okay, why LLMs? Notice that I drifted a little bit into LLMs because they are, again, the state of the art. But again, have a general view that it's not necessary that LLMs what will be around in 5 years or 10 years. Just like convolutional neural networks, people thought everything will be convolution, but it did not. Just keep in mind, in the end, it's a system for nonlinear curve fitting for a loss function, for a data set that is labeled. That's it. And all the rest is just details, right? Architectures change, tricks to train change, scale changes, but it's the end, it's the same. But at least for LLMs as we have now, they have what they call emergent abilities. What does emergent abilities mean? People found out, as you increase the model size, the model can do new stuff, right? So the model, for example, can translate. But when you train it more, with more bigger data set and you increase the model size, now it can also, for example, understand context. Or it can, for example, reason. Or it can do planning. So the bigger the model, so far at least, that at least at this size of flops, you need for a model, right? You get emergent abilities. So it's understandable also why people are rushing to train bigger models, even if it's inefficient, because you get these emergent abilities. And then you have multimodal language models, which is another interesting feature. So the one interesting feature is that you have emergent abilities, which means we still have a runway. We didn't stagnate yet. People have more bigger models, and they still can make the models learn new stuff and do other stuff. The other feature, as I explained earlier, multimodal. The models can handle different things, right? They can handle nowadays text, audio, video, whatever signal it is, at the same time from the same model. So you can share the model trained between them, but you just maybe fine-tune on a different decoder, which is much easier than having individual models. That's why large language models are very attractive. So you would say, for instance, but how long, if you speak about HPC, how long does it take to train, right? So it's speculated that, again, this is leaks because it's not announced by OpenAI, that this is the number of flops you needed in the model, and you had about 20 trillion tokens, 20 trillion words basically, almost word. Let's say a token is a word. Maybe it's 3 to 4, but let's say one token, one word. This is the volume of text it was trained on. 20 trillion words, not just any words. They have to clean up. They have also to remove offensive content. They have to assure there's no replication. They have also to assure that none of the input is already generated by another model, because they found out that if you train on your same data, you degrade, right? So that's what was speculated. So that if you would want to take GPT-4 and train it on a system like Fugaku, it would take almost a year and then multiply by 3. Because Fugaku's efficiency at best is 30% of peak. Remember that I said these models are made of matrix multiplications, but there are other operations also that are memory bound, that are slow due to data movement. So at best you get 30%. So that means this is best case scenario, but in practice you need 3 times this time. So you need 3 years of the entire Fugaku system yourself to just train GPT-4, right? In the case of OpenAI, they use the GPUs that have lower precision, right? And tensor cores, matrix engines, like these are units on the GPUs that allow you to do matrix operations much faster. So it was, because it was designed for that. Remember, Fugaku was designed prior to 2020, before all this came into, existence. So it didn't have support for very low precision, didn't have matrix engines, right? So even in the best case, when you had dedicated GPUs, they needed 25,000 A100 GPUs for 3 months alone. And as you know, supercomputers are a shared commodity. Usually you have a system, it's shared by people. You cannot get a full system to yourself. It doesn't happen. At best, like big systems like Fugaku or Summit or Frontier or Lumi, once, twice a year, they invite researchers. You can get the full system for half a day. That's if you have groundbreaking, results. And usually you don't really generate some meaningful science. It's just to show how much you scale. So imagine having a supercomputer for yourself for 3 months just to run the model once. This is just to train it once. Remember, they had a lot of this is empirical. So it's a cycle of testing, changing the hyperparameters, tuning, running again, and then running again until you find something that works. So in reality, you multiply this by a factor, 5 or 6 or 10 or whatever it takes time is. To give you a clear feeling if you're a scientist or an engineer, this is the table I made to compare. This is one of the state-of-the-art applications that run in Fugaku. And actually, it made it all the way to a Gordon Bell finalist, which is a prestigious award for groundbreaking research at scales never achieved before. So this was a 3.5 mesh global weather simulation. So you take the entire Earth, you make a mesh around it, icosahedral or some type of mesh, right? You just make it a discretized domain, basically. And this discretized domain is at a resolution of 3.5 kilometers, which is unprecedented. This is why it was groundbreaking research. Because imagine the number of points if the Earth is divided into a mesh of a resolution of 3.5 kilometers, right? So the number of grid points in this mesh was 4.5 trillion. And it has data assimilation. Data assimilation means it didn't just simulate, it also, while simulating, it was ingesting real measurement data and using Kalman filters or whatever method to just correct its prediction as it goes, right? Without going into details, I compare this to GPT-4 from numbers we know. Just to give you an understanding, right? To run this simulation versus to train this model, training that model takes about 1,600 times the budget of resources to run this very, state-of-the-art climate weather model, and just tells you how much resources you need. What's even more funny, I just compared here per data point. So if it's a climate or weather simulation, what is a data point? It's a grid point. Right? If you have a mesh describing the entire Earth, just take one point, and I count how many additions and multiplications I need to do per each point in that discretized domain to get to the result, right? 90 megaflops, 90 million operations per point, which is amazing. Imagine how complex this simulation is if per each point you have to do 90 million additions and multiplications to get to a result in this simulation. And you're not even simulating for a long time, you're just simulating 9 hours. That's it. You're saying, I run a simulation that simulates the weather for 9 hours, right? But if for GPT-4, what is a data point? I think probably it's a token, right? Because if we agree that your input is a token, be it text or image or whatever, then per each token being fed. So every time you're using ChatGPT and you write, you have a report, you don't want to do it, and you say, write a report and blah, blah, blah. Each word you write is one token. Each one of them requires this amount of compute, right? If it's in the training you didn't do yourself. This is what OpenAI did before releasing the model. For them, it required 6 teraflops, right? 6 teraflops, right? A gigaflop is a billion, so 6 trillion additions and multiplications are done for every single word you enter in ChatGPT. That's in training. In inference, which is what you do actually, right, as a user, is actually this number, 2 trillion flops for every single word. And its next token prediction means it just predicts the text, and then if you keep on writing to it, it does it for every token, right? That's why it's expensive, so expensive. What happens that they're trying to subsidize to gain ground, of course, as a commercial space and so on. But if you're a scientist or a mathematician and you want to run this stuff on a supercomputer, it will cost a lot. And this is why all of HPC centers around the world are trying to struggle with this point, that if people rely more on these things in science and engineering, it will eat up any compute budget you have. So you either buy an individual system just done for that, which is expensive, or you realize, you come to the fact that most of the system will go into just using this. That's why I say in 10 or 20 years, people will look back in this era and think this is very inefficient. If for a climate simulation, for every data grid point, I need 27 more token per one word, just insanely inefficient. But here we are. Oh yeah, I actually had a slide that's hidden. But I will, yes, measure that. It's in connection to that. It's actually in the main slide deck, by the way. That currently, actually, because in Japan, we realize that there's no open source model trained on Japanese text. So we have a project called Fugaku GPT. And what we're doing now is we're trying to train a model that is GPT size, not GPT-4 even, GPT-3 size or 3.5, right, using Fugaku. And it's been taking months to tune the software stack, collect the data set. Some of it we collected, some of it we just got collaborators from Japan, like publishers, news publishers, newspaper publishers, literature, publishers, to give us more data, plus what we collected. And in the big picture, because many different supercomputing centers are realizing that these models, we don't just need them for text, we have scientific applications we care about, right? They want to train a model. So there's a consortium called TPC, Trillion Parameter Consortium, which was started and led by Aragon National Lab They have the system Aurora, and their target is that them and also other centers around the world, also in Europe, the main center, like, for example, Lumi, and also other systems coming online in BSc and ULIC and so on, with us and other teams which participate and train these models for science to be open source. So that's chapter 1. Remember, we have 4 chapters. So I will blow through the next in 10 minutes, basically. So far, this was a very crash course on machine learning and state of it. How does it relate to HPC, right? You might ask, right? This is an HPC school. So there's 2 ways to look into it. There's HPC and AI. Okay, as I will show in the next few slides, it takes so much time, like from the previous slides, even you've seen how much compute and time and cost it takes. So you want to apply best practices of HPC to make AI faster. And then there's the other way around, which probably concerns the audience here. How do I apply AI in HPC? If I have scientific applications, be it at small scale on my laptop or be it a simulation running on a supercomputer, how do I apply these machine learning methods? Because they can be useful in my model. So this is basically what AI and HPC are interacting with. Now, the issue of challenges of large-scale machine learning. So let's now, from the point of view of HPC, looking at machine learning as just a workload. We want to train models, just like we, for example, do climate simulations, molecular dynamics, CFD, etc. Well, we have something called neural networks, LLMs, and we want to train. It's a model, it's a code that runs. Okay, so basically at a very high level, HPC is a study of bottlenecks. That's it. HPC is about a bottleneck. Where do the bottlenecks come from? Anywhere. They can come inherently from your algorithm, right? Inherently from the problem you solve, sorry. Or from the algorithm you write to solve the problem, right? Or from the solver itself. They can come from the system software, the operating system, the runtime systems, the message passing library, the compiler can cause also bottlenecks. They can come from limitations of the hardware, right? Moving data, for instance, or the storage system where you're storing your files. But in the end, it's a study of bottlenecks. Thank you very much. It's a study of bottlenecks. Okay, so the question is, Fugaku can sustain 442 petaflops. That's a peak performance of Fugaku you can really measure. So that means if you want to scale machine learning, if you want to scale any application actually, but we're speaking about machine learning, to use the entire system, you need to find in your application this amount of additions and multiplications per second, right? That's 442 to the 10 to the 15. If you don't find them in your application, then you're not using the system fully. You're not efficient. Your parallel efficiency is not going to be great. You're not going to scale. You're going to use some portion of the system. Beyond that, you cannot. You just simply don't have enough work, enough parallel work in your application. So the question is, can you write even a program that has all this amount of additions and multiplications in parallel? Hint, yes you are. It's called multiplication. In fact, the way they benchmark supercomputers with something called high-performance LIMPAC is basically a general matrix multiplications. Because a multiplication has n to the order n to the power 3 operations, but n to the power 2 number of elements, right? But the question is, how do you do that for machine learning? How do you expose this parallelism, right? So again, HPC is finding the bottleneck. So this is a figure that shows a supercomputer in 2023. Those numbers reflect basically something between Frontier and Fugaku, right? And it shows that in current systems, like in different points of time, depending on the technology, it differs. But in current systems, moving data to the CPU, central processing unit, is actually what's a bottleneck, right? So if you look at this figure, if you have a CPU, it takes, let's say, more or less 1 nanosecond, sometimes less than that actually, to add 2 numbers, 2 floating point, and 2 real numbers, right? And it takes about 4 picojoules. If you're moving the data from memory, so when you write A equal B plus C are stored in the memory, and you get them from the memory, you spend 50 times more the time, the red color, to the time of actually adding or multiplying. Then you don't really care how fast your processor is. Nobody cares. If it's 1/50 of the time it takes to get the operands of the add operation, then you're just stuck there. And similarly, this gray color is the power. 80 times more the power to transfer. And it gets worse, right? If you have an accelerator, if you have a GPU on your system, which is a discrete accelerator connected, by PCI Express or NVLink or something like that, it's 5,000 times, right? So if you want to transfer data, if you want to go to the network, like state-of-the-art high-performance computing network, it's 1,000 times. If you want to go to storage, right, you're a person who works with a lot of files because you do an experiment, you're a scientist or an engineer, you're reading a lot of files. Or in this example, you want to train a deep neural network, but as we said, the data set is very big. You need to read it from storage. Then you take 30 times more to move this byte from here to here than it takes to actually compute. So in the finding the bottleneck game, data movement is a bottleneck, right? Thing is, in traditional HPC application, you usually have one bottleneck, or sometimes more, depending on how you problem. Even if you ask experienced people in HPCs, you would just out of their head, say, oh yeah, fluid dynamics, you're memory bound. Yeah? In body problems, you're compute bound, but also as you scale, you become network bound. Right? Graph or regular stuff, you're memory latency bound because you do random access, etc. But in machine learning, it's quite different because you scaled very fast, right? We scaled the size of models in 6 years, 1 million X, which is insane, right? Again, it's insane. If you take classical HPC applications, they actually map the Moore's law. If you take, for example, state-of-the-art weather or climate simulation resolution and map it, draw it over time, I guarantee you it will fit exactly on top of Moore's law. So basically, to go 1 million X, it would take decades, or I don't know. You do the math, maybe 20 years or 15 years. But for that, it's like 6 years, right? And the bottlenecks become so pronounced. Again, I told you before why all these parameters, right? There's a funny story in a paper by Freeman Dyson, famous physicist, right? Who said, von Neumann said, John von Neumann, that with 4 parameters I can fit an elephant, right? That he was speaking about that when you have parameters and you want to fit some curve or fit something in it, you don't need a lot of parameters yet. With 4, I can fit an elephant. With 5, I can wiggle its trunk. And actually, some people took him for that, right? Literally. And they went and wrote a paper on it. You can find the link in the end. They literally showed that he can plot an elephant with 4 parameters, and they can wiggle the trunk if you have an extra parameter. So people can do that. So you would say, if these parameters, these few parameters, can allow me to fit a very elaborate shape, why do I need all these 1-point-something trillion parameters, right? Because over-parameters, what they call them now is over-parameters models are effective, right? So the model is over-parameterized, right? You would say, probably in this big model, I don't need all of it. I can take a subset of the samples and reach exactly the same accuracy, which is correct. There's even a paper on it, famous paper called the lottery ticket hypothesis, which says in every dense model, there's a subset of it that if you take it out, train, it will give you the same quality. And they call this a lottery ticket because it's like winning a lottery. Now the issue is, how do you predict? Because to know what is the subset of the model that can replace the model, I basically have to predict the sparse connections, which means I have to go through the model entirely, which doesn't make sense, right? Then people just stick with over-parameterized models, right? Not because they're the only way, but because simply knowing subsets of models that can do the training is just too much. So we need a large model. Again, the scaling laws, that the model and data grow exponentially. So HPC is a science of bottlenecks. Machine learning models increased 1 million X in size in 7 years, right? And they're over-parameterized. We cannot make them smaller. And the amount of data that come with them is proportional. So you don't only have a lot of compute to do. You don't only have a lot of operators, because this is a model size. You have a lot of operands. You have a lot of data, right? So the challenges are a lot. Because remember, I told you, in each HPC type of problem, you usually have one or so bottlenecks. Here you can vary it easily. By just defining the scale on the model and training strategy and dataset, you can easily make it memory capacity bound, so it's bound by the capacity of the memory, or I/O by the storage, right? You're as fast as how fast you read from the storage system, or by the communication, the network, or by the compute, or latency. Depending on how you change it, it can be any of these, which even makes it more tricky problem to optimize. I will skip through the next. You have the entire set of slides you can check. And those were more like examples to motivate you more on applying scaling to solve problems that are kind of, were basically intractable without AI, right? So using AI to make things faster is nice, but the question is, can you solve intractable problems? This is what really gets nicer. I can probably cover it in the other slide, the other lecture in 2 days, and also I would be glad to discuss it offline anytime. Just one more thing is this is maybe, I guess, the slide before the last slide. So all what I said now is okay, it's nice in commercial space. You use ChatGPT, it gives you wrong results, you call it hallucination. It's okay, nobody would get harmed, right? You just see funny jokes online about weird content, but in science and engineering, you cannot tolerate all that. There's stuff you have to handle. And those are just some of the challenges that are not yet solved that a lot of people on the science and engineering side and also on the computer science side would need to resolve for these technologies to be mature and reliable enough to use in simulations. Some of it relates to the model itself, how to handle tokenization for arbitrary data, right? Remember, we said it just takes tokens, large language model, but if I have different type of data sets as a scientist or an engineer, how do I find tokenization? How do I encode it also, right? How do I decode? How do I explicit output coming out? How do I handle long input sequences? How do I reconcile out of order data? Because in science, sometimes your measurements just come in different order, not in order from some instrument or so on. How do you handle multimodal, different contents? Because in science, sometimes you have different types of data going into a model where you want to understand from. There's issues related to data itself, which is, for example, massive sizes. Remember, we said it was trained on 20 trillion tokens. That's nothing, that's text. Text is not so dense. 20 trillion tokens is just a few terabytes, a few hundred terabytes. It's nothing. But only just one, device like LHC or ITER or square kilometer array, they generate, order of tens of petabytes per day or something like that, per year, sorry, right? And that's every year. Your data is also semi-structured if you're a scientist or an engineer. Usually it's not just clean text or images. Data is semi-structured. And other main tools, how do you curate your data set? How do you clean up your data set? How do you do training? Some of it also matters, how do I integrate into my simulations or my workflow, right? How do I guarantee correctness and uncertainty? This is an open problem, nobody has to resolve it. People are working on it, but still it's an open problem. How do I do interaction between a simulation and model? I don't want to do this offline. I don't want to do it in tandem. I train or do inference as I train. All these are open, unsolved problems that hopefully in the next few years, from the scientific community, people would start to look at, that in the commercial space are not really issues. Final thing, generative AI is basically a set of methodologies to produce content. Remember, in all my example, I was saying prediction. Well, generative AI is just predicting something new, basically, that fits what you gave it as input, right? This is what ChatGPT is. It still is predicting, it's just not predicting something you would expect. So it's called generative, so it's generating new content. Nonetheless, training is the same. There are different flavors to it that I guess probably don't discuss now. Maybe in 2 days I will elaborate on generative AI really, like GANs, LLMs, and diffusion models. And my last slide is basically the first slide I started with. That, again, if you're a fresh or junior scientist and engineer, you might be witnessing a once-in-a-life opportunity. Might not, but you might. So you probably might want to keep attention on what's happening in that space. Don't throw all your work and say, oh, let's do all AI. It doesn't work this way. Just keep an eye on what's happening. Educate yourself more on it. Keep engaged. You don't need to be an expert that develops AI. You will be a user, but keep an eye, understand the fundamentals, right? Keep an eye on the tools, understand what's happening, and also keep engaging with people in your domain that will try to solve these problems, right? Because trust me, this will not be solved by industry because there is no money in science, right? There's no money in science, basically. So there's money maybe in applications like NLP, images, but nobody cares about, I don't know, like astrophysics or whatever. Nobody really cares. So industry will not solve these problems. You have to resolve these issues on your own. So keep an eye on it and basically similar to how some entire disciplines were reshaped by computers when they were introduced. It might be again at this point. I hope that the aim, I know it was long, sorry for that, and it's the end of the day, you're tired, I know that also. I hope it was enough to motivate you. I'm here until the end of Friday, and if you have any questions anytime, even after the school ends, I'll be glad to answer. Thank you.
Thank you, Mohammed. Okay, we are on time. And if there are any questions? Yes. Alexander. Okay. Oh.
Sorry, can you repeat the last part? I heard the first part, but not the last part.
I mean, when you know, for training those large models, you have billions of data points of files that you need to deal with. And often the HPC system limits the number of files per user on the system, and it's just, you have to process things in batch, make large archives or whatever. So it's not even the computing itself, but it's just the data processing before you can even start.
Yeah. Good, very good question. So the question, to summarize, is, again, like we said, it's the issue of bottlenecks. And as he's asking exactly, your bottleneck can be just a storage. Yeah, not any of this compute or communication, just you have so much data spread in small files, and supercomputers were designed to handle a small amount of big files. This is POSIX compliant, a Lustre-like file system and such. Now what to do, right? One push is going to object storage, like for example, DAOs and systems like Aurora are doing. Another thing is to try to not train with all this data, so you train on stages, right? And this is a lot of people are doing. One third direction, and actually I have a paper this week, it's in NeurIPS this week, which is not to train with the data itself, but you do hiding of the samples. So you do tricks to not read all the data all the time, but you shuffle using the network. Because if you're going epochs, in each epoch you're reseeing the data but in a different order, what you would want to do is to shuffle using the network. This way you can just escape an order of magnitude time waste, just going to the storage back and forth. But yes, what you're saying is exactly true. The sentiment of it is true. If you go for really large scale, especially for stuff that's so dense and occupies a lot of memories, not text, basically anything but text, you will probably be stuck at storage. And then we know that in HPC, like there are HPC applications where you're already stuck in storage. So this should just be another application basically where you're bound by storage.
Okay, another questions? Anyone? Okay, we have two more.
Thank you. Ru from Philippines. I'm just wondering, how do you know you have an optimal or a good enough number of neurons, layers, and what activation function to use?
So yeah, so again, a lot of it is empirical. What these studies on what they call scaling laws found that roughly you want to maintain the ratio of samples, as in training samples or tokens, proportional to the number of parameters. And the numbers are usually 1 to 10 or 1 to 20. So for each 20 tokens or samples, you need one parameter at least. There's no theory that drives that. If you read the literature on it, there's some theoretical analysis with some guarantees, but it's not like some exact equation that says you must use this if it's this, or it gives you a bound. So a lot of it is experimental, but what we know, at least empirically from all the testing that happened, is that yes, there is a certain ratio you want to keep, and it fluctuates between 3 to 1 to 20 to 1. 3 to 1, so 3 inputs or samples to one parameter. One neuron, basically. One input to a neuron, weight to a neuron, right? Or 20 to 1, so somewhere around that, which is, again, empirical. I agree, it's not satisfying if you like rigor, but again, here we are. Any other question? Just one in the back.
Hello, my name is Samsuri from Indonesia. For AI training and deep learning and also machine learning is the biggest challenge is data preparation. Can you tell the story about your data preparation regarding the LLM?
Yeah.
And
So
the next question is any different method between data preparation for AI, deep learning, and machine learning itself? Thank you very much.
yeah. Well, I have a good story actually. That is summarized in one slide. Yeah, this one on the right side. So this is work that when I engaged in it with collaborators, they were basically trying to see the productive performance of solubility of compounds, and they predict how soluble a compound is in some liquid, right? There's a lot of data already existing out there. We want to train a model, right? So what we realized is we spent 1.5 years to make the data set, to make the curation of the data set, right? And that involved 3 revisions. This was in Nature Scientific Data. They requested like a lot of reviews because, hey, how do I guarantee, this data set is a replication of this data set, or this data set interacts with this data set, or there's an intersection, or there's data that is not relevant to what you want to predict in solubility. So what we found was the hard way is that there's lack of tools in creation of data set on how you create data sets. And actually, I even have it in one of these slides here. Like this one. That data set preparation or creation is a very human labor intensive process. Engineers do at companies. In science, like I write, it's 10x a nightmare. Because if you want to clean and prepare the data set, if it's done in a commercial product, images or like text, then you can find some automated way, or you can find a way to outsource to cheaper labor, which actually what OpenAI did. But by definition, if you work on a science problem, the person who's going to do that is a PhD level person. You don't have enough of these to sit around, take data sets, clean them up, remove bad data and run stuff. So this is a big issue that actually probably is where a lot of the effort and whoever masters this part is probably gonna take a lot of strides above other people. And there's no solution for it. So this is one thing the community should rally around. How to make tools for making creation of data sets and sharing of data sets and cleanup of data sets. And also attribution. Okay, where did this come from? Because this is important in science. It's not important in commercial space. Commercial space, you don't know even what OpenAI trained on. There's claims even they just they scrap the internet, get images, text, whatever they trained on, which you don't own, by the way. But in science, you cannot do that. You have to have attribution. Because you want to know if this is the output, where did it exactly come from? So I can track it back and say, my prediction or my whatever I guessed is due to this data stuff. So it's even much worse. Like I said, 10x a nightmare.
Okay, one last question. It's already from this.
My name is Yuli from BRIN. I have a question. When we get the prediction result with higher accuracy, sometimes the prediction results become less accurate. For example, in real-world application. For example, in water quality in surface freshwater, in the river or in the lake, we use data from 20 years historical data. It gives the good results. However, the influence from land use, population, or the sudden earthquakes, which are not included in the historical data, change the structure of water bodies, so it's influenced the prediction results. So how we can solve this problem? Thank you.
Very good question, and the short answer, you can't. because again, remember, these models just train and define features, define things in your data you don't see. It learns everything, especially transformers, because you feed them tokens at a very fine-grained resolution. So what you as a human think is some error or something in the signal that is noise, basically, and you will ignore. The model might learn that. And this is an issue, and as the example I said, when people were giving CT scans, and the model started to learn the shape or how the text looks like, the metadata at the end of the file, and started to predict based on the data itself, not the image. So that's a problem of these black box models, right? And it throws you back to this correctness and uncertainty quantification, that if I cannot be sure that prediction is correct, then how would I trust it, right? A human might catch it, but we need an automated way, because if you deploy it in a production code simulation, how can you recover from that? So this is, again, one big open question. And that's why I think moving into the space of like commercial space, again, if the model is hallucinating or wrong, you don't care. But in science, it's hard. So I guess the battlefield for the next 10 years is basically this, exactly as you're saying. How to assure I can control the signal that's going in, or at least I can interpret it, or I can ground it in some reality. There's efforts, something called, for example, PIN, physics-informed neural networks, trying to ground the network, how it works according to some equations. So you can try to inject some checks. But more or less in the end, it's called black box optimization. And this is a standard mathematical term, by the way, black box optimization. As in, you cannot really go back and say, this prediction was generated because exactly the model found this feature in the data. So, yeah.
No problem. Okay, thank you. And do we have another? Yeah, we have 3 minutes. Any? Okay, there's no question. And so it will conclude our second day. And thank you, Mohammed. And we have an announcement from this. Oh, give an applause for everyone. Thank you. And we have an announcement from.
Okay, I just want to announce little things. First, about the coffee break. It's always available, so don't be ashamed to take a coffee if you are sleepy in here tomorrow. Because I ask to available every day, not just only a break time. And the second thing is about tomorrow. We will have parallel class, and the class will be in this side. The class A, that is for bioinformatics, group of life science, and then we have in here for earth science, and the third one in the computer science. So tomorrow will be parallel session. So for those who still catch up today, because the background not computer science, don't worry. Tomorrow will be your favorite subject. Okay, and then apa namanya nih kalau kue ada apa? Snack. Apa namanya? Oh, snack. Snacks for break this evening, coffee break is already available, but also the class is concluded. So bring the bring the foods to the dormitory in case it is not being eaten, then it will be trash. So sorry. So the